Hello and good morning everyone guys. I welcome you all once again to this wonderful channel by Unacademy NEET English. I believe you all are doing good and having a great time. Well, my name is Kar Khurshid Alam and you can also call me KK sir. But before we move ahead, I want quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats quickly. Let me know in the chats quickly. Am I audible and visible to each and everyone? Let me know in the chats quickly. Okay, all right. I believe that we are live now and super excited for today's session. In today's session, we will cover the entire class 11th organic chemistry. Well, my dear lovely students, I would want you all guys to mark the attendance by smashing the like button and also do share the stream with everyone around. I would want you all guys to be with me till end of this session. So grab your pen, open your notebook, let's get to the work together. So are you excited for today's session? Let me know in the chats quickly so that we will start today's session. Are you guys super excited for today's session? Let me know in the chats quickly. Let me know in the chats quickly. Show some Josh in the chats so that I can understand that Josh, your Josh is very high. Come on, come on. Come on, show some Josh in the chats quickly. So are you ready to complete today's class 11th organic chemistry in this one shot? Are you ready for this shot? Come on, come on, come on, my dear lovely students. Yes, yes, that is great, that is great, that is great. So without wasting time, let's get started with the first chapter of your, class 11th, and that is what we call General Organic Chemistry, or that is known as what we call GOC. First chapter of your class 11th Organic Chemistry is simply GOC. After completing GOC, we will start isomerism, and after that, we will start hydrocarbon chapter. So in nutshell, we are going to complete what we call class 11th organic chemistry. Just a moment, give me a second so that we will start with GOC. So my dear lovely students, this will be our first topic. It will be General Organic Chemistry. Now, are you ready for this chapter? Tell me, are you ready for this chapter? This will be a mega marathon and this session will be of 10 to 11 hours. Duration will be 10 to 11 hours. But I would want you all guys to be with me till end of this session. So let's get started. Let's get started. The first question in this is electronic displacement effects. We know electronic displacement effects are of two types. One is a permanent effect, another is a temporary effect. But in GOC, the most important effect is the permanent one, which includes inductive effect, resonance effect, and my dear students, hyperconjugation effect. And among these three, which one is the strongest effect? Resonance effect or mesomeric effect is the strongest effect. After that, it is hyperconjugation effect. After that, it is inductive effect. But remember, except halogens, because for halogens, it is inductive effect which is powerful as compared to resonance, because we know halogens show two effects. One is minus I, another is plus R, and in that I is stronger than resonance. Another effect which is known as temporary effect, it is of two types. One is electromeric effect, another is inductomeric effect. So let's discuss these one by one. Let's start with inductive effect. Now, what is inductive effect? According to your NCERT textbook, what is the definition of inductive effect? Have a look. Inductive effect means, my dear lovely students, inductive effect means simply. Inductive effect simply means, have a look. Inductive effect means simply polarization of, say this bond, say this is polarization. Just a moment. It is polarization of a sigma bond. It's a polarization of sigma bond caused by polarization of its adjacent sigma bond. What is meant by that? Listen carefully. Have a look. What is meant by this statement? Have a look. Now, say for example, you are having a carbon chain like this. If you are having a carbon chain like this, tell me, if we talk about this carbon chain, can we simply say that this carbon and this carbon have similar electronegativity? Similarly, this carbon and this carbon are having same electronegativity. This carbon and this carbon is having same electronegativity, which clearly indicates that there will be no displacement of electron at all. So there will be no displacement of electron. That means there will be no polarization at all. But my dear lovely students, if carbon chain is like this, it is attached to, say for example, electron withdrawing group, let us suppose chlorine. What will happen over here? Have a look. This chlorine is more electronegative as compared to carbon, so it will withdraw sigma electrons towards itself and it will acquire a partial negative charge. This carbon will acquire a partial positive charge. Now listen carefully. So what has happened in this bond? In this bond there is polarization. Displacement of sigma electron has happened in this bond, or we can simply say polarization has been happened during this bond because of this partial negative and partial positive charge. So polarity gets developed, polarization takes place in this bond. Now listen carefully. Now carbon and carbon, they are not similar carbons like these, because this carbon is having partial positive charge, this carbon is neutral, and among partial positive charged carbon and neutral carbon, we know partial positive charge is having more electronegativity as compared to neutral carbon, so it will withdraw its electron towards itself, so it will acquire a partial positive charge. Now can I say in this bond polarization occurs, but during this bond, carbon-carbon bond, here there will be no polarization. But here in this carbon-carbon bond, there is polarization. But this polarization occurs only due to polarization of this sigma bond. Is this clear to you? So polarization of this bond due to polarization of this sigma bond is simply known as what we call inductive effect. That means displacement of sigma electron in one bond due to displacement of sigma electron in its adjacent bond. According to NCERT textbook, this is known as what we call inductive effect. I hope this is clear. Now similarly, now this carbon is acquiring partial positive charge. It will also withdraw electron towards itself, so here will be partial positive charge. That means in bond 3, that means between carbon and carbon, once again displacement of sigma electron has been taken place. Once again polarization has been taken place, but this polarization or this displacement of electron has been taken place in bond 3 because of bond 2. That means due to its adjacent bond. So whenever displacement of sigma electron or polarization of any sigma bond takes place due to displacement of electron or due to polarization of sigma bond, but that sigma bond should be adjacent to that. This is known as what we call inductive effect. So in this case, inductive effect is present, but here there is no inductive effect as there is no polarization or displacement of sigma electron. Similarly, my dear lovely students, have a look. If we talk about this carbon chain, here bond between carbon and magnesium is there. What is magnesium? Magnesium is a metal. We know between carbon and magnesium, carbon is more electron negative, carbon is more electronegative, so it will withdraw its electrons towards itself. So this carbon will acquire a negative charge and this will acquire a partial positive charge. That clearly indicates that during this bond there is polarization, or during one bond there is displacement of sigma electron. Now as this acquires now partial negative charge, it will repel its electron towards this. That means it will donate electron towards this and it will acquire a partial negative charge. That means once again a polarization occurs in this bond or displacement of electron takes place in this bond due to displacement of electron or polarization of this adjacent bond. Similarly, my dear students, in bond 3, now displacement of electron, sigma electron or polarization will take place. But this displacement or this polarization in this bond is because of this bond. That means polarization or displacement of sigma electron in any sigma bond due to polarization or displacement of electron in its adjacent sigma bond is known as what we call inductive effect. I hope definition of inductive effect is clear to you. Now let me know in the chats, is this clear to you? Is definition of inductive effect clear to you? Let me know quickly. Let me know quickly, my dear lovely students. Let me know in the chats. Let me know in the chats quickly. Let me know in the chats quickly. Is this clear to you? Is definition of inductive effect clear to you? Come on, everyone, come on. And if it is clear to you, show some respect, show some green hearts in the chats quickly. Show some green hearts in the chats quickly if this is clear to you. If this is clear to you. Come on, my dear lovely students. Come on. Come on. Lovely, lovely. Need some green hearts. Quick. Quick. That's great. That is great. God bless you all. God bless you all. Now, after this. So this is definition of inductive effect. After this, let me tell you that you should know these points. You should know these points. Point number 1. That means characteristics of inductive effect. Point number 1, that inductive effect is a permanent effect. It is a permanent effect. This is point number 1, that inductive effect is a permanent effect. Point number 2, it involves partial displacement or displacement of sigma electrons only. Partial displacement or displacement of sigma electrons only. Listen carefully. After that, remember, it is unidirectional. Or you can say it is irreversible. It's an irreversible effect. Listen carefully. Now, after that, remember, it is distance dependent. It is distance dependent and decreases due to increase in distance. Decreases due to increase in distance. That means it is inversely proportional to the distance. Inductive effect is inversely proportional to the distance. Point number 5. It is a relative effect. So whenever relative term is there, that means there must be some standard reference. So as it's a relative effect, that's why the standard reference for inductive effect is hydrogen or CH bond. And remember, my dear lovely students, inductive effect for hydrogen is assumed to be 0. Is assumed to be 0. That means hydrogen neither donates electrons nor withdraws electrons as per inductive effect is concerned. But any atom or any group which donates sigma electrons more strongly than hydrogen shows electron donating inductive effect, and any atom or any group which withdraws sigma electrons more strongly than hydrogen shows -I or electron withdrawing effect. So inductive effect basically is of two types according to Ingold convention. And what are those types? Those types are what we call -I, that means electron withdrawing inductive effect, and +I, that means what we call electron donating inductive effect. What is electron withdrawing inductive effect or -I? It is simply that inductive effect with the help of which any atom or any group withdraws sigma electrons towards itself more strongly than hydrogen. But there are few groups which you should remember that these are basically withdrawing sigma electrons more strongly than hydrogen, and this series is known as what we call plus I series. Now, there is a trick to remember this series. If you want to remember with the help of the trick is like this. So it's no Ferrari, no Rolls Royce, so rich, so home, no home, so no soap can stop carbon. Father Carl Braun in office collecting orders, chop sushi sir, oh triple new phenyl double. So you should remember at least these groups. Now after that, another is electron donating effect, inductive effect. That means it is plus I effect. That means it is that inductive effect with the help of which any atom or any group donates sigma electrons but more strongly than hydrogen. Remember that. So these are the groups in this. This is, I mean, say CH2 minus, NH minus, O minus, CO minus. That means anions first. After that, it's alkyl, in general, tertiary, secondary, then methyl, what we call primary, then methyl, then TD. That means tritium or tritium, and after that, it's isotope of hydrogen, deuterium as well. So this is the trick. Can no one cook? Try some extra meals, tasty dinner. So you should remember these groups as well. Now, after that, my dear lovely students, there is what we call applications of inductive effect. Now, what are the applications of inductive? First application is stability of positively charged species. Now remember, stability of positively charged species is directly proportional to, remember this, directly proportional to plus I, that means electron donating group, and it is inversely proportional to minus I. That means whenever electron donating group is attached to what we call a positively charged species, it stabilizes that positively charged species, it increases the stability, and it decreases or destabilizes the positive charge. Number one formula is this. You should remember this one. You should remember this. Another, you can simply say like this. First of all, it is plus I. After that, it is neutral. After that, it's minus I. Now the question is, what is neutral? That means any group which neither shows plus I nor shows minus I, which neither shows electron donating inductive effect nor shows electron withdrawing effect. You have to write down that here. But this is plus I. Say for example, our question contains more than one plus I groups. Then which plus I should we write first? We should write strong first. After that, we should write weak. So you have to write strong to weak first. Here you have to write down weak first, and after that you have to write down strong. Now, what is meant by this? Let's try to understand this with the help of simple example or with the help of simple question. Now, have a look. Have a look, my dear lovely students. Say for example, question is compare stability. Say for example, question is like this. Compare stability. So stability, we have to compare stability of positively charged species. Say for example, first one is like this. It is CH3 having a positive charge. That means this is the carbocation. Carbon having a positive charge is known as carbocation. So this is first one. Second one is like this. CH3, CH2 with a positive charge. Listen carefully. Third one is like this. CH3, CH, CH3 with a positive charge. And then the fourth one is, let me write down that here. Have a look. Fourth one is like this. CH3, C, CH3, CH3 with a positive charge. Now, first of all, you should know that this positively charged species is attached to hydrogen only, and hydrogens neither show plus I nor show minus I. That means this carbocation is attached to that atom which is basically neutral. Neutral means which neither shows plus I nor shows minus I. Here neutral means that. Okay, now this is attached to CH3, and we know CH3 group is a plus I group. Here, this is attached to CH3 on one side as well as on another side. That means there are two CH3 groups. That means there are two plus I groups attached to this positively charged species. Similarly, here are three plus I groups attached to the positively charged species. Now, my dear lovely students, we have to simply compare stability. Now, have a look. How to compare stability? First of all, you have to write down plus I, then neutral, then minus I. Now look towards this question. First, we have to write down plus I. But among plus I, we have to write down strong first and then weak first. That means first of all, we will write down plus I. Plus I are these groups. This is neutral, and at the end we will write down this one. So among these, which is having strong plus I or more plus I? It is this fourth. So can I write down 4? After that, can I write down it is 3? After that, can I write down it is this 2? And finally, it is 1. Now, is this clear to you? Let me know in the chats quickly. Is this clear to you? Let me know in the chats quickly. Is this clear to you? Let me know in the chats quickly. Great. Many among you have given me the answer as well. 4, 3, 2, 1 is the right answer. Let me know in the chats quick. Is this clear to you? Is this clear to you? First, you have to find out plus I, but which plus I? Stronger one first, then weaker. After that, say you have to write down neutral, but after that you have to write down minus I, but there was no minus I group. That's why first I will write down plus I, stronger, weaker. After that, this one, then finally this neutral species. I hope this is clear. After that, let me give you another example over here. Let's take another example over here. Tell me. Let's take another example over here. Have a look. If I write CH3 having what we call once again a positive charge. Number second example is like this. That this is like this. CH2 positive, CH2Cl is another example. Third example is like this. It is NO2, then CH2, then CH2 with a positive charge. And then fourth one is FCH2, CH2 with a positive charge. My dear lovely students, now have a look. Once again, this carbocation or positive charge is attached to hydrogen, so this is neutral. But this carbocation or positive charge is attached to CH2Cl. Because of this Cl, it becomes minus I group. As we know, Cl is electron withdrawing or minus I group. Now, NO2 is also minus I group. This F is also minus I group. That means there are 3 minus I groups and 1 neutral species. But as per stability of positive charged species is concerned, first of all, we have to write down plus I. But there is no plus I. After that, we have to write down, have a look. First of all, we have to write down plus I. But if there is no plus I, we will write down neutral first. So which one is neutral? Neutral is first one. So I will write down first. After that, we have to write down minus I. We have to write down minus I. But which one? Weak first. After that, stronger one. Among these, which one is stronger and which one is weak? For that, you should remember. You should remember this. You should remember this. You should remember this one. Have a look. Have a look. This is fluorine. This is chlorine. And this is what we call nitro. These 3 groups are there. So which comes first in alphabet? Which comes first in, this preference order? Have a look. Have a look. Have a look. It is, first of all, it is this nitro group. Have a look. First of all, it is this nitro group. After that, it is fluorine. After that, it is chlorine. So which one is stronger? Nitro is stronger. After that, fluorine. After that, chlorine. So we have to write down weaker first. We have to write down weaker first. Weaker is chlorine. Now, let's go to our question and try to solve this question. Now tell me. Nitro is stronger. After that, fluorine. After that, chlorine. So we have to write down weaker one. Weaker is chlorine. After that, it is fluorine. And after that, it is what we call nitro. That is why this will be the answer of this question. Is this clear to you? Let me know in the chats quickly. Is this clear to you? Let me know in the chats quickly. Let me know in the chats quickly, my dear lovely students. Okay, Netik. God bless you, Netik. God bless you. God bless everyone. God bless everyone. That's great. That is great. This is clear to you. This is clear to you. Okay. Okay, my dear lovely students. Let's take another example. Let's take another example of this. Let me know in the chats quickly what will be the answer of this question. One is CH3 with a positive charge. Another is FCH2 with a positive charge. Another is, say for example, CH2 with a positive charge. Another is CH3, CH2 with a positive charge, and another one is CH3, CH, CH3 with a positive charge. Now, first of all, we should know that this positive charge is attached to hydrogen. That means this is the neutral species. This is attached indirectly to this fluorine. So this, because of fluorine, it group becomes minus I. Because of chlorine, it becomes minus I. But because of this CH3 group we know is plus I group. Here there are two plus I groups. Now we have to write as per positive charged species is concerned, stability of positive charged species is concerned, we have to write first. Which one? Come on. Which one? Plus I. But which plus I? As there are two plus I groups. Stronger first and then weaker. After that, it should be neutral. After that, it should be minus I. But among minus I, it should be weaker minus I first. After that, stronger one. Now, let me know in the chats what will be the answer. Answer will be simply 5. After that, it will be 4. After that, it will be 1. After that, it will be 3. After that, it will be 2. Because among plus I, stronger one first, then weaker, and then neutral, and among minus I, weaker first, then stronger. Is this clear to each and every one? Is this clear to each and every one? 5, 4, 1, 3, 2 is the right answer. God bless you, everyone. God bless you, everyone. Is this clear? Is this clear, my dear lovely students? Okay, that is great. That is great. That is great. After that, my dear lovely students, after that, we will be having another, that is negatively charged species. And listen carefully. For negatively charged species, you know that negatively charged species are stabilized due to minus I groups. That means if minus I group is attached to that carbon, that species which is having negative charge, minus I or electron withdrawing group increases the stability. That means it stabilizes the negative charge. And it is inversely proportional to plus I. Listen carefully. So this is point number 1. Second point is, remember, you should write minus I first, then neutral, then plus I. But among minus I, it should be stronger first, after that weaker one. Similarly, among plus I, weaker should be first, and after that it should be stronger. So this is another formula when you compare what we call stability of negatively charged species. For example, have a look. Let's take this question. Compare stability. Compare stability. Obviously of negatively charged species. Say for example, first one is like this. CH3 having negative charge. Second one is this. CH3 having this, CH2 having negative charge attached to CH3. After that, it is CH3, CH, CH3. After that, my dear lovely students, it is CH3, then C, then CH3, then CH3, then this is having a negative charge. Now, first of all, what we will do? We will simply look towards those species which are attached to a negatively charged species. This is hydrogen, so this can be simply neutral. This CH3 is plus I group. This CH3 is plus I group. This CH3 is also plus I group. That means here 2 plus I groups are attached. Here 3 plus I groups are attached to this negatively charged species. So more the number of plus I groups, more stronger will be the plus I effect. Now tell me, my dear lovely students, these are the negatively charged species. These are the negatively charged species. Now let me know, in case of negative charged species, what we have to do is, we have to write down first minus I. But is there any minus I? There is no minus I. After that, we will write down neutral. Is there any neutral species there? Yes, it is one. After that, we have to write down plus I. But which plus I, my dear lovely students? Which one? Weaker one first. Among these, which one is weaker? Weaker is this one. So, I will write down this. After that, little bit stronger. That means this one. After that, this one. So, the answer will become simply 1, 2, 3, 4. Is this clear? Is this clear, my dear lovely students? Is this clear? Let me know in the chats. Is this clear? Quick. Everyone is giving me the answer. That means this is clear to each and everyone. That means this is clear to each and everyone. God bless you. God bless you. Okay, someone is saying what is meant by relative effect? Relative effect means basically you are saying that inductive effect is of two types. One is electron donating, another is withdrawing. But you are basically comparing this inductive effect of inductive effect of, say for example, those groups which show plus I with hydrogen. It is not directly that you are saying this is what we call plus I. It is plus I because it donates more stronger electrons than hydrogen. That means in comparison to hydrogen, because standard reference is there. I hope this is clear to you. Relative means that means you are comparing its effect with, say hydrogen. Similarly, minus I group. What is meant by minus I group? Any group which withdraws sigma electrons, but in comparison to what we call hydrogen more strongly than hydrogen. That means this is the relative effect. I hope this is clear. I hope this is clear. Okay. Okay, my dear lovely students. After this, let me give you another example. Let's take another example. You try to solve this question. Let's take another example. Try to solve this question. It's like this. FCH2, CH2 negative. My dear lovely students, tell me, what about this? Cl, CH2, CH2 negative. What about this? This is NO2, CH2, CH2 negative. Now tell me, my dear lovely students, first of all, what will we do? We will see what are the atoms or groups attached to this negative charged species. It's hydrogen. Hydrogen neither shows plus I nor shows minus I. So I will say N, neutral. Now what about F? It shows minus I effect. What about Cl? It shows minus I effect. What about NO2? It shows minus I effect. Now, in case of negative charged species, what we have to do is, we have to write down minus I first, then neutral, then plus I. But which minus I, my dear lovely students, stronger? These all are minus I. So we will write down minus I first, but as there are three minus I groups, so which minus I will we write first? We will write that minus I first, which is more stronger, and we know NO2 is stronger, after that fluorine, after that chlorine. So we will write down 4 first, after that we will write down 2, after that we will write down 3, after that we will write down neutral. After this we have to write down plus I, but there is no plus I. Hence, the answer of this question is simply 4, 2, 3, 1. So, let me know quickly, is this clear? Everyone is giving me the answer. God bless you. And I want everyone in GMC. Come on. In your respective GMCs, you have to go there. You have to go there. Come on. Come on, my dear lovely students. You have to show NTA that you are the best. Whatever they did, that simply do not bother you at all. You will crack and you will go to your respective GMCs. Definitely. Come on. Come on, my dear lovely students. Now, after this, if I give you one more example like this, CH3 having negative charge, then let us say NO2 is attached to this, what we call negative charged species through this CH2. Now, after that, it is F, CH2, CH2 negative. Then, my dear lovely students, let us say, fourth example is CH3, CH2 having negative charge. And let us say, fifth example is there. Let us say there is another example. Let's say there are 5 examples in this question. Now, tell me, what will we do? First of all, we know this is neutral. What about this NO2? Minus I group. That is good. What about this F? It's minus I group. Very good. What about this CH3? It is plus I group. What about this CH3? This is plus I group. But there are 2 plus I groups. Now, what we have to write first? What we have to write first? Have a look. Have a look. We have to write down minus I first. But if there are more than 1 minus I groups, then stronger one first. After that, weaker one. That means we will write down minus I first. That means 2 or 3. 2 is NO2, F is, 3 is F. We know NO2 is showing stronger minus I as compared to F. So we will write down 2. After that, we will write down 3. So first minus I. After that, neutral. After that, plus I. But among plus I, weaker one first. This is weaker. This is stronger as this is having 2 plus I groups. So I will write down 4. And finally, I will write down 5. So 2, 3, 1, 4, 5 will be the answer. That is great. That is great. Come on, come on, come on. 2, 3, 1, 4, 5 will be the right answer. Great. That is great. That is great. That is great, my dear lovely students. That is great. That is great. After that, my dear lovely students, our third application is acidic strength. Our third application is acidic strength. Have a look. Remember forever that acidic strength, I mean say acidic strength or strength of an acid, any acid, is directly proportional to stability of its conjugate base. Because we are talking about basically right now those acids which can donate H positive. Whenever acid donates H positive or loses H positive, the negatively charged species obtained after acid loses H positive is known as conjugate base. Say for example, if we talk about carboxylic acid, when carboxylic acid loses H positive, it will result in the formation of RCOO minus. That means this is the conjugate base of this carboxylic acid. Similarly, if we talk about alcohol, when alcohol loses H positive, it results in the formation of RO negative. So RO negative means alkoxide ion is the conjugate base of alcohol. So I hope this is clear. So acid strength is directly proportional to stability of conjugate base. This is formula number 1. Formula number 2, remember, strength of acid is directly proportional to minus I and inversely proportional to plus I. Remember, this is another formula. This is formula number 2. Similarly, my dear lovely students, you should remember that strength of acid is directly proportional to Ka. That means dissociation constant of acid, and it is inversely proportional to pKa. You should know this because you have completed your equilibrium as well. After that, strength of acid is directly proportional to H positive ion concentration and it is inversely proportional to pH. This is another formula for acidic strength. Similarly, strength of acid is directly proportional to pKb and it is inversely proportional to dissociation constant of base Kb. Similarly, my dear lovely students, strength of acid is directly proportional to pOH and it is inversely proportional to OH minus ion concentration. It is inversely proportional to OH minus ion concentration. So I hope you know all these formulas. If you don't know, try to remember these formulas, please. Try to remember these formulas. This is 1, these are 2 formulas, 3, these are 2 more, 5, these are 2 more, 7, these are 2 more, 9, these are 2 more, 11. So these are the 11 formulas you should know related to, say acidic strength. Now, say for example, and one more, I am giving you one more. Remember this. First of all, write down minus I, then write neutral species, then write plus I. But here you have to write down from stronger to weaker. Here you have to write down weaker to stronger. That means with the help of this formula, you can find out acidic strength. Once you know acidic strength, then you can say stability of conjugate base. You can say Ka, pKa, H positive, pH, pKb, Kb, pOH, OH minus ion concentration. Now how? Have a look. Say for example, question is like this. Compare acidic strength. Suppose you have to compare acidic strength. And say for example, first question is like this. It is HCOOH. Then second is ClCH2COOH. Third one is CH3COOH. And fourth one is FCH2COOH. Now, how to check which acid is stronger acid? With the help of this one simply. Now have a look. This is simple formula. Now look towards these. This is COH and to that COH H is attached and we know H is neutral species. To this COH, this CH2Cl is attached. So because of this Cl, it becomes minus I group. Because of this CH3, we can say CH3, that means plus I group is attached to this carboxylic acid. Similarly, because of this F, we can say minus I group is attached to COH. First of all, we have to write down minus I. Now, we have to write down minus I. Minus I groups are 2 in number, but which minus I we have to write down? Stronger first, and after that weaker one. That means I will write down stronger. Which among F and Cl is stronger? F is stronger, so I will write down 4. After that, I will write down 2. So first of all, we will write down minus I groups. After that, it's neutral. That means 1. After that, we will write down, I mean to say, plus I group. So the answer of acidic strength will be this. This will be the acidic strength order. Is this clear to you? Is this clear to you? Let me know quickly. Is this clear to you? Is this clear to you? Everyone, come on. Everyone is giving me the answer. That means this is clear to you. Now listen carefully. Say for example, question asked in your examination is that write down the stability order of their conjugate bases. Say for example, acids are given and the question is like this. What will be the order of stability of their conjugate bases? First of all, what will you do? You simply, at that time, you have to find out first of all acidic strength order. This is acidic strength order or strength of acid. But question is not, say for example, strength of acid. Question is stability order of their conjugate base. Have a look. We know strength of acid is directly proportional to stability of conjugate base. That means whatever is the acidic order, stability of conjugate base will be the same order. That means here we can say that this 4 is having stronger stable conjugate base as compared to 2. 2 is having stable conjugate base as compared to 1. 1 is having stable conjugate base as compared to 3. Similarly, if question is arrange these acids in their decreasing order of Ka value. Decreasing order of Ka value. That means whatever is this order, Ka will be same. What will be the decreasing order of pKa? Whatever is this order, pKa will be inverse. Why? Have a look. Have a look. Ka and pK are inversely related. Similarly, if question is saying that what will be the H positive ion concentration order? H positive ion concentration order will be same. What will be pH order? pH order will be inverse because strength of acid is inversely related to pH. So with the help of strength of acid, you can simply answer question of Ka, pKa, H positive, pH, pKb, Kb, pOH, OH minus ion concentration. I hope this is clear to each and everyone. Is this clear to each and everyone? Let me know quickly. Is this clear to you? Let me know quickly. Let me know quickly. Come on, my dear lovely students. Is this clear? Okay, someone is saying crystal clear. Great, great. Green hearts are there. That means this is clear to you. God bless you. God bless you. God bless you. Okay. Now, after this, if I write down like this, if question is like this, say for example, question is like this. Question is like this. First option is like this. COOH, and here it is electron withdrawing group. After that, it is like this. And after that, it is like this. So tell me what will be the acidic strength order. First of all, these acids are attached with the Cl is minus I group. This Cl is also showing minus I effect. This Cl is also minus I group. Now tell me, my dear lovely students. Here, the COH, if it is 1, this is 2, this is 3, this is 4. To this COH, Cl is attached to second carbon. To this COH, Cl is attached to third carbon. And to this, Cl is attached to fourth carbon. That means we have to check which one among these is showing stronger minus I effect. We know minus I effect is simply, we can find out minus I effect simply with the help of a rule, that is DNP rule, distance, number and power. First of all, check the distance. This is closer to, I mean say COH. This is farther away as compared to this one. So more will be the distance, lesser will be the inductive effect, or weaker will be the inductive effect. So can I say As this distance is less, so this is strongest inductive effect, then this, then this. So we have to write down stronger minus I. So the answer will be simply 1, 2, 3. So this will be simply the acidic order. This will simply be the acidic order. I hope this is clear. I hope this is clear. Is this clear to you? Is this clear to you? Yes, exactly. More the distance, weaker will be the inductive effect, because inductive effect is distance independent. Oh, sorry, distance dependent. It decreases with increase in distance. That means it is inversely proportional to what we call distance. Now, great. After that, for example, another example is like this. Say, for example, you have another example like this. Suppose you are having this one. COOH. Here it is F. COOH once again. And let us suppose F is here. Third one, let us suppose it's like this, COOH, and let us suppose F is here. What will be the answer? Come on, quickly. What will be the answer? Because all these groups are showing minus I, minus I, minus I. You have to write down stronger minus I first. Which one will be the strongest minus I? Closer to COH or which is far away from COH? It will be closer one. That means it is 3, after that 2, after that 1. And every one is giving me the right answer. 3, 2, 1 is the right answer. That is great. That is great. What about this one? What about this one? If you are having a structure like this, this is also an acid, this is alcohol. Now, let me tell me quickly what will be the answer. Here it will be, say for example, Cl and Cl. Tell me. It's like this. After that, fourth one is like this. Fourth one is like this. It's I, it's OH. Tell me quickly. This is minus I. This is minus I. Both these groups, there are two minus I groups. Here minus I group is only one. Here minus I group is only one. First of all, what will we do? Distance, number, power. That means distance is first. Distance is lesser in 2 and 4. That means 2 and 4 will be stronger acid. But after that, number here is more as compared to that. So we will write down 2 first. After that, we will write down 4 first. After that, among 1 and 4, distance, it is 3. And after that, it is 1. So this will be the answer, 2, 4, 3, 1. Now, is this clear? Is this clear? We are only talking about right now inductive effect. We are not talking about hyperconjugation or resonance. So no need to write down meta, para and all those things. Okay. Now after that, we will be having another question, that is basic strength of amines. But first of all, in general, remember, in general, we can simply say this one. In general, we can say basic strength is directly proportional to, listen carefully, it is directly proportional to plus I and it is inversely proportional to minus I. In general, basic strength is directly proportional to plus I and inversely proportional to minus I. Second thing is that, first of all, in general, you should write down plus I, then neutral, and after that, minus I. But listen carefully. Here, first of all, you should write down stronger to weaker, and here, you should write down weaker to stronger. Similarly, basic strength is directly proportional to, in general, it is directly proportional to stability of conjugate acid. It is directly proportional to stability of conjugate acid. And basic strength in general is directly proportional to Kb and inversely proportional to pKb. This is in general. Similarly, you can write down basic strength is inversely proportional to or directly proportional to pK and inversely proportional to K. Basic strength in general is directly proportional to OH minus ion concentration and inversely proportional to POH. That means opposite to that of acidic character. Similarly, basic strength is directly proportional to pH and inversely proportional to H positive ion concentration. But this is in general. But as per basic strength of amines is concerned, so listen carefully, as per basic strength of amines, we can say it is solvent dependent. We can say it is solvent dependent. Have a look. Number one, in gaseous phase, that means when solvent is not present in gaseous phase, or in non-aqueous media, or in aprotic solvent. If we talk about these, then remember forever, it is 3-degree amine which is more basic than 2-degree amine, and 2-degree amine is more basic than 1-degree amine. And remember, all these amines are more basic than ammonia. That means if you compare 3-degree, 2-degree, 1-degree amine with ammonia, ammonia will be at the end. So this is the basic character or basic order that is known as basis T. So we can simply say this is basis T order. Basis T order among amines in this medium. Similarly, my dear lovely students, in aqueous media, or you can say protic solvents, in protic solvents, what will be the order? Listen carefully. Order will be 2-degree, then it will be 1-degree, then it will be 3-degree, or order will be 2-degree, then 3-degree amines, then 1-degree amines. But listen carefully. This order is possible if in case of amines the value of R is CH3. That means the smaller value of alkyl. Similarly, this value is only at that time if R is ethyl group. That means if ethyl is attached to nitrogen. That means if you write down like this, CH3 NHCH3, CH3 NH2, CH3 whole 3N, then as value of R is CH3, your answer should be like this. But in comparison to ammonia, obviously ammonia will be at the end. So this is the basis T order as per solvents are concerned. But these are the basis T order of different amines, 1-degree, 2-degree, 3-degree amines, 1-degree, 2-degree and 3-degree amines. But if you are having question like this, say for example question is compare basis T. Compare basis T. Suppose question is like this. First question is like this. It is CH3 NH2. Listen carefully. After that it is CH3, then it is what we call NH, then it is CH3. Similarly, it is CH3, then it is N, then it is CH3, then it is CH3. Now listen carefully. Here in case of amine, this is primary amine, this is secondary amine, this is tertiary amine. And in these amines, what is the value of R? Value of R is CH3. And there is no, information whether solvent is polar protic solvent, I mean say whether solvent is protic solvent or whether solvent is aprotic solvent. When solvent is not given, when solvent is not mentioned, take water as solvent. Take water as solvent. That means we have to compare basicity of these 1 degree, 2 degree, 3 degree amines in protic solvent. That means in this one. And what is the value of R? Value of R is CH3. So what will be the order here? It will be 2 degree first, then 1 degree, then 3 degree. That means it will be 2 degree. That means it will be second one. Then 1 degree is first one. And then 3 degree is this one. So this will be the basicity order. Similarly, if question is like this, CH3, CH2, NH2. Once again, NH2 means this is primary amine. Number second, it is CH3, CH2, then NH, then CH2, CH3. Similarly, it is like this, CH3, CH2, then it is N, then it is CH2, CH3, then here it is CH2, CH3. Listen carefully, my dear lovely students. Once again, these are the amines, primary, secondary and tertiary amines, but solvent is not given. Whenever solvent is not given, take solvent as water. Take water as solvent. Now, this is polar protic solvent or protic solvent. So, here, what is the answer? It is first 2 degree, that means it is 2. But after that, it should be 3 degree. Have a look. Have a look. If R is CH2, CH3, 2 degree, 3 degree, 1 degree. That means I will write down 2, then I will write down 3. After that, I will write down 1. I hope this is clear. I hope this is clear. Let me know quickly, is this clear? Let me know quickly, is this clear? Come on, quickly. Yes, if you work, everything is possible. Nothing is impossible, let me tell you. Just try to work smartly, that's it. Try to work smartly, that's it. You can increase your marks easily. Now, after that, say for example, we are having another question. Let's take another example. Let's take another question. So, let us suppose another question is like this. Tell me the answer. Tell me the answer. This is CH3, CH2, NH2. Second one is CH3, CH3, NH2. Now, this is Cl, CH2, NH2. Now, listen carefully. Listen carefully. Can I say this is NH2, NH2, NH2? That means all these are primary amines. These all are primary amines. Now, when all are primary amines, what to do now? You have to check which group is this. This is plus I group. This is also plus I group. But this is an alkyl group. This is alkyl group. Alkyl groups in general show plus I. But if alkyl group is having branch, then it is stronger plus I as compared to this one. And this is having minus I. Now, listen carefully. Have a look. Have a look. Have a look. Have a look. Look towards this formula. Write plus I first, then neutral, then minus I. Write plus I first, then neutral, then minus I. Which plus I? Stronger one. Stronger one is 2. After that, it should be 1. After that, it should be 3. So this will be the answer. Very, very simple answer. Very, very simple answer. After that, if you are having a question like this, tell me the answer now. NH2, say for example, this is having F. This is NH2. NH2 is having F over here as well. Then NH2. To this NH2, at this position, it is CH3. And to this same amine, there is CH3 group now at this position. Tell me quickly. Can I say this is minus I? This is minus I. This is plus I. This is plus I. Now, which among these we have to write down first? We have to write down minus I first or plus I? We have to write down plus I first. We have to write down plus I first. That means we should compare these two only. This is, say weaker plus I as distance is more from this NH2. This is stronger plus I as distance is less. So I will write down 3 first. After that, I will write down 4. First plus I groups. After that, minus I. But among minus I, we have to write down weaker one. This will be weaker as distance is more. So I will write down 2. After that, I will write down 1. I hope this is clear to each and every one. I hope this is clear to each and every one. So it is 3, 4, 2 and 1. Because in these cases, you have to write weaker first and then stronger. Minus I should be weaker first, then stronger. I hope this is clear. I hope this is clear. Okay, that is great. That is great. Now, let's move to another question. But before discussing this resonance, we will first of all discuss, I mean to say this one. We should know first of all what is conjugation. Listen carefully. What is meant by conjugation? Conjugation means presence of p or d orbitals at 3 adjacent positions. At 3 adjacent positions. Parallel and within the same plane. Whenever you are having 3 p or d orbitals which are parallel and within the same plane and are present at 3 adjacent positions, we simply say molecule is having conjugation, and compound in which conjugation is present is known as conjugated compound. Now listen carefully. So what is conjugation? Presence of orbitals p or d at least at 3 adjacent positions, parallel and within the same plane with respect to each other is called conjugation. Now have a look. This conjugation is of 2 types. One is pi pi, another is pi p. What is meant by pi pi? Let's have a simple example over here. Simple example is like this. Have a look. If we talk about this unsaturated system, this is unsaturated. With respect to this unsaturated system, this is another unsaturated system. So let me check with respect to this. With respect to this. Can I say with respect to this? This is the atom, or this is the atom which is directly attached to this unsaturated system, or this is an unsaturated system, then this is the atom attached directly to this. Yes or no? So this atom is known as key atom. This atom is known as key atom. So it is, we are talking basically of this one, this atom or group. If this atom or group, this is the trick, if this atom or this group is having pi bond, listen, but first of all, carbon-carbon double bond should be present. So if this atom which is directly attached to carbon-carbon double bond is having pi bond, we will simply say that conjugation as pi-pi conjugation. We will simply say that conjugation as pi-pi conjugation. Similarly, if this is having what we call p orbital, which can overlap. If this is having p orbital, that p orbital can overlap with these p orbitals. If this is having p or d orbital, then we call at that time this conjugation as p-pi conjugation. Now, if that p orbital contains lone pair, we will call that as pi lone pair conjugation. If this p orbital contains negative charge, conjugation is known as pi negative charge conjugation. If that p orbital contains an odd electron, conjugation is known as pi odd electron. If that p orbital is vacant, then conjugation is known as pi vacant orbital conjugation. That means in nutshell, if this key atom or this group is having pi bond, or it's having lone pair, or it's having negative charge, or it's having odd electron, or if it is having vacant orbital, then we will simply say there is conjugation present within the molecule, and at that time compound is known as conjugated compound. But basically what is meant by conjugation, have a look. Actually conjugation means presence of p orbitals. Have a look, my dear lovely students. We know. What we know is that this is having p orbital, this is having p orbital. That is why they form a pi bond after, overlapping. As they form pi bond, that means their p orbitals have been overlapped so as to sideways overlapping. Because of sideways overlapping, pi bond has been formed. Similarly, this is having p orbital and this is having p orbital. Because of overlapping of p orbital, this pi bond has been formed. Now look towards this. Can I say 1, 2, 3, 4 p orbitals are there, which are parallel and within the same plane. Whenever you are having at least 3 p orbitals, maximum it can be 4, 5, but at least there are 3 p orbitals at 3 adjacent positions which are parallel and within the same plane. Hence, this is the compound in which conjugation is present. So the compound is conjugated compound. I hope this is clear. So I will simply write down over here that CH2 double bond CH, single bond CH, double bond CH2 is a conjugated compound. And in this conjugated compound, pi-pi conjugation is present. Similarly, if I write down like this, CH2 double bond CH, single bond NH2, and I will write down a lone pair here. So I will say with this pi bond, it is this p orbital which contains lone pair of electron which is in conjugation. Hence this is pi lone pair conjugation. Similarly, my dear lovely students, we can write down CH2 double bond CH, single bond CH2 having a negative charge. So with respect to this pi bond, it is this carbon having a negative charge in its p orbital. That's why this is known as pi negative charge conjugation or pi p conjugation. Similarly, if I write down like this, CH2 double bond CH, single bond CH2 with an odd electron. So this will be simply known as pi odd electron conjugation. Similarly, if I write like this, CH2 double bond CH, single bond CH2 with a positive charge. This carbon having a positive charge is a carbocation, and at that time this is having empty, vacant p orbital. So that's why I will simply show this is an example of what we call pi vacant orbital. Similarly, sometimes it is like this, CH2 double bond CH, single bond BH2. We know whenever boron forms 3 bonds, that means it's having 6 electrons. That means its p orbital is vacant. When its p orbital is vacant, so we can simply say this type of conjugation we can simply say as pi, what we call vacant orbital conjugation. But here vacant orbital is p orbital, vacant orbital is p orbital. Here vacant orbital is, this odd electron is present in p orbital, negative charge is present in p orbital, lone pair is present in p orbital. So generally, these types of, conjugation is known as pi-p, and this is known as pi-pi conjugation. So I hope this is clear to you what is meant by conjugation. So conjugation simply means presence of at least 3 p or d orbitals parallel with respect to each other and within the same plane at 3 adjacent positions. But with the help of the trick, you can simply check whether the conjugation is present or not. Now, so this is all about conjugation. After that, these compounds in which conjugation is present is known as conjugated compound, and the alternate positions like this. If this is position number 1, this is third. That means these are alternate positions. Similarly, alternate positions of conjugated compound are known as conjugate positions. They are known as conjugate positions. Now, look towards what is actually resonance. So if we talk about only conjugated system, remember, if we talk about conjugated compounds only, then what is meant by resonance? Resonance at that time is simply what we call delocalization of pi electrons. In case of conjugated compounds, what is resonance? Resonance means delocalization of pi electron. What is meant by delocalization of pi electron? Listen carefully. Delocalization of pi electron means it is basically these orbitals which have overlapped overlapped, but this overlap is partial overlap. This overlap is what we call partial overlap. So actually partial overlap of orbitals in such a way so that pi electron density remains same throughout. So what is meant by basically delocalization of pi electron? It is actually partial overlap of orbitals in such a way so that pi electrons throughout this ring will be same. That means whatever will be the pi electron density over here, it will be same over here, it will be same over here, same here, same here, same here. This is known as what we call resonance. But remember, my dear lovely students, this resonance takes place in this structure, and the structure in which partial overlap of orbital takes place, that means in which delocalization of pi electron takes place, is known as resonance hybrid. This is the actual structure of the molecule. And those structures which give information regarding this delocalization, they are not actual structures, they are hypothetical structures, and those structures are known as delocalized structures because they are giving information about delocalization. They are known as resonating structures because they give information about resonance, or they are known as canonical structures or contributing structures. They are always separated by means of double-headed arrow, but they are not actual structures. They exist only on paper, or we can simply say they exist on this board, or say smart panel. I hope this is clear to you. So delocalization is taking place here. Here, bonding is not delocalized. Bonding here is localized because this pi bond belongs to these two atoms only. This pi bond belongs to these two pi bonds, these two atoms only. And this pi bond belongs to these two atoms only. But here, pi electrons belongs to all these carbons. So this is the actual structure. This gives us information about basically the molecule, but this alone cannot give us information about the molecule. This alone cannot explain the properties of a molecule. This alone cannot explain properties of the molecule, but with the help of these, we can form this, and this can explain all the properties of the molecule. So this is what we call a resonance. But there are conditions for resonance. Remember, first condition is that all resonating structures must have same energy or nearly same energy. What is meant by that? Have a look. If you are having these two structures are identical structures. When they are identical, their stability will be same, their energy will be same. That means potential energy of first and potential energy of second is same. That means resonating structures must have same energy. As they have same energy, hence they can be resonating structures. Similarly, if we talk about this and this is neutral, this is charged. But neutral species are more stable as compared to this, but there is not that much difference. That means this is stable as compared to this. That means this is less energetic as compared to this, but energy difference is not that much. That is why we can simply say potential energy, that means energies of these two are almost same. Hence, as energies are almost same, hence they can also be what we call resonating structures of each other. But my dear lovely students, look towards this. Positive charge is present on less electronegative element. That means it is considered to be stable. But here, positive charge is present on more electronegative element. Here, positive charge is also present on more electronegative element. But my dear lovely students, this positive charged species is having complete octet. But here, this positive charge species is present on more electronegative element, but this does not have complete octet. That means this is least stable as compared to this. This is very less stable as compared to this. If this is very less stable as compared to this, that means this is very much energetic as compared to this. So energy difference here will be very high. Hence, these two cannot be what we call resonating structures of each other. So there must be this condition that only those can be resonating structures which have either exactly same energy or which are having nearly same energy. If energy difference is very much high, then they are not resonating structures of each other. Then they cannot be separated by double bonded arrow. I hope this is clear. After that, point number next is this one, that all the resonating structures must have same position or same arrangement of atom. Have a look. Have a look. If we talk about this hydrogen is attached to carbon. After that, it is attached to oxygen. That means what has happened during this? Position of hydrogen, position of atom has been changed. So they can never be what we call separated by means of double bonded arrow. They can never be resonating structures. But these two can be resonating structures because rule number 1 as well as this rule number 2 is fulfilled. Because there is no change in position of atom. There is no change in arrangement of atom. Hence, they can be what we call resonating structures. After that, my dear lovely students, that all the resonating structures must have same number of paired and unpaired electrons, but they only differ in the way of distribution of electrons. Have a look. How many what we call electron pairs are present in this? Have a look. This is one pair. This is second pair. This is third pair. We know this bond is made up of electron pairs. So 4 pair. This is 5th pair. This is 6th pair. This is 7th pair. And this is 8th pair. 8 pair of electrons are there and one non-bonding, one unpaired electron is there. So here, 1 pair, second pair, this bond is 3rd pair, this bond is 4th pair, this bond is 5th pair, 6th pair, 7th pair, 8th pair. That means both are having 8 pair of electrons. Number of paired electrons are same. What about number of unpaired electrons? They are also same. But they differ in the way of distribution of electrons. Have a look. This oxygen is having more electron density as compared to this oxygen. Similarly, this oxygen is having lesser electron density as compared to this oxygen. So they differ only in the way of distribution of electrons. Otherwise, they are having same number of paired and unpaired electrons. So all those rules, rule number 1, rule number 2, rule number 3, all are, fulfilled over here. Hence, these are resonating structures. After that, have a look. All the atoms which take part in resonance must be planar. Why? For resonance, why they should be planar? Because we know resonance means partial overlapping, and overlapping can take place only effectively if they are parallel with respect to each other. They are within the same plane with respect to each other. Now have a look. This nitrogen containing lone pair of electron in a p orbital, let's suppose this is the p orbital and this is the p orbital of carbon. Both are parallel and within the same plane. They will overlap and resonance. We can simply say these two are resonating structures. But here, this and this was parallel, but once this CH3 group is attached, they are attached, CH3 group and this NCH3 group, they are present at two adjacent positions. These are bulky groups. When two bulky groups are present at adjacent positions, when they are closer together towards each other, when they are closer, what will happen? Electron cloud of one bulky group and electron cloud of another bulky group, they will repel. They will repel in space. This is known as steric repulsion. So because of steric repulsion, what will happen? This whole group, because of steric repulsion, changes its plane. That means if it is present in this plane, first like this, now because of repulsion, it goes in another plane. When it goes in another plane, now this and this, they will not overlap effectively now. Or if they are perpendicular, they will not overlap at all. In nutshell, here resonance will be decreased. There will be decrease in resonance. There will be no overlapping over here because this is present in one plane, this is present in another plane, but all those atoms which take part in resonance should be present in within the same plane. Now, because of repulsion, they are present in different plane, hence there will be no resonance. If there is no resonance, these two are not resonating structures of each other. So can we say here resonance has been decreased, or this is inhibition of resonance because of steric repulsion? That's why this phenomenon is known as SER. SER means steric inhibition of resonance. That means inhibition of resonance has been taken place because of steric repulsion. I hope this is clear. These two were, present within the same plane, and within the same plane they overlap, but they are not present within the same plane because of repulsion. Hence they will not overlap. There will be no resonance at all. After that, all the atoms which take part in resonance must have a maximum of 8 electrons, but if those atoms belong to second period, or it must have 18 electrons if they belong to third period. Generally, elements given are either belonging to second period or those elements belong to third period. Have a look. We cannot say it will form a pi bond over here. Why? Because if resonance takes place like this, then this nitrogen, which is a second period element, and second period element can have maximum of 8 electrons in its valence shell, you know that. But here this nitrogen contains 5 bonds, means each bond is having 2 electrons. That means this nitrogen contains 10 electrons, but nitrogen can never have 10 electrons. Pentavalent nitrogen is not possible. If it is not possible, it will not be formed. If it will not be formed, then these two are not resonating structures of each other. But beta, this P belongs to third period. So here P contains 10 electrons, but third period element can have a maximum of 18 electrons. So 10 electrons are present. So 10 electrons are possible. Hence these two are resonating structures. But what about this? Have a look. Now, by doing so, rule number 1, rule number 2, rule number 3, rule number 4, rule number 5, all are fulfilled. Hence these two are also resonating structures, because here this is second period element. All these are having 8 electrons. No atom is having more than 8 electrons except hydrogen. Hydrogen is always having duplet completed. So apart from hydrogen, we are talking about of carbon and nitrogen. These are having maximum of 8 electrons, not more than 8 electrons. Hence this is possible. But this is not possible, as second period element nitrogen is having more than 8 electrons over here. Is this clear till now? Let me know quickly so that we will move ahead. Let me know quickly so that we will take another very important question, that is stability of resonating structures. Tell me, my dear lovely students, is this clear? Show some Josh quickly. Show some Josh. Yes, Pramod is very happy, I think so, because green hearts are there. Come on, there should be green hearts. Come on, everyone. That is great. Everyone is saying clear. Now, stability of resonating structure. You have to follow this order. First of all, if question is from stability of resonating structure, how will you answer? Number 1, first rule is that neutral resonating structure, this one is more stable than charged resonating structure. First you have to check this one. Have a look. There is example. This is neutral, this is charged. Which one is more stable? Neutral is more stable than charged. Why? Because more charge, more reactivity, lesser stability. So neutral is more stable than this. That's why 1 greater than 2. What about second rule? Second rule says stability of resonating structure is directly proportional to number of chemical bonds, but you can check pi bonds. This is what we call a trick. Check pi bonds only. Now have a look. This is having 2 pi bonds. This is having only 1 pi bond. More pi bond, more stability. Why? Because more the bonds, more will be the force of attraction. More the force of attraction, more will be the stability. So it will be once again 1 greater than 2. Now third one is this one. A resonating structure in which all the atoms have complete octet except, I mean to say, hydrogen is considered more stable as compared to that resonating structure in which all the atoms does not have complete octet. All the atoms do not have complete octet. Have a look. Here, this carbon is not having complete octet, but here, all these atoms except hydrogen have complete octet. So this is more stable as compared to this. So 2 greater than 1. I hope this is clear. I hope this is clear. Remember these. You have to first check this, then this, then this. After that, you have to check fourth one. What is fourth one? Have a look. If you are having more than, say, one resonating structure, and if all these resonating structures have some charge, but answer is, say, you cannot answer this question by rule 1, rule 2, rule 3. Then you have to use rule 4. What is rule 4? If all the resonating structures have some charge, then that resonating structure is considered more stable in which negative charge is present on more electronegative element. That means Men, and that which contains positive charge on less electronegative element. That means Len is more stable. Have a look. Rule 1, rule 2, rule 3, rule 1, rule 2, rule 3 cannot answer the question. That's why we will use rule 4. Now what is rule 4? Positive charge is present on carbon and oxygen. Oxygen and carbon. Here positive charge is present on oxygen and carbon. That means among carbon and oxygen, you have to check. Among carbon and oxygen, they belong to same period. We know on moving from left to right, from carbon to oxygen, electronegativity increases. So first of all, you have to find out which one is Men, which one is more electronegative element. This is Men. Which one is Len, which is less electronegative element. This one is Len, less electronegative element. Now listen, positive charge on Len is more stable and negative charge on Men is more stable. So now tell me, positive charge on carbon, is more stable and negative charge on oxygen is more stable. That means positive charge on carbon and oxygen, negative charge on oxygen is more stable. That is why first is more stable as compared to second. So first is more stable as compared to second. After that, next is resonating structure in which there is more what we call charge separation. Listen, resonating structure in which there is more charge separation, but charge separation, that means distance between the two charges, but those charges should be unlike. One should be positive, another should be negative. If there is more distance between positive and negative, force of attraction will be less. That means resonating structure will be less stable. And if charge separation, that means distance between positive and negative is less, that at that time is more stable. Have a look. This is positive and this is negative. Unlike charges are separated but distance is less. Unlike charges are separated but distance is more. When charge separation between positive and negative is less, attraction will be more, stability will be more. That means 1 is more stable than 2. I hope this is clear. After that, rule number 6. Whenever you are having resonating structure in which like charges are present on adjacent species. Adjacent positions, like charges are present on adjacent positions. Positive, negative, lone pair, negative. Then we know like charges are present on adjacent position. That means repulsion will be more. Repulsion more, that means energy more. Energy more, matlab least stable. So such resonating structures are least stable if positive, negative, lone pair, negative, lone pair are present at adjacent positions. Now, let's use these rules and let's answer these questions. Can anyone answer me first question and second question quickly in the chats? Quick. Let me know the answer of first question and second question in the chats. Quick. Let me answer. Let me know the answer. Let me know the answer in the chats. Write down the answer in the chats. I am waiting. Let me know the answer in the chats. Quick. Sorry. Okay. Okay, 132. First one. Now have a look. Have a look. What do you have to check first? Rule number 1. What was rule number 1? Neutral is more stable than charged, but there is no neutral. That means rule number 1 cannot answer the question. Number 2. What was second rule? More number of bonds, more number of pi bonds. There are 2 pi bonds, there are 2 pi bonds. This is having only 1 pi bond. That means rule 2 says that this second will be at last. After that, rule 3. We have to use rule 3 between 1 and 3 because 1 and 3 cannot be separated by rule 2. Both are having 2 pi bonds. Now, what was rule 3? Resonating structure in which all the atoms have complete octet, and resonating structure in which all the atoms does not have complete octet, but this is having complete octet, this is having complete octet. That means rule 3 cannot answer. Rule 4, charge rule. This is having positive charge on nitrogen, positive charge on nitrogen, same stability as per positive charge is concerned. But what about negative charge? Negative charge is present on nitrogen, negative charge is present on carbon. Negative charge is more stable if it is present on more electronegative element. Which one is more electronegative, nitrogen or carbon? Nitrogen. So what will be the answer? Answer will be 1, 3, 2. That means those students who have given me the answer 1, 3, 2, they are exactly correct. They are exactly correct. What about this question? What about question number 2? First of all, neutral one. Which one is neutral? 1. After that, among these 3, which is having more number of pi bonds? It is, I mean, say 2. After that, these 2, rule number 3. This is not having complete octet, this is not having complete octet. That means rule 3 cannot answer this. 1, 2, 3 cannot answer, so use rule 4. What was rule 4? Negative charge present on oxygen is more stable as compared to carbon. Similarly, positive charge present on carbon is more stable as compared to oxygen. So I will write down 1, 2, 4, 3. So this will be the answer of this question. I hope this is clear to each and every one. I hope this is clear to each and everyone. Yes, everyone is giving me the right answer. 1, 2, 4, 3 is the right answer. 1, 2, 4, 3 is the right answer. Great. After that, my dear lovely students, stability of any species because of resonance is directly proportional to extent of resonance. So those species in which, say for example, you are having 2, 3 species and all are showing resonance, then which one will become more stable? That will become more stable according to resonance, which is having more resonance. That means extent of resonance should be more. So this is the formula. This is the formula that stability of any species because of resonance is directly proportional to extent of resonance. Now the question is, extent of resonance depends on how? Depends on what? Extent of resonance depends on equivalent resonance and non-equivalent resonance, but it is directly proportional to equivalent resonance and it is inversely proportional to non-equivalent resonance. Now the question is, what is equivalent resonance? Have a look. Have a look. Question is, among these, which one is having more resonance? That means which one is having more stability according to resonance. So whenever you are having structures like this, in which you know resonance is possible, so you first of all draw their resonating structures. So its resonating structure is like this. Its resonating structure is like this. Now have a look. Both these resonating structures are equally stable. So remember, resonating structures contribute towards hybrid, resonating structures contribute towards resonance, resonating structures contribute towards actual structure, that means resonance hybrid or resonance, but if they are equally stable, they will contribute equally. That means contribution of any resonating structure is directly proportional to basically stability of the resonating structure. These both are equally stable, hence their contribution towards resonance hybrid will be equal. That is why the hybrid formed over here, the contribution towards this hybrid is equal of both these resonating structures. Hence the resonance present in this is known as equivalent resonance, because resonance contribution has these, this and this both have given equal contribution towards resonance, hence this is known as equivalent resonance. But what about this one? Have a look. This is one of the resonating structures. Its another resonating structure is like this. Its another resonating structure is like this. Have a look. But this is neutral, this is charged, this is more stable, so its contribution will be more. It is less stable as compared to this, that means its contribution will be slightly less. So hybrid is this. So the information of resonance or information towards this hybrid is given by both, but they will not give I mean to say equal information towards hybrid. They will not give equal information as per what we call resonance is concerned. They will not give equal information, means here resonance is not equivalent. Here resonance is equivalent. So what is meant by equivalent resonance? If contribution towards resonance from resonating structures are equal, at that time we call that resonance as equivalent resonance. But if contribution of resonating structures towards resonance hybrid or towards resonance is not equal, we will simply say that as non-equivalent resonance. And remember, this is having non-equivalent resonance, this is having equivalent resonance. So here resonance, extent of resonance will be more as compared to this. So this is given, you have to think of this. This is given, you have to think of this. That's why you will simply say this is more stable as compared to this one. I hope this is clear. Why first one is more stable than second? But according to resonance, not in, say general. According to resonance, this is more stable as compared to this, because here it's equivalent resonance means extent of resonance more, non-equivalent resonance means extent of resonance is less. So more resonance, more stability. Similarly, extent of resonance is directly proportional to linear conjugation and it's inversely proportional to cross conjugation. Have a look. Here you can say this delocalization is in one, say direction. Here you can say it can be either in this direction or in this direction. So whenever pi electron movement is in opposite direction in say presence of magnetic field, then you can call it as cross conjugation. And in presence of magnetic field, if pi electrons direction will be in pi electron movement will be in same direction in presence of magnetic field, we call that as linear conjugation. And if pi electron movement is in opposite direction in presence of magnetic field, we call that as what we call cross conjugation. So this is having cross conjugation, this is having what we call linear conjugation. So in first case it is one which is having more stability or which is having more resonance as compared to second. Similarly in second question it is one which is having more resonance or more stability as compared to second, because this is having linear conjugation and this is having cross conjugation. After that next is extent of resonance also depends on electronegativity of a species which undergoes resonance, which takes part in resonance. Now have a look. Here it is the lone pair present on nitrogen which takes part in resonance. This is the lone pair of oxygen which takes part in, what we call resonance. But we know nitrogen and oxygen belong to the same period, and we know electronegativity from nitrogen to oxygen increases as oxygen is more electronegative, so its electrons are more tightly bound, and nitrogen is less electronegative as compared to oxygen. So as compared to oxygen, these electrons are loosely bound. So more loosely bound electrons, more will be the resonance. So in these two cases, we can simply say one is having more resonance as compared to two. One is having more resonance as compared to two. Next is extent of resonance is directly proportional to conjugate positions. Have a look. This is one conjugate position, this is another. Alternate positions of conjugate compound is conjugated position. Here, this and this, they are the alternate position. This is also alternate position, but there is no conjugation. There is no p orbital available now. P orbitals are available only from this position to this position. So the alternate position of this part is known as conjugate position. So this is not the conjugate position. So here only two conjugate positions are present. Here three conjugate positions are present. Hence, the resonance in one will be more as compared to second. And lastly, this one. So more stronger the overlapping, more will be the resonance. Now have a look. Here it is 2p orbital of this nitrogen which overlaps with 2p orbital of carbon. That means here overlap is 2p. It is 2p overlap, or 2p pi overlap. Here it is 3p. This is 3p because phosphorus is third period element. This lone pair is present in its 3p, and here it is carbon which is 2p. So it is 3p 2p overlap basically taking place. So this is more effective overlap as compared to this. So we will simply say one is having more resonance as compared to two. So this will be the order of resonance, extent of resonance, or strength of overlapping, or simply what we call stability due to resonance. After that, extent of resonance is directly proportional to energy of delocalized electrons. Let me tell you, pi electrons are generally delocalized electrons. But what are pi electrons? Pi electrons are either those electrons which are present in double bond, or pi bond of a triple bond. Say for example, it can be a double bond, it can be a triple bond, or it can be any electron which is in the form of a lone pair or negative charge but present in conjugated orbital. Whenever lone pair or negative charge is present in a conjugated orbital, we can also call those electrons as pi electrons. So energy among these is negative, after that lone pair, after that double bond, after that triple bond. This is the energy order. This is the energy order. Now this is the energy order. Now look towards this. So more energy. Here it is lone pair which takes part in resonance. Here it is negative charge which takes part in resonance. So among this lone pair and negative charge, whose energy is more? It's negative charge. That means its extent of resonance is more as compared to 1. So I will say extent of resonance in case of 2 is more as compared to 1. And this is more stable as compared to this. When I say this is more stable, that means I'm talking about its resonance hybrid. This resonance hybrid is actually more stable than the resonance hybrid of this according to resonance. After that we will be having another definition, that is resonance effect. What is meant by resonance effect? Listen carefully. Any substituent, any atom, any group which is capable of donating pi electrons or withdrawing pi electrons but due to resonance is known as what we call resonance effect or mesomeric effect. But listen carefully. So if this group donates electron towards conjugated system, this group withdraws electrons away from conjugated system. So any group, any substituent which donates electrons, but which electrons? Pi electrons, or which withdraws pi electrons because of resonance, at that time we call that effect as resonance effect or mesomeric effect. Remember, for this, what we call resonance effect to operate, resonance is basically the mechanism. That means without resonance, there will be no resonance effect. And remember, resonance effect is of two types. One, that effect with the help of which any atom or any group donates pi electrons towards conjugated system and increases electron density of conjugated system. Another, any group which withdraws pi electrons away from conjugated system and decreases electron density of what we call conjugated system. These are of two types. So which donates pi electron because of resonance and increases electron density of, I mean to say, what we call conjugated system, that group is known as plus R group or plus M group, because plus R means electron donating resonance effect or plus M means electron donating mesomeric effect. Similarly, that group which withdraws pi electrons away from conjugated system because of resonance shows minus R or minus M effect. That means resonance effect is basically of two types. One is plus R, that means electron donating resonance effect, also known as electron donating mesomeric effect. Another is minus R, that means electron withdrawing resonance effect. So what is plus R? It is simply that resonance with the help of which any atom or any group donates pi electrons towards conjugated system, but because of resonance and increases electron density of conjugated system. But my dear lovely students, remember, if benzene is there, if such group is attached to benzene, it will donate pi electron towards benzene and increases electron density of benzene, generally at ortho and para position. That means such groups are ortho para directing with respect to electrophile, because once they increase electron density at ortho and para, so electrophile will go to ortho as well as para position at that time. And such groups, ortho para directing groups, increase electron density at ortho and para or increase electron density of ring in general, and hence such groups are activating groups except halogens. Why? Because halogens donate pi electrons because of resonance. That means they are orthopara directing because of resonance, but they withdraw electrons away from benzene ring, away from aromatic ring because of inductive effect. And we know halogens are having stronger inductive effect as compared to resonance. That is why, remember this point, this is very important point, that all orthopara directing groups are all orthopara directing groups are activating groups except halogens. Halogens are orthopara directing, but they are deactivating because in general they decrease the electron density of the ring. So these are the points which I have already told you that. Now after that, there are few groups which show plus R, and this is what we call those groups, and this series is known as plus R series. For this you can use this trick as well. You can use this trick as well. Now, there is one more trick. How can you find out whether the, atom or group shows plus R or not? Simply, you have to check this conjugated system, whether this is benzene ring or carbon-carbon double bond. If an atom or a group attached to that benzene or carbon-carbon double bond contains lone pair or negative charge, or that's having non-polar pi bond, at that time, if they show resonance, because for resonance there should be some conditions, those conditions should be fulfilled. If it shows resonance, then such groups, such atoms show plus R effect. So please remember this as well. After that, another is minus R. Minus R is exactly opposite to that of plus R. That means what will minus R groups do? They will simply withdraw electrons, but which electrons? Pi electrons, because of resonance, away from conjugated system, and they simply decrease electron density. And if say such groups are attached to benzene ring, they will withdraw electrons away from benzene ring from ortho and para position and decreases electron density at ortho and para. That means if they decrease electron density at ortho and para, meta becomes, by default electron rich, so electrophile goes to meta position. So such groups are meta directing groups with respect to electrophiles, and such groups are always what we call deactivating groups. So there are minus R series as well, but there is a trick with the help of which you can find out why such groups are, minus R groups. Have a look. If such atom, this is the atom which is attached to conjugated system, if such atom is having a vacant orbital, if such atom is having a vacant orbital, or such atom is having a polar pi bond and also shows resonance, then such atoms or groups simply show minus R effect. I hope this is clear to each and every one. Now, after that, there is application of resonance. Applications. Application number one is carbocation stability, Carbanion stability, and carbon free radical stability. All these can be solved, all these questions can be solved with the help of only one formula, that is extent of resonance. What is meant by that? Have a look. Suppose you are having these three carbocations. Here, resonance takes place from this side as well as from this side. More what we call number of conjugate positions, so extent of resonance will be more as compared to this. This is having more resonance as compared to this. So what will be the stability order? More the extent of resonance, more will be the stability of, carbocation. So 1, 2, 3 will be the answer. Similarly, my dear lovely students, here it will be once again 1, 2 and 3. Why? Because in 1, resonance is more as compared to 2, as compared to 3. You have to answer the question on the basis of resonance. That's why this is known as application of resonance. Once again, it will be 1, 2 and 3. I hope this is clear to each and every one. Let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? Quick. Let me know in the chats quickly. Let me know in the chats quickly, am I clear till now? Yes, sir. Clear. Great. Now, after that, my dear lovely students, there is another application, and that application is bond length. Listen carefully. First of all, you should remember this, but try to understand what is this. First of all, single bonds. Bond length of single bond is more than partial double bond, then double bond, then triple bond. But partial double bond can be because of resonance. And if partial double bond is because of resonance, but that partial double bond is basically, seen only and only if resonance hybrid is there. But if resonating structures are there, then this partial double bond seems to be either single bond or double bond. So what is this single bond and what is this single bond? This is that single bond which seems to be single bond, but because of resonance, that is actually partial double bond. This single bond is actual single bond. This is that double bond which seems to be double bond, but when resonance occurs, basically because of resonance, that is not the actual double bond, that is actually partial double bond, and this double bond is actual double bond. After that, there is the formula. This is the formula. Formula is, if you are having a single bond which seems to be single bond, but in actual practice it is a partial double bond, then use this formula. Use this formula for bond length. And if it seems to be a double bond, but in actual sense it's a partial double bond, at that time use this formula. Use this formula for bond length. Now, what is this? Come, have a look. Have a look. Now, question number 1 is compare bond lengths. You have to compare bond lengths. You have to compare bond lengths. Now, have a look. This is what we call X. This bond is what we call Y. This bond is Z, and this bond is A. Now, this bond is a normal single bond. This bond is a single bond, normal single bond. This bond is a normal double bond. Now, what about this? We know here it will be resonance. Once resonance takes place, that means this single bond is not single bond, it is actually partial double bond. This is partial double bond, but which seems to be a single bond. It's a partial double bond, seems to be a single bond. What about this? It's once again a partial double bond because of resonance, but it seems to be a single bond. Now tell me, first of all, which one will I write first? First, single bond. Single bond is this one, so I will write down 1. But 1 bond is X, so I will write down X. After that, can I write down this double bond at the end? Because single bond, double bond and partial double bonds are there. Single bond should be first, then partial double bond, and at the end that will be double bond. So at the end, double bond is Y. So at the end it should be Y. After that, it should be Z or A. But it is that partial double bond which seems to be single bond. That means formula is this one. So have a look. If we talk about conjugate positions, this is one conjugate position, this is another conjugate position. Two conjugate positions are there. Here, this is 1, this is 2, this is 3. Now tell me, in these two cases, more number of conjugate positions is present in this one. More conjugate position, more resonance. More resonance, bond length will be less. That means its bond length will be less, its bond length will be more. So it is Z, then it is A, and then it is Y. So answer should be like this. So first it is normal single bond, then at the end it is what we call double bond, and in between these two are partial double bonds. But among partial double bonds, check whether it seems to be a single bond or whether it seems to be a double bond. It seems to be a single bond. When it seems to be a single bond, use this one. If it seems to be a double bond, use this one. Now, answer is this one. Is this clear? Let me know quickly, is this clear? Let me know quickly, is this clear? Quick. Tell me, is this clear? God bless you. God bless you. Come on, my dear lovely students, tell me. So this is clear to you. Now have a look. Have a look. Look towards this. This bond is X, this bond is Y, and this bond is Z. After that, this bond is A. But this bond is double bond, normal double bond. This bond is normal single bond. That means here I will write down this is a double bond. This bond is a normal single bond. This bond is partial double bond, but it seems to be a double bond. Have a look. So it's a partial double bond, but seems to be a double bond. Similarly, this is the double bond, but this is the partial double bond, this is the partial double bond, but it seems to be a double bond. First, we will write down double bond. First of all, we will write down this single bond. So single bond is A, so I will write down A. At the end, I will write down this is double bond is X, so at the end, I will write down X. Now, among Y and Z, as they are the partial double bonds, but seems to be double bond, I will use this formula. Now have a look. Have a look. This is the conjugate position number 1. This is 2. This is 1. This is 2. And this is 3. So more conjugate position, more resonance. More resonance, then more bond length. That means I will write down Z. And after that, I will write down Y. Here, more resonance, more will be the double bond. Why? Because double bond, partial double bond seems to be double bond. Here, bond length is inversely resonance. Why? Because here partial double bond seems to be single bond, and in that case it's inverse relation. And if partial double bond seems to be double bond, at that case, at that time, this formula is applicable. That means bond length is directly proportional to extent of resonance. After that, my dear lovely students, relative acidic strength. Now you have to compare the acidic strength of these. How to compare acidic strength? Simply lose H positive and form its conjugate base. Form its conjugate base. Have a look. This is the conjugate base. This is the conjugate base. What about this? This is the conjugate base of this. What about this? This is the conjugate base. Now, when you draw all the resonating structures and after that you form resonance hybrid. Let me form a resonance hybrid directly. So this will become the resonance hybrid. Listen carefully. Listen carefully. This is the resonance hybrid, or let me show the resonating structures as well. Let me draw the resonating structures as well. This is its resonating structure number second. Resonating structure number second is this one. Its resonating structure third will be this one. Have a look. All these are equally stable. If all are equally stable, that means they are hybrid. They are hybrid. Like this. Contribution towards hybrid. Contribution towards hybrid. Have a look. Contribution towards hybrid. Contribution towards hybrid. From all these resonating structures will be equal. That means this is having equivalent resonance. Similarly, if you draw the resonating structure of this, its resonating structure will be this. Both are equally stable. What does that mean? That clearly indicates the contribution from these towards this hybrid is once again equal. Is once again equal. So that means once again equivalent resonance is there. But here, my dear lovely students, when you draw the resonating structure, in first resonating structure, negative charge was present on oxygen. In second, it is present on carbon. Now, they are not equally stable. They are not equally stable. When resonating structures are not equally stable, when resonating structures are not equally stable, their contribution towards hybrid will not be equal. Their contribution towards hybrid will not be equal, my dear lovely students. So, their contribution towards what we call hybrid will not be equal. That means here resonance is not equivalent resonance. Here resonance is not equivalent. Resonance here is not equivalent. Now tell me, in third case resonance is not equivalent, but in these two cases resonance is equivalent. Now tell me, among these, which one is least stable then? This is least stable. If this is least stable, its acid will be weaker acid. So I will write down at the end 3. Now among these two, both are having equivalent resonance. Now, how many conjugate positions are there? 1, 2, 3. Here only 2. So more conjugate position, more resonance, more stable. That means first is more stable. If first is more stable than second, that means first is stronger acid as compared to second. So sulfonic acid first, then it is simply what we call carboxylic acid, and finally it is phenol. I hope this is clear. This is acidic strength order. After that, basic character of amines. My dear lovely students, have a look. This electron present on nitrogen takes part in resonance, but it takes part in resonance with respect to one ring. It takes part in resonance with respect to 2 rings. It takes part in resonance with respect to 3 rings. That means, can I say in third, resonance will be more? I mean, say this lone pair will take part more in resonance. This will be more delocalized. If this is more delocalized, its electron density will be less available because it is used in resonance. Now, its electron density will be less available. It is less, used in resonance, hence its electron density will be more available for donation or for protonation. So, remember, we will simply, for such type of, species, we will say more basicity, lesser will be the resonance, or more resonance, lesser will be the basicity. So, basicity or basic strength of such species whose lone pair or whose electron density takes part in resonance. So that species which takes part in resonance more is having lesser basicity. So the basic order will be here 1, 2 and 3. Remember this. Sorry. Now, this is the answer. I hope this is clear. After that, there are few compounds known as aromatic, few compounds non-aromatic, few compounds anti-aromatic. But remember, aromatic compounds are always more stable than non-aromatic compounds, and non-aromatic compounds are more stable than anti-aromatic compounds, or you can say anti-aromatic compounds are least stable or unstable species. Now, how to check? There are conditions. Simply remember those. Condition for aromatic compound is that it should be cyclic, planar, complete delocalization, or with the help of these 3 points you can simply remember this point, that is complete cyclic conjugation should be there. Point number 1. Similarly, complete cyclic conjugation should be there in anti-aromatic compounds as well. That means if these 3 points or this point is present, that means compound can be aromatic, compound can be anti-aromatic. But after that, if compound is having these 3 points, that means this point, in addition to that, if it is having 4n plus 2 pi electrons, where n starts from 0 to infinity, that means if compound contains 2 pi electrons, 6 pi electrons, 10 pi electrons, 14 pi electrons, 18 pi electrons, you have to add 4 electrons, so on and so forth. If complete cyclic conjugation as well as such number of pi electrons are present, then we can call that compound as aromatic compound. And if compound is having complete cyclic conjugation and in addition to that, it's having 4n pi electrons, where n is 1 to infinity, that means n, if n is 1, that means if it's having 4 pi electrons, 8 pi electrons, 12, 16, 4, 4, 4, you have to add 4, 4. Now, then such compounds are known as anti-aromatic species. But if all these 4 points or all these 4 points are not fulfilled, that means compound is neither aromatic at that time nor anti-aromatic at that time, then compound can be what we call non-aromatic. For example, this should be cyclic, this should be cyclic. That means open structures, that means acyclic compounds, they can never be aromatic, they can never be anti-aromatic. They are non-aromatic species. Now the question is, what are these pi electrons? Pi electrons are, remember, pi electrons are those electrons here which are present in what we call conjugated orbitals. Whether those are lone pair, whether those electrons are pi electrons, pi bonded electrons, I mean say pi electrons of a double bond or a triple bond, or those electrons are what we call negative charge electrons, but present in conjugated orbital. At that time, if such electrons are present in conjugated orbital, then one lone pair is considered 2 pi electron, one pi bond is considered 2 pi electron, one negative charge is considered 2 pi electrons. But if odd electron, if only one electron, say for example, is present in a conjugated orbital, you can count that as one electron as well. Now, have a look. Have a look. Now, look towards this. My dear lovely students, we know this is sp2 hybridized, and whenever hybridization is sp2 and sp, at that time p orbitals are available as per carbon is concerned. So here it is the p orbital. Here it is the p orbital. But this is sp3. So there is no p orbital. If there is no p orbital, can I say in this ring there is no conjugation? Because for conjugation there must be at least 3 p orbitals or 3 d orbitals at 3 adjacent positions parallel and with respect to the same plane. So there is no complete cyclic conjugation. That means, look towards this, complete cyclic conjugation is absent. Complete cyclic conjugation is absent. That means it is neither aromatic nor anti-aromatic. So we can simply say, my dear lovely students, this is non-aromatic because of absence of complete cyclic conjugation. Now look towards this one. Now look towards this one. This is P, this is P, this is P, and this is P. Because they have overlapped, sideways overlapping, because of sideways overlapping, there is, I mean, say, formation of pi bond. Or I can show like this. There is P, P, which have been overlapped. Similarly, sideways overlap of P and P orbitals. So in nutshell, how many P orbitals are present? 4. But we need at least 3 for conjugation. That means conjugation is there. But this conjugation is complete conjugation as per this ring is concerned. So this is complete cyclic conjugation. Now tell me, in these conjugated orbitals, how many pi electrons are there? This is one pi bond, this is another pi bond, that means 4 pi electrons are there. So complete cyclic conjugation is there with 4 pi electrons. That means this is anti-aromatic. This is anti-aromatic. Have a look, have a look. Complete cyclic conjugation with 4 pi electrons, that means it is anti-aromatic. I hope this is clear. Now, my dear lovely students, have a look. If we talk about this, this is sp2 hybrid orbital, which means p orbital is there, p orbital is there. This is also sp2, which means p orbital is there. That means here conjugation is present, and that too within the complete ring. So complete conjugation, complete cyclic conjugation is present. Now, my dear lovely students, if complete cyclic conjugation is there, how many electrons are present in this, this and this? This is not having any electron, but this and this is having a pi bond, that means 2 pi electron. So can I say this is complete cyclic conjugation and this is having 2 pi electrons. So I can simply say this is aromatic with 2 pi electrons. Because whenever you are having complete cyclic conjugation and 2 pi electron, it is simply aromatic. And these complete 4 points are known as Huckel's rule. In nutshell, any species which obeys Huckel's rule is known as aromatic species. After that, have a look. This is sp2, that means p orbital. sp2, that means p orbital. This is also sp2, means p orbital. Now look, complete cyclic conjugation is there, but this p and this p forms a pi bond. That means in these two conjugated orbitals, there is a pi bond, means 2 pi electrons. And in this conjugated orbital, there is negative charge. Negative charge, one negative charge in conjugated orbital is equivalent to 2 pi electrons. Now, in total, can I say these 2 pi electrons of pi bond and these 2 pi electrons of this negative charge makes it 4 pi electrons. That means complete cyclic conjugation with 4 pi electron means this is anti-aromatic, my dear lovely students. Now, if your species like this or this, have a look. What we have to do at that time. Remember, whenever you are having a circle like this inside the ring, that clearly means this is having complete cyclic conjugation. That means these 3 points are already present at that time. Complete cyclic conjugation. When such structure is present, that means 3 points are already present. 3 points are already present. That means we have to check only pi electrons at that time. Here we have to check all those points, but here we have to check only pi electrons. Now listen carefully. Can I say this is 4-membered ring? So I will write down 4. This is 4-membered ring, so I will write down 4. But in this 4-membered ring, there are 2 positive charges, which means 2 electrons have been lost. So I will simply subtract 2 because 2 electrons have been lost from this 4. So answer is 2. This answer gives us information about pi electron. Now tell me, complete cyclic conjugation with 2 pi electron. Can I say this is aromatic? This is aromatic. What about this? This is 4, then 2 negative charges. Negative means gain of electron, but 2 negative means plus 2. Gain of 2 electrons. Answer is 6. So how many electrons are there as per pi electrons are concerned? So 6 pi electrons are present. So this is complete cyclic conjugation with 6 pi electron. Once again, this is aromatic. Now what about this, beta? This is p orbital overlap, p orbital overlap. That means here conjugation is present, because conjugation means at least 3 orbitals, 3 p orbitals parallel and within the same plane. But there are 4, so conjugation is present. But conjugation is not present completely, because this carbon is not having, this sp3 carbon is not having any p orbital. Because of this carbon is not having conjugated orbital, so there is not completely cyclic conjugation. Conjugation is there, but complete cyclic conjugation is absent. Complete cyclic conjugation is absent, hence this is non-aromatic. This is non-aromatic. I hope this is clear. Okay, whenever you are having a double bond, but outside the ring, endocyclic double bond, at that time, what you will do? Draw its resonating structure simply like this. Draw its resonating structure simply like this. Because this is more electronegative, give, say pi electron towards that. Go, say you have to move pi electron towards more electronegative element. Okay, now, so this is our resonating structure. Now look towards this resonating structure. Look towards this resonating structure. This is p orbital, this is p orbital, this is p orbital, this is p orbital. They have overlapped. This is also p orbital, and that p orbital is empty. That means complete cyclic conjugation is there. But this p orbital is empty. These 2 p orbitals are having pi bond, means 2 pi electron. These 2 p orbitals are having pi bond, means 2 pi electron. So 2 and 2, 4 pi electrons are there within the ring. Hence this is anti-aromatic, my dear lovely students. This is anti-aromatic. What about this? What about this one? Have a look. P orbital is there, overlapping. P orbital is there, overlapping. This is also p. But this p is having negative charge now. Now listen carefully. Complete cyclic conjugation is there. These 2 p orbitals are having pi bond, means 2 pi electron. These are having pi bond, means 2 pi electron. This is having negative charge, means 2 pi electron. So this is aromatic with 6 pi electrons. This is aromatic with 6 pi electrons. What about this? What about this? Listen carefully. Listen carefully. This is what we call a p orbital, and p orbital, they have overlapped. Similarly, this is having p orbital and p orbital, this overlap. This is another p orbital and this is another p orbital. That means one p orbital is in conjugation with these, but this is not within the same plane, so this is not in conjugation. That p orbital which is not in conjugation, electron present in that is not, is not counted. So this we cannot count these electrons, as these electrons are not present in conjugated orbital. So we will count these electrons. So these are 2 electrons, pi bond, 2 electrons, pi bond, 2 electrons. That means this is having 6 pi electrons. So let me write down, this is aromatic with 6 pi electrons. If this is clear, let me erase these, and let me write down answers only. If this is clear till now. If this is clear till now, let me show you like this. Let me show you like this. Let me show you like this now. Okay. So this is anti-aromatic. I hope this is clear till now. Now after that, once again, these are having p orbitals because overlapping has been taking place. So p, and p. So all these orbitals are present within the same plane, and this is complete cyclic conjugation. After this complete cyclic conjugation, how many pi electrons are there? 6. So I will say 6 pi electrons. So this is aromatic with 6 pi electrons. This is known as benzene. Listen carefully, listen carefully, listen carefully. These are basically this and this orbital, this and this orbital, they are within the same plane. Listen, they are within the same plane, but there is sp2 and sp2 orbital like this, which overlap and forms extra bond. These orbitals are not in conjugation with this. So this pi bond is not calculated. This pi bond is, pi bond, you cannot count this pi bond, as this pi bond is out of plane. This is not in conjugation with other pi bonds. So I will simply erase this one. Now tell me, how many pi electrons are there? Count this one, don't count this one. So 2, 2, 4, 2, 6. So once again, this is aromatic with 6 pi electrons. And result, remember, this is known as called cyclooctatetraene. Whenever you are having cyclooctatetraene, this is unstable basically like this. That's why it changes its shape to this one. It changes its shape to this one. This is known as tub-shaped structure. So it exists in basically tub-shaped structure. And remember, we know tub-shaped structure is a non-planar structure. As it is non-planar, means clearly indicates, that means it is neither this because it should be planar, nor this because it should be planar. If it is non-planar, hence remember cot, that means cyclooctatetraene is always non-aromatic. It's always non-aromatic. Similarly, here these pi electrons are, you cannot count these pi electrons, what we call lone pairs, because such electrons are present in an orbital which are not in conjugation with other electrons. So this is pyridine or pyridine. This pyridine is once again aromatic with 6 pi electrons. So this is aromatic with 6 pi electrons. I hope this is clear. I hope this is clear. Let me show you 2 more examples. Remember, if you are having aniline means if you are having a monocyclic structure in which there are more than one double bond but in conjugated form and contains even number of atoms. So completely cyclic, or we can simply say monocyclic completely conjugated, or completely conjugated monocyclic polyene containing even number of carbon atoms. When you number this like this, 1, 2, 3, 4, 5, 6, 7, 8, this is 9, this is 10. At 9 and 10 position, there are hydrogens which are very closer to each other, but they are not bonded, but they are very closer to each other. Because of that non-bonded interactions, or because of electron repulsion at 9 and 10 position, 9 and 10 goes out of plane. 9 and 10 goes out of plane. When 9 and 10 is in different plane with respect to 1, 2, 3, 4, 5, 6, 7, 8, that means there will be no conjugation like this. There will be no overlapping like this. That means complete conjugation will be broken at that time. There will be no complete cyclic delocalization, because 9 cannot overlap with 8 now. 5 cannot overlap with 10 now, because 9 is in different plane and 8 is in different plane. 10 is in different plane, 5 is in different plane because of these hydrogens. This is known as 10-aniline. So remember, 10-aniline is simply 10-aniline is simply non-aromatic because of this non-bonded hydrogen interactions taking place at 9 and 10 position, due to which carbon number 9 and carbon number 10 goes out of plane. They are not now in plane with respect to 1, 2, 3, 4, 5, 6, 7, 8. So they are non-aromatic. So 10-aniline is non-aromatic. Similarly, remember this one. This is known as benzoquinone. This is known as benzoquinone. Remember, this is parabenzoquinone or benzoquinone. Remember this. Benzoquinone is also non-aromatic because it is stable even at room temperature. You cannot say like this. Why? Have a look. You cannot say like this. You cannot say that it is having only 4 electrons within the ring, so this is anti-aromatic. Suppose we say this is anti-aromatic. What is meant by that? That means it is highly unstable, but it has been seen that it is stable even at room temperature. That's why it is not anti-aromatic. So remember this, that benzoquinone is simply what we call non-aromatic. So remember, benzoquinone is non-aromatic. So this was all about aromatic, non-aromatic and anti-aromatic species. After that, my dear lovely students, there is another thing, that is resonance energy. What is meant by resonance energy? Resonance energy simply means amount of energy which is decreased, not lost. Amount of energy which is decreased due to delocalization or due to resonance. Remember this. So amount of energy decreased due to delocalization or due to resonance is known as resonance energy, also known as delocalization energy, also known as resonance stabilization energy. And this is equal to, resonance energy is equal to resonance of energy of resonance hybrid minus energy of most stable canonical structure. Now listen carefully. Now resonance hybrid is basically that structure in which delocalization takes place, in which resonance takes place. When delocalization takes place, resonance takes place, energy is decreased. So its energy will be obviously less as compared to most stable resonating structure or most what we call stable canonical structure. So here, this will be always more stable because of delocalization. Why? Because during delocalization there is decrease in energy. Decrease in energy makes it less energetic. Less energetic means more stable. So this is more stable as compared to this, or this is less energetic as compared to this. If this is less energetic as compared to this, remember, its value will be always negative, because less energy minus more energy, value will be always negative. But that negative energy does not mean it is exothermic in nature. Now, that clearly means that how much energetic this is as compared to resonance hybrid, or how much stable resonance hybrid is as compared to more stable canonical structure. And remember, this gap between resonance hybrid and most stable canonical structure is known as resonance energy. Say for example, this gap is, say for example, this much in one compound, it is this much in second compound. So more this gap, more will be resonance energy. What is resonance energy? More resonance energy means more decrease in energy. More decrease in energy means that compound it will be least energetic. That means more stable. In nutshell, remember, stability of any species because of resonance is directly proportional to resonance energy. Remember, stability of any species because of resonance is directly proportional to resonance energy, because resonance energy is not energy, it is decrease in energy. More resonance energy means more decrease in energy. More decrease in energy means least energetic. Least energetic means more stable. I hope this is clear to each and every one. Now, after that, my dear lovely students, there is, another permanent effect, and that is hyperconjugation effect. Now, we will complete GOC within 10-20 minutes. After that, we will take break, and after break, we will start isomerism. So, be attentive what is meant by hyperconjugation. Hyperconjugation has different names, many names, but few of them I have written over here. For example, sigma delocalization, no bond resonance, Baker-Nathan effect, secondary resonance, extension of resonance. Now the question is, when we can say that this compound shows hyperconjugation? For that, simply remember, if you are having carbon-carbon triple bond, and to that carbon-carbon triple bond you are having alpha carbon, that means to that carbon directly attached carbon is known as alpha carbon. That means if that carbon is sp3 and it contains one hydrogen, at that time hyperconjugation is present. Or you can simply say, if you are having carbon which is sp2 and to that carbon directly attached carbon, that means alpha carbon, is sp3 which contains one hydrogen. But what should be this sp2? It can be either carbon-carbon double bond, it can be either carbon of benzene ring, it can be either carbon of carbocation, it can be either of carbon free radical. So whenever such species are there, you can simply say hyperconjugation is present. But according to NCERT, what is hyperconjugation? Have a look. According to NCERT, hyperconjugation is simply delocalization of sigma electrons. But which sigma electron? Delocalization of sigma electron of CH sigma bond. Sigma electrons of which bond? CH sigma bond. But that CH sigma bond should be of alkyl group. And this alkyl group should be attached to either unsaturated system, that means either triple bond or double bond species, or it should be attached to an atom containing what we call unshared p orbital. That means containing p orbital without any electron or p orbital with odd electron. I hope this is clear to each and every one. Now, have a look. Types of hyperconjugation. There can be, as this is an extension of resonance, so in case of resonance, there was pi-pi conjugation and pi-p conjugation. Instead of pi, here it is sigma. So it is sigma pi and sigma p conjugation. Have a look. Here, this is the sigma bond of CH sigma bond of alkyl group is in conjugation with pi bond, hence this is known as sigma pi. Here it is CH sigma bond which is in conjugation with this carbocation p orbital, so this is sigma p. Here it is in conjugation with p orbital of odd electron carbon, hence sigma p. Now listen carefully how to draw these hyperconjugative structures. Now listen. So we can simply say this sigma orbital can overlap with this. So when this sigma orbital overlaps, this will be the resonating hyperconjugative structure. If this CH sigma bond overlaps with this, then this will be the overlapping structure. This will be the hyperconjugated structure. If this CH bond overlaps, then this will be the hyperconjugated structure. But none of them is actually the hyperconjugative structure. They give, none of them is the actual structure actually. They give us information about hyperconjugation. So this is the actual structure, and in this actual structure, this CH sigma bond, this CH sigma bond and this CH sigma bond, as they take part in overlapping, their sigma electron density is uniform over here, here and here. So whenever overlapping takes place in such a way, whenever sigma bond overlapping of CH bond takes place in such a way that all CH sigma bonds are having same sigma electron density, this is known as delocalization of sigma electron, known as what we call hyperconjugation. So look towards this. Can we say positive and negative charges are separated? So here charge separation has been taken place in sigma pi hyperconjugation. But in this sigma positive, only positive charges are present. There is no charge separation. Here only odd electrons are present. There is no charge separation. Hence, there is no charge separation. Here charge separation is there. So types of hyperconjugation, there are broadly two types, sigma pi and sigma p, but according to Muller and Mulliken, there are two types of hyperconjugation. One is sacrificial, another is isovalent. Sacrificial hyperconjugation is that type of hyperconjugation in which charge separation takes place, and that means that is sigma pi. And isovalent hyperconjugation is that type of hyperconjugation in which there is no charge separation. That means that is basically sigma p, yani that is sigma positive or sigma odd electron hyperconjugation. I hope this is clear. I hope this is clear. Now, the question is here, it's a simple formula that how many hyperconjugative structures will involve CH sigma bond if structure is open structure or if structure is aliphatic structure, then it's equal to number of alpha hydrogens. Have a look. Here 3 alpha hydrogens were there. So 1, 2 and 3 hyperconjugative structures are there for this structure, or 3 hydrogen CH hydrogen bonds are involved. That's why they form 3. Similarly, this can form 1, 2, 3. Similarly, this can form 1, 2, 3. But in total, how many total hyperconjugated structures will be there? Number of alpha hydrogen plus 1. Plus 1 means that itself, this one. Plus 1 means this one as well. Plus 1 means this one as well. So this is the formula for aliphatic species. After that, my dear lovely students, there is application. That means stability of carbocation, carbon free radical, and stability of alkanes. It's not alkane, it's alkene. Let me correct this. Let me correct this. It is alkene. Let me correct this. Stability of carbon free radical, carbocation and alkenes. Listen, this is alkene. This is directly proportional to extent of hyperconjugation. And another is heat of hydrogenation. It is directly proportional to number of pi bond. But if number of pi bonds are same, at that time it is inversely proportional to stability. Now have a look and answer me this question. Now have a look. This carbon is having positive charge. There is no sp3 hybridized carbon attached to it. But here it is sp3 hybridized carbon attached to it. So this becomes alpha carbon. And to this alpha carbon, there are 3 hydrogens. So this is having 3 alpha hydrogens. So this positive charge is attached to this sp3 hybridized carbon. So this is alpha. 3 and 3, 6 alpha hydrogens are there. Similarly, this is having 9 alpha hydrogens. So more the number of alpha hydrogens, more will be the hyperconjugation, more the hyperconjugation, more will be the stability. So in nutshell, we can simply say 4, 3, 2, 1 will be the stability order. 4, 3, 2, 1 will be the stability order. Similarly, my dear lovely students, this is alpha. So here 3 alpha hydrogens are there. Because whether carbocation, carbon free radical, carbon having double bond, it's attached to sp3. sp3 becomes alpha. So this is alpha, so 6 alpha hydrogens. This is alpha, this is alpha, this is alpha, so 9 alpha hydrogens. So this is having 0 alpha hydrogen. So according to hyperconjugation, answer will be 4, 3, 2 and 1. This will be the stability order according to hyperconjugation. Similarly, this is alpha, this and this is alpha. Similarly, this is alpha carbon, alpha carbon, alpha carbon, alpha carbon. Alpha carbon means sp3 hybridized carbon attached to carbon-carbon double bond or attached to carbocation or attached to carbon having an odd electron. So this is having 0 alpha hydrogen. So what will be the stability order? 4, 3, 2, 1 will be the stability order. Because more the number of alpha hydrogens in general, more will be the hyperconjugation. More hyperconjugation means more will be the stability. After that, heat of hydrogenation. First of all, look towards these compounds. These all are having same number of pi bonds. If they are all having same number of pi bonds, check stability only. Check stability only. So this is having 3 alpha hydrogen, this is having 6 alpha hydrogen. Which one is least stable among them? It is this one. So heat of hydrogenation order is always inversely proportional to stability. So I will write down 1, 2 and 3. So 1, 2, 3 will be the answer because this is heat of hydrogenation, and heat of hydrogenation is inversely proportional to stability provided number of pi bonds are equal. Here, pi bonds are 2, pi bonds are 2, pi bonds are 2. Now, we will check alpha hydrogens. So this is alpha, so 4 alpha hydrogens. Here, this is alpha with respect to double bond. With respect to double bond, this is alpha, 2 and 1, 3 alpha hydrogens. With respect to double bond, this is having 1 alpha hydrogen, that means only 2 alpha hydrogens are there. Because this is the carbon which is directly attached to carbon-carbon double bond. And this is sp3, that's why this is alpha. So least alpha hydrogen means lesser number of alpha hydrogen means least stable. Least stable means that is having more what we call heat of hydrogenation. That's having more heat of hydrogenation. Oh, let me show this once again. Let me show this once again. This is alpha. This is alpha and alpha. This was having 6 alpha hydrogens. This was having 3 alpha hydrogens. And this was having 0 alpha hydrogens. So the heat of hydrogenation answer will be simply 1, 2 and 3. This is the answer. After that, my dear lovely students, this is alpha, 4 alpha hydrogens. This is alpha and alpha, 3 alpha hydrogens. This is having alpha, alpha, that means 2 alpha hydrogens. So stability order will be 3, then 2, sorry, not stability order, heat of hydrogenation order will be 3, 2 and 1. Because this is heat of hydrogenation order. Heat of hydrogenation is inversely proportional to stability if number of pi bonds are equal. If number of pi bonds are identical or equal. After that, we have to compare bond length. Once again, same which was used in resonance, but the only thing here is we have to check hyperconjugation over here. Have a look. Have a look. This is a proper double bond. This is a double bond. This is a double bond. What about this? This is a partial double bond. Partial double bond. But it seems to be a double bond. Once again, this is a partial double bond. But it seems to be a double bond. Now, first, this is double bond. these two are partial double bond. That means double bond will be at the end. So X will be at the end. These two are partial double bonds, but which seems to be double bond. That means use this one. Use this one. Count alpha hydrogens. So it's having 2 alpha hydrogens. This is having 3 alpha hydrogens. So more the alpha hydrogen, more extent of resonance, more will be the bond length. That means I will write down first Y. After that, I will write down Z. And after that, I will write down X. Simple. Now, what about this one? What about this one? It seems to be what we call a single bond, and it is a single bond. Seems to be single bond, and it is single bond because there is no hyperconjugation. This seems to be a single bond, but it is a partial double bond because there is hyperconjugation. Why hyperconjugation is present in this? Why not this? Because this is having 1 alpha hydrogen. This is not having any alpha hydrogen. This is having 2 alpha hydrogen. So hyperconjugation once again is present. That means this one becomes the partial double bond, but it seems to be a single bond. Now, these two are partial double bond. This is single bond. Write single bond first. That means we will write down X first. After that, among Y and Z, use this formula. This is having only 1 hydrogen. This is having 2 hydrogens. So this is having more extent of resonance, lesser bond length. This is having lesser extent of resonance, more bond length. So I will write down Y. After that, I will write down Z. Now tell me, is this clear till now? Quick. Is this clear till now? Don't write 1, 2, 3. Don't write 1, 2, 3 because 1 is the molecule, 2 is the molecule, 3 is the compound. I mean, say molecule or a compound. You have to say bond length. You have not, you don't write 1, 2 and 3 because 1 is not the bond. Bond is X, bond is Y, bond is Z. So write down X, Y, Z instead of 1, 2, 3. Instead of 1, 2, 3. Okay, is this clear? Is this clear? After that, there is directive influence of alkyl groups. Have a look. This is an alkyl group which can undergo hyperconjugation. Because of hyperconjugation, alkyl group donates electron towards the ring and increases electron density of the ring at ortho and para position. Increase of electron density means negative charge appears at ortho and para position. That means alkyl groups donate electron because of hyperconjugation and increases electron density of the benzene ring at ortho and para position. That clearly indicates alkyl groups are ortho-para directing with respect to electrophile. So alkyl groups are, they increase simply electron density of the ring mainly at ortho and para position because of hyperconjugation, and alkyl groups are ortho-para directing with respect to electrophile. But only those alkyl groups which can undergo, I mean to say, hyperconjugation. Like resonance and what we call, like resonance, we can simply say hyperconjugation has no effect on meta position. That means resonance as well as hyperconjugation has no effect on meta position. After that, my dear lovely student, there is reverse hyperconjugation. Point number 1, when is it present? If carbon is sp2, but only either carbon-carbon double bond or it is of benzene ring. And to that carbon, alpha carbon should be, that means attached carbon should be sp3, and to that sp3 carbon there must be at least one electron withdrawing group as well as a good leaving group like halogen. Have a look. Now this halogen is a good leaving group. It will leave with electron, so it will become deficient, it will withdraw electrons. So what will happen? Electrons have been withdrawn away from benzene ring. That means if this is hyperconjugation, it donates electron towards benzene ring, it withdraws electrons away from benzene ring. That means it is reverse to that of hyperconjugation. That is why this is known as reverse hyperconjugation or negative hyperconjugation, minus H. Now, because of this CH3 group withdraws electrons away from what we call benzene ring and decreases electron density at an ortho and para position. That means beta becomes by default electron rich. So CH3 group in nutshell is what we call meta directing group. Is this clear to you? Now, like resonance and hyperconjugation, this reverse hyperconjugation or minus H has no effect on meta position as well. After that, remember, in case of benzene derivatives, this is the formula. It's not only number of alpha hydrogens, it is 3 into number of alpha hydrogens. Have a look. Because of this 1, 2, 3. Similarly, because of another 1, 2, 3, because of another 1, 2, 3, that means number of these say alpha hydrogens in this case. Have a look. Number of alpha hydrogens. So this one hydrogen forms 3, another hydrogen forms 3 hyperconjugated structure, another hydrogen shows 3 hyperconjugated structures. In nutshell, it can show further 9 hyperconjugated structures. That means number of alpha hydrogen 3 multiplied by 3. So 3 into number of alpha hydrogens. 3 into number of alpha hydrogens. After that, we will be having a temporary effect that is known as electromeric effect. Listen carefully. Have a look. What is meant by electromeric effect? Have a look. Can I say like this? Can I say like this? C double bond C, H and H. Have a look. There is no displacement of electron because there is no electronegativity difference. So no displacement of electron takes place over here. But when this reagent approaches this pi bond, it withdraws electrons towards itself. That means pi electron density has been now shifted completely towards one of the atoms linked together by means of multiple bond in presence of reagent. So complete transfer of pi electron towards one of the atoms linked together by means of multiple bond because of presence of reagent is known as electromeric effect. But once there is no reagent, there will be no electron displacement effect. That means electronic displacement effect is absent in absence of reagent, and it is present in presence of reagent. This sort of what we call displacement is known as temporary displacement effect and is known as electromeric effect. So what is electromeric effect? Complete transfer of pi electrons towards one of the atoms linked together by means of a multiple bond in presence of a reagent. That's why this is known as a temporary effect and is called electromeric effect. Now, that electromeric effect in which pi electrons are transferred towards an atom to which reagent gets finally attached. Have a look. Pi electrons are transferred towards an atom to which reagent gets finally attached is known as plus E, and during this effect cations are obtained. And another electromeric effect in which pi electrons are transferred towards an atom other than the one to which finally reagent gets attached. Reagent gets attached to this, but pi electrons are transferred to other atom. So this is known as minus E effect. And remember, this electromeric effect is generally used in different reactions. Now, after that, there is another effect that is known as inductomeric effect. This is also a temporary effect because it takes place in presence of reagent, and in absence of reagent, it does not take place. Now have a look. Listen carefully. Can I say, in case of CH3Cl, there is partial displacement of electron. That partial displacement of electron is known as inductive effect. That means here inductive effect takes place. But transfer of electron is partial. But in presence of reagent, when reagent is there, complete transfer of electron takes place. That means, can I say, this sigma electron transfer is now not partial, but it is complete. That means we can simply say that this inductive effect, transfer of electron, transfer of sigma electron, inductive effect has been increased due to presence of what we call reagent. That effect is known as simply what we call inductomeric effect. That means, what is inductomeric effect? It is that effect which enhances or increases this moment of sigma electron, transfer of sigma electron. That means it enhances or increases inductive effect, and it occurs only and only in presence of reagent and is called inductomeric effect. Or you can simply say inductomeric effect is that effect with the help of which sigma electrons are transferred completely towards one of the atoms in presence of reagent. I hope this is clear. So this was all about inductomeric effect. Now, these are 3 important points which you should remember, that whenever stability of carbocation is given, if it is that carbocation during which resonance is possible, hyperconjugation is possible, inductive effect is possible, then you have to remember this. That means plus R, plus H and plus I stabilizes the carbocation, but these 3 destabilizes the carbocation. And this should be your order. Plus R, first you have to check plus R. After that, you have to check plus H. After that, you have to check plus I. Plus H means hyperconjugation. Then that species which does not have any, effect, this is the order with the help of which you can find out stability of carbocation. This is stability of carbanion, and this is stability of free radical. But in this is very, very important point. You should remember this. Whenever carbon free radical is attached to either plus R or minus R, its stability is increased. Its stability is increased. Here it is plus R increases stability, minus R decreases stability. Here, minus R increases stability, plus R decreases stability. But here, both plus R and minus R increases stability because of that effect. But we will not, touch that effect, and I will not tell the name even of that effect. So you simply remember plus R and minus R. Simply remember minus R and plus R. Or if you want to remember the name is Keto-Dative Effect, but don't go there. You should simply remember plus R and minus R. Now, my dear lovely students, this is what we call all about GOC. Now, we will take isomerism now, but we will discuss isomerism after break. We will discuss isomerism now after break. We will discuss isomerism after break. Now, it is 1:35. Exactly, we will meet at 2:15. So break till 2:15 p.m. So this is break till 2:15. But I would want you all guys to be present at 2:15 p.m. Now, is everything clear now in GOC? Is everything clear now in GOC? Let me know quickly so that we can have a lunch. Come on, guys. Tell me quickly. Okay. That is great. That is great. So let's meet on once again. Let's meet once again. But I would want you all guys to be present at 2:15 because there is another important chapter, and that is known as isomerism. So till then, take care, bye-bye, and love you all. Okay, welcome once again, and good afternoon. I hope we are live now. Let me know in the chats if I am audible and visible to each and every one. Please let me know quickly. Please let me know in the chats if I am audible and visible to each and every one. Let me know in the chats quickly. Am I audible and visible? Okay, that's great. That is great. So without wasting time, let's get started. Let's get started with the very important chapter, isomerism. Have a look. First of all, we should know what is meant by double bond equivalent or degree of unsaturation, or what we call index of hydrogen deficiency. So definition over here, definition is that number of hydrogen molecules required so as to convert an unsaturated molecule to a saturated one. What is meant by that? Have a look. For example, you are having an unsaturated molecule like this, ethene, and you want to convert this ethene to ethane. So how many molecules of hydrogen do we need? We need one molecule of hydrogen. Similarly, if we want to convert this ethane to alkane, because this is an unsaturated species, to convert unsaturated molecule to saturated molecule, we need one molecule of hydrogen. Here, to convert this unsaturated molecule to saturated molecule, we need two molecules of hydrogen. So the number of molecules required so as to convert this molecule unsaturated into saturated one is known as its degree of unsaturation. So its degree of unsaturation is 1, or its index of hydrogen deficiency is 1, or its double bond equivalent is 1. Similarly, its degree of unsaturation is 2, because number of hydrogen molecules required to convert this into saturated is, say 2. And remember, these are saturated molecules, and for saturated molecules, degree of unsaturation is always 0. That means no need to remember the formula for du. You can calculate du simply by comparing your compound with, say, saturated hydrocarbon alkane. And do you know what is the general formula of alkane? General formula of alkane is CnH2n. That means just compare number of hydrogens of a compound with number of hydrogens of alkane, you will get number of hydrogen molecules required so as to convert unsaturated to saturated one. That means you will get degree of unsaturation. How? Have a look. For example, we have to calculate degree of unsaturation. First of all, question written over here is C2H2. That means compound is a hydrocarbon. Now, this hydrocarbon contains 2 carbons. Now compare it with the hydrocarbon which is alkane having 2 carbon atoms. Number of carbon should be same. So here number of carbons is 2. So alkane having 2 carbon is C2H6. Now what is the difference between these hydrogens? How many hydrogen atoms are there in alkane, and how many hydrogen atoms are there in this compound? This is having simply 6 hydrogens, and this is having only 2 hydrogens. Have a look. So we have to compare it with alkane having same number of carbons. So can we say from this to this, we need how many hydrogen atoms? We need 4 hydrogen atoms. That means we need 2 hydrogen molecules. As we need 2 hydrogen molecules from this to this, or to convert this into this, we need 2 hydrogen molecules. That means degree of unsaturation for this molecule is 2. Similarly, here number of carbons are 10, so I will write down C10H. We know the general formula of alkane is CnH2n plus 2. So if n is 10, let me write down over here. It is CnH2n plus 2. Now, n value is 10. Then what will be 2n plus 2? That means that will be 22. So it is CnH22. So from this to this, we need how many hydrogen atoms? 4 hydrogen atom. That means we need, 2 hydrogen molecules. So once again, its degree of unsaturation is 2. Is this clear? Is this clear to each and every one? Now, have a look. It is C6H6. Can I write? It is C6. C6. That means N is 6. Then it is 6 into 2. 2 into 6 is 12. 12 plus 2 is 14. That means our saturated hydrocarbon should be C6H12. Now, compare it with this. There are 8 hydrogen atoms, deficiency of 8 hydrogen atoms, or we need 8 hydrogen atom to convert this into this. That means we need 4 hydrogen molecules. So degree of unsaturation simply is what we call 4. So if you are having hydrocarbons, then compare that hydrocarbon with alkane having same number of carbons, you will get degree of unsaturation easily. But if we are having carbon hydrogen and in addition to that we will be having fluorine, chlorine, bromine or iodine, say for example, then what we have to do is just remove chlorine, remove that fluorine, chlorine, bromine or iodine, and in addition to that add same number of hydrogens. That means this molecule becomes C6H6. Now for this, compare it with say alkane having same number of carbon atoms. Now compare it with alkane having same number of carbon atoms. Now if I compare it with alkane having same number of carbon atoms, that means I have to compare it with C6H14. From this to this, we need 4 H2 molecule. That means degree of unsaturation for this is 4. Hence, degree of unsaturation for this is also 4. Now, so if fluorine, chlorine, bromine, iodine is there, replace that fluorine, chlorine, bromine, iodine with same number of hydrogens. If you are having oxygen or sulfur, that means bivalent species, then just remove that bivalent species. Remove that. The remaining thing is hydrocarbon. Now compare it with alkane having same number of carbons. That means C7H16. How many hydrogen molecules do we require to convert this into this? We require 4 hydrogen molecules. Once again, that means degree of unsaturation once again is 4. I hope this is clear. After that, if you are having nitrogen or phosphorus, that means if in addition to hydrogen and carbon, we are having nitrogen, we are having phosphorus, that means we are having trivalent species. Then what to do? Remove that trivalent species and also remove equal number of hydrogens. Also remove equal number of hydrogens. So remaining thing becomes C7H8. It becomes C7H8. Once again, it is C7H8. Compare it with alkane C7H16 having same number of carbons. Then once again we need 4 hydrogen molecules. So once again degree of unsaturation here is 4. Now tell me, can you calculate now degree of unsaturation? Tell me quickly. Can you calculate degree of unsaturation now? Tell me quickly. Tell me quickly. Can you calculate degree of unsaturation now? Let me know in the chats, my dear lovely students. Come on, quickly. Let me know in the chats quickly. Can you calculate degree of unsaturation now? Yes, sir. Come on, everyone. Okay, that is great. I'm not ma'am, beta. I'm sir. Okay. So, now we can calculate. Okay. After that, what is isomerism? Listen carefully. Different compounds having same molecular formula are called isomers. And the phenomenon is known as isomerism. Are called isomers and the phenomenon is known as isomerism. And the phenomenon is known as isomerism. Listen carefully. Now, if you are having different compounds, but those different compounds have same molecular formula, such compounds are isomers and the phenomenon is known as isomerism. And this isomerism is of two types. One is structural, constitutional, regio or linkage isomerism. Another is known as stereoisomerism. So let us discuss first structural isomerism. What is meant by structural isomerism? Listen carefully. Isomers which differ in connectivity or which differ in structural formula are called structural isomers, and the phenomenon is known as structural isomerism. That means if isomers differ in connectivity, if isomers differ in structural formula, then we can call those isomers as structural isomers. Now the question is, what is meant by connectivity? What is meant by structural formula? For that, let's discuss different types of structural isomers so that you can simply understand what is meant by connectivity or what is meant by structural formula. So first type of structural isomerism is chain isomerism. Now what is meant by chain isomer? Listen carefully. Chain isomers are those structural isomers which differ either in arrangement of carbon chain, whether that carbon chain arrangement is different in parent chain or side chain within the molecule. Such structural isomers are called simply chain isomers, nuclear isomers or skeletal isomers, and the phenomenon is known as chain isomerism, skeletal isomerism, or what we call simply nuclear isomerism. Have a look, my dear students. What is the formula of these compounds? These are different compounds. One is butane, another is 2-methyl propane. So different compounds having same molecular formula, hence they are isomers. But listen carefully. These two are having different connectivity because this carbon is having CH3, 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 but such connectivity is not present in this. That means these two are basically having different connectivity, having different structural formula, hence they are structural isomers. Similarly, this carbon is having ethyl group attached to it, but it's not having any ethyl group attached to it. This is having 2-methyl at 2 positions. So they differ in connectivity, they differ in structural formula, hence they are structural isomers. But these are those structural isomers which differ. These two differ in parent chain, because if we number over here, it's 1, 2, 3 and 4. That means there are 4 carbons in the parent chain, but here are only 3 carbons present in parent chain. That means these are those structural isomers which differ in arrangement of carbon chain, and that arrangement is different as per their parent chain is concerned. Hence they are known as chain isomers. Similarly, if we number this chain, if we number this parent chain, this is having 6 carbons in parent chain, this is also having 6 carbons in parent chain. But what about side chain? There are 2 carbons in the side chain. There is only 1 carbon atom in this side chain. There is only 1 carbon atom in this side chain. In nutshell, these are the structural isomers which differ in arrangement of what we call carbon chain, but that arrangement is different in their side chains. Hence, they are also known as chain isomers. But remember, my dear lovely student, this is very, very, very important point, that these two are chain isomers, but they belong to same homologous series. These two are chain isomers, that means they belong to same homologous series. When they belong to same homologous series, that means they are having same functional groups. So remember, chain isomers are always having same functional group. Similarly, chain isomers are always having same functional group. After that, we will be having another one, that is position isomerism. What is meant by position isomer? Position isomer is that type of structural isomer which differ from each other in position, but in position of either functional group, in position of either substituent, in position of either double bond, or in position of either triple bond. Have a look. There is different connectivity, hence they are structural isomers. Different connectivity, hence they are structural isomers. Different structural formula, hence they are structural isomers. But here, functional group is OH. Here, functional group is also OH. That means functional groups are same. But the position of functional group is, it's present at 1 position. Here, it's present at 2 position. Hence, position of a functional group varies. Similarly, here, substituent. Position of substituent varies because Cl halogens are always treated as substituents. Here 2 halogens are present at 1,2 position. Here 2 halogens are present at 1,1 position. Hence they differ in position of substituent. They differ in the position of functional group. These differ in position of double bond. Have a look. Here double bond is between 2 and 3. Here double bond is between 1 and 2. So they differ in position of double bond. They differ in position of triple bond. These two. Hence, these two differ in position of what we call triple bond. Hence, we can simply say these isomers are what we call, they are known as position isomers. But remember, position isomers also belong to same homologous series. That means they are having same functional group. These two are having same functional group because these two are position isomers. These two are not position isomers. These two are position isomers. These two are position isomers. Hence they belong to same homologous series. They have same functional group. Second point. Position isomers have same chain. Same chain. There is no variation in chain. If variation in chain is there, then it is simply what we call chain isomer. After that, another type is, but before that, there is a question and there is information. Maximum number of carbons required to show, number one, chain isomerism and position isomerism. As per alkanes are concerned, number of carbons should be 4. And as per alkenes is concerned, number of carbon 4, alkynes, number of carbon 4, alcohols 4, as per chain isomerism is concerned. Similarly, for position isomerism, number of carbons in alkanes must be 6, in alkenes there must be 4, and alkynes there must be 4, and alcohols there must be 3. But remember, minimum number of carbon atoms required to show position isomerism is 2. Why is 2? Why not 3? Have a look. These two are position isomers and minimum number of carbons in these are 2. So you just remember these things as well. After that, my dear lovely students, there is a rule known as CS rule. Sometimes it's also known as XY rule, but I have written CS because C means number of carbons, C stands for carbon, S for substituent. That's why CS rule. What is CS rule? CS rule says if CS value for isomers, remember first of all, both the compounds or compounds should be isomers. So if CS value for 2 or more than 2 isomers have, if 2 or more than 2 isomers have same CS value, then such isomers are position isomers. And if they have different CS value, then they are chain isomers. Now the question is, what is meant by CS? Have a look. C stands for number of carbon atoms in a parent chain and S stands for a number of substituents. Have a look. This is 1, 2, 3 and 4. Number of carbons. Carbons here is 4. Substituent is absent. There is no substituent. So CS value here is 40. Similarly, this is 1, 2, 3. Now here C is 3, 4 is 1 because this is methyl group acting as a substituent. Now tell me, can I say CS value here is 3, 1? Now look towards these. These two are isomers, but their CS value is different. CS value is different. Hence, these two are simply chain isomers. Hence, these two are chain isomers. Now have a look. This is 1, 2, 3 and 4. Number of carbons present in a chain, that means C is 4. There is no substituent because this is the functional group. There is no substituent. So CS value here is 40. What about this? 1, 2, 3, 4. Both are isomers. Now here C is 4, S is 0. So CS value for this compound is also, say 40. Look towards these two isomers. Both are having same CS value. Hence these two are what we call position isomers. So this is what we call CS rule. After that, my dear lovely students, there is another type, that is metamerism. Now the question is, what is metamerism? Metamerism is basically that phenomenon during which metamers can be obtained. So what are metamers? Have a look. Structural isomers which differ in arrangement of carbon chain or arrangement of carbon atom or carbon. In addition to that, it may be either carbon atom or you can say alkyl group, aryl group, cycloalkyl group. It can be any group on either side of, but this is very, very, very important, on either side of polyvalent functional group. That means the functional group present in a compound should be polyvalent. It should be bivalent, trivalent, but not monovalent like CHO, COH, or say alcohol. They never show metamerism. Now have a look. These type of functional groups can show what we call metamerism, but first of all, this type of functional group should be present. After that, on either side of the functional group in different compounds, there must be different carbon atoms or different groups. Have a look, have a look. If I talk about this is the oxygen, a bivalent functional group. Two sides of this oxygen, it's 1 carbon and 3 carbon. 1 and 3 carbons are on two sides. 1 carbon alkyl group and 3 carbon alkyl group. Now, what about this ether? It's 2 carbon, 2 carbon. That means it's having 2 carbon alkyl group, 2 carbon alkyl group here on both sides of oxygen. And here it's 1 carbon and 3 carbon. Now have a look. Can I say 1 carbon, 3 carbon is different than 2 carbon, 2 carbon? That means around bivalent functional group, around polyvalent functional group, they differ in what we call carbon atoms or they differ in these groups. Now, these are known as what we call simply metamers and the phenomenon is known as metamerism. Similarly, this ketone is a polyvalent functional group. This is a polyvalent functional group. Similarly, this ketone is a polyvalent functional group. To this ketone, this polyvalent functional group, 1 carbon, 3 carbon groups are there. Here, 2 carbon groups are there. That means around this polyvalent functional group, groups are different. Groups which are present over here, they are not present in this. The groups which are present over here, they are not present in this. That means here, 2 groups are different as compared to these 2 groups. It's not like that these 2 groups should be different. No. Whatever the groups are present in this, these 2 groups should not be present over here. I hope this is clear. Now, after that, look towards this. This is also a polyvalent functional group. This is also a polyvalent functional group. But there is difference between these and this. This is the only one atom to which alkyl groups or groups are attached. This is the only one atom of this to which groups are attached. But here, there are 2 atoms. One is carbon, another is oxygen. Can I say to oxygen, there is methyl, and to carbon, there is propyl. Here, to carbon, there is methyl, and to oxygen, there is propyl. Listen carefully. Here, to oxygen, there is methyl. Here, to oxygen, there is propyl. That means to this side, these groups are different. Similarly, to carbon, there is methyl. To carbon, there is propyl. That means to this side, groups are different. In nutshell, these 2 groups are different as compared to these 2 groups. How? Because these 3 carbons are attached to oxygen. Here, only 1 carbon is attached to oxygen. Here, 1 carbon is attached to carbon, but here 3 carbons are attached to carbon. Hence, these are what we call metamers. But remember, metamers also belong to same homologous series. That means they must have same functional group. And metamers can also be sometimes called as special type of what we call positional isomerism, because here it is functional group is present at 2nd position, functional group is present at 3rd position. So sometimes they can also be called as positional isomers. Now, I hope this is clear. After that, there is another isomerism, that is functional isomerism. And remember, functional isomer is simply that structural isomer which differ from each other with respect to their functional group. That means they must have different functional groups. Now, listen carefully. Suppose here are few examples of functional isomers. Suppose saturated alcohol and saturated ether. This is having their general formula. Suppose if N is 2, can I say it is C2, then it is H6 and O. Suppose C2H6O is this one. C2H6O is this one. Have a look. C2H6O. C2H6O. Have a look. You can use different values of N, but I have, first of all, N, if N is equal to 2. If N is equal to 2, then these, this alcohol and this ether, they are having same formula. Same formula, but listen carefully, they are having same formula, but their functional group is different. Here, functional group is OH, alcohol. Here, functional group is ether. So can I say these 2 are having different functional groups, but they are isomers, structural isomers, hence they are what we call functional isomers. Similarly, you can use different values for N over here and you can draw structures, but try to remember these compounds because it is aldehyde having, it's aldehyde and ketone having same formula, which can be, functional isomers. It can never be an aldehyde and a saturated ether. They can never be what we call functional isomers. Similarly, carboxylic acid can be functional isomer of ester, but carboxylic acid can never be functional isomer of thiol. So remember these compounds as well, or these examples as well. After that, these are further examples. Try to remember these examples with formulas so that N can be any value and you can use the structure at that time. After that, there is ring chain isomerism. Now, what is meant by ring chain isomerism? This is structural isomerism. Remember, structural isomers which differ in such a way that one is, one possesses a cyclic structure, another possesses open structure. Remember, but both are having different functional groups. Have a look. Say, for example, one is alkyne, another is cycloalkene. Similarly, one is alkene, another is cycloalkane, having these formulas. Suppose, let me write down this one. Suppose if N is, as this is cyclo, for cyclo, carbon should be at least 3. So, suppose carbon is 3. Now, what will be the formula? CnH2n, formula will become C3H6. Now, alkene, C3H6 is like this. Can I write down like this? This is alkene. Now, what is cycloalkane? Cycloalkane, can I write down like this? So 1, 2, 3 carbon, 3, 4, 6 hydrogens, and this is having 1, 2, 3 carbon, 2, 2, 2 hydrogens. That means these 2 are simply what we call ring chain isomers. Why? Because one possesses open structure, another possesses ring structure. Both are structural isomers and both are different, having different functional groups. One is having cycloalkane, that means alkane functional group, cycloalkane functional group. Other are having alkene functional group, that means they are having different functional groups. Now the question is, if this question is asked in an exam and you have to choose only one option, and options are like, they are number 1, position isomer, number 2, chain isomer, number 3, functional isomer, number 4, they are what we call ring chain isomer. Now, they are not chain isomer, they are not position isomer, but they are functional isomer, they are ring chain isomer. You have to choose only one. At that time, use this preference order, and preference order is RTF MCP. But what is R? R means ring chain isomer, T means tautomerism, F means functional isomerism, M means metamerism, C means chain isomerism, and P means position isomerism. Have a look. These two are having different functional group. That means they are ring chain as well as functional isomer. But I will prefer ring chain if I have to choose only one, because ring chain comes first in what we call preference order. I hope this is clear. But remember, whether it is ring chain isomer, whether it is functional isomer, whether it is tautomer, they have different functional groups. But if we talk about two metamers, they are having same functional group. Two chain isomers are having same functional group. Two position isomers are having same functional groups. I hope this is clear. After that, my dear lovely students, there are few questions. How to approach these questions? Look towards the board. Have a look. Have a look. First of all, tell me, what are these two compounds? Are they having same what we call functional group, or they are having different functional group? First of all, you have to check whether they are isomers or not. But these are isomers, these are isomers, this is isomer, but these two are not isomers. I will show that. So first of all, you should know that these two are isomers. Once you know these two are isomers, after that, second point is you have to check their functional group. Their functional group is same. If functional group is same, look towards this. If functional group is same, look towards this. They can be either metamer, chain isomer, or position isomer. They can never be RTF. If functional group is same, that means they can be either M, they can be either C, they can be either P. But for metamerism, there must be polyvalent functional group, but there is no polyvalent functional group, so I will cross this. Now, for chain and position, use CS rule, use CS rule. Now have a look. Here, chain carbon containing in this chain is 6. Substituents are 1, 2, 3. So CS value is 63 or 63. What about this? C is 6. S value is once again 1, 2, and 3. So once again, CS value is 63. Now tell me, these two are having same CS value. Then these two are simply what we call position isomers. These two are simply what we call position isomers. So this is the relation between these two. This is the relation between these two. Very, very simple. After that, have a look. These are having same functional group. Same functional group means either metamer or chain isomer or position isomer. But here, which type of functional group is this? This is univalent functional group. Univalent. It can form only one bond. Just give me a second. I will, just a second. I will put on my shoes basically. Just a second. Okay. Now, so these are what we call having same functional group. So it can be either metamer, chain isomer, or position isomer. But this is univalent functional group, so this can never be a metamer. So after that, let's check whether it is chain or position with the help of CS rule. So 1, 2, 3, 4, 5, 6 carbons are there here. 1, 2, 3, 4, 5 carbons are there. So carbon is having number of carbons 5. Substituent, that means S value. Substituents is number 1. That means CS value is 5, 1. Very simple. Here C is 6, S is 0. That means CS value is 6, 0. They are different values. CS values are different. Hence these are chain isomers. Very simple. Chain isomers. What about this? Have a look. This is having a functional group OH. This is having functional group O. That means different functional groups. Hence they are functional isomers. They are having functional isomers. Now what about these two? Look towards the board. This is basically the polyvalent functional group? First of all, both are having same functional groups. That means it is either metamer, chain isomer, or position isomer. Now, for metamerism, there must be polyvalent functional group. So, polyvalent functional group is there. Now, check first this carbon. To carbon, there is benzene ring. To this carbon, there is cyclohexane ring. That means here, groups are different. What about this? Here, at oxygen, it is cyclohexane. At oxygen, it is benzene. That means here, groups are different. So, can I say these two compounds are structural isomers, and groups from this side as well as from oxygen side, they are different. Hence, these two are simply metamers. These are what we call metamers. Now, after that, have a look. These two are having different functional group. Hence, they can be either ring chain isomer or functional isomer, because we have not studied tautomer yet. So they can be either R or F, but one is having, say closed structure, one is having open structure. So I will simply give preference to ring chain isomerism, or to say functional isomerism, because preference order is RTF MCP. Now, what is the name of this compound? Have a look. 1, 2, 3, 4, 5, 6. Its name is 1-bromo-3-chlorohexane. Oh, sorry, 1-bromo-3-chlorobenzene. What about this one? 1, 2, 3, 4, 5, 6. This is once again 1-bromo-3-chlorobenzene. That means name of these compounds is identical. If different compounds, if there are more than one compound and all the compounds are having same name, same formula, that means they are not different. If they are not different, they can never be isomers. So can I say they are identical species or they are homomers? So they are identical or they are homomers. I hope this is clear. So this is the relation. After that, you have to remember this, my dear lovely students. For alkanes, there is, say the column, the table. Just try to remember this, because if question is from alkane, you will directly answer that question, that how many total possible structures or structural isomers will be possible. So this is the answer. For alkyl groups, just try to remember this, because we can use this in different questions. Try to remember this. Try to remember this. Now, come. Let's have this one. Let's have this one. Question is, find total structural isomers for C4H9Cl. Listen carefully. It is C4, it is H9, and then it is Cl. Now tell me, how many structural isomers are possible for C4H9? It is 4. So answer is simple. Answer is simple. Answer is as 4 isomers are possible, so our answer should be 4. That's it. So the question is, total structural isomers for C4H9Cl will be 4. You don't have to show which are those structures. Don't need to draw those structures. Now, after that, find total number of structural isomers for C4H10O. First of all, when we talk about C4H10O, its general formula is CnH2n plus 2O. Have a look, because carbons here are 4 and hydrogen is double of 4 plus 2. That means it is 2n plus 2. So give value of n as 4, it will become this one. So that means it clearly indicates, have a look. It clearly indicates, have a look. It clearly indicates CnH2n plus 2 means saturated alcohol and saturated ether. It clearly indicates that our compound is basically alcohol and ether, saturated alcohol and ether. For alcohols, listen carefully. For alcohols, trick is like this. Write down functional group OH. If I write down OH from this, how many carbons remain? It remains 4 carbons and 9 hydrogens. And we know C4H9 means 4 isomers are possible. So there are 4 alcohols for this one. Then let me show you ethers now. How to show ether? Listen carefully. First of all, ether functional group is O. Write down CH3 on one side. So that means among this we have written O and CH3. The remaining part will be C3H7. So write down this. Among these alkyl groups, which one is larger? It is this one. Count number of possible isomers of larger one. We know this can form 2 isomers. Have a look. I will show you once again that table. It is C3H7, it is 2. CH3 and C2H5 is 1, 1. C3H7, 2. C4H9, 4. C5H11, 8. Now, have a look, have a look, have a look. So after that, add CH2 from this side, from right side, where you have already written CH3. Now, carbon, add carbon. Carbon and carbon becomes carbon 2, that means C2. H3 plus H2 becomes H5. After that, O remains as it is. Then this side you have to subtract CH2. Here you have to add, here you have to subtract. So subtract 1 carbon from C3, that means it becomes C2. H7 minus H2 means H5. Among these two, which one is, say larger alkyl group? You can take any one because both are identical. So say for example this one. And we know this can form one isomer. Have a look, have a look. This can form one isomer. C2H5 can form one isomer. I hope this is clear. Now, after that, my dear lovely student, add CH2. When you add CH2, listen carefully. It becomes C3H7, C2 and add C, C3, H5 plus 2 is H7. After that, here you have to subtract CH2. It becomes CH3. But listen. This oxygen is attached to CH3. This oxygen is also attached to CH3. This oxygen is attached to C3H7. It's also attached to C3H7. That means this is basically this one. That means this one has been repeated. Once it has been repeated, we don't need this one. We don't need this one. So now the total number of ethers is 2 and 1, 3. Total number of alcohols is 4. That means 4 plus 3, total isomers will be 7. Total isomers will be 4 plus 3 is equal to 7. So this is having total possible structural isomers in the form of alcohol and ether, and total will be 7. 4 will be alcohols and 3 will be ethers. I hope this is clear. After that, there is once again a question, but question is that how many alcohols will be primary, how many will be secondary, how many will be tertiary. Then if question is like this, then you cannot use this trick. Then you have to remember this one. You have to remember this one. How many carbons are there? 4 carbons are there. Listen carefully. Try to draw 4 carbons in a chain. What are the total possibilities of these 4 carbons? One possibility is its connectivity. All the 4 should be present in one chain, and second possibility is that 3 carbons are present in one chain, and fourth one is, say outside the chain as substituent, as side chain. So there are 2 possibilities. Now listen carefully. If I give hydrogens to them, listen. So this is what we call one type of hydrogen, say alkane. This is another type of alkane. Now listen. As this is an alcohol, and alcohols can be obtained from alkane by replacement of H with the help of OH. So listen carefully, what we have to do is, we have to simply check if this is carbon A, that means you have to check surroundings, all the 4 groups attached to this carbon. This is also A. Why? Because here HHH on 3 sides and CH2, CH2, CH3 on 4th side is attached. This is also HHH, CH2, CH2, CH3. So these 2 are identical carbons. That means identical hydrogens are also there. So these are having, say type B. Similarly, this and this is A type, this is B type. Now listen carefully. Now tell me, we have to replace one hydrogen by one OH. If I replace this A by one OH, then don't replace this A because product will be same. Say for example, if I replace this H by OH, product will be CH3, CH2, 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 OH, that means butan 1-ol. Similarly, if you replace this H by one OH, once again it will become butan 1-ol. That means among these, only one you have to replace, only one hydrogen by OH. Similarly, among these, if you replace hydrogen of B by OH, don't replace this one as well. That means these are the 2 possibilities from this. If you replace from this, don't replace from this and this. And you can replace from B as well. In nutshell, how many hydrogens can be replaced by OH? 1, 2, 3, 4. That is why C4H2O shows, say total number of alcohols possible is 4. Total possible alcohols are 4. 1, 2, 3 and 4. But which type of carbon is this? This is primary carbon. So if you replace hydrogen by OH, OH will be attached to primary carbon, that will be a primary alcohol. What about this hydrogen? This is a secondary carbon. This is a secondary carbon. Hydrogen, once replaced from this and OH is attached to that, it will become a secondary alcohol. Similarly, this is a primary carbon and this is a tertiary carbon. Now tell me. If we replace primary hydrogens, and that means hydrogens attached to primary carbon, if we replace primary hydrogens of primary carbon by OH, we get primary alcohol. So how many primary alcohols can be possible? From this, primary alcohol is possible. From this, primary alcohol is possible. That means 2 primary alcohols are possible. From this, 1 secondary alcohol is possible by replacing H by OH. And from this, tertiary hydrogen will be replaced by OH. That means 1 tertiary alcohol is possible. That means primary alcohols which are possible are 2, and secondary alcohols which are possible is only 1, and tertiary alcohol possible is also only 1. I hope this is clear. Total number will be 4, but among these 4, 1 will be tertiary, 1 will be secondary, and 2 will be, primary. So you have to find out primary, secondary, and tertiary. I hope this is very, very clear. So first of all, when alcohol is given and primary, secondary, and tertiary, you have to find out primary, secondary, and tertiary. Just form same number of alkane. I mean, say that alkane contains same number of carbons. Form that. Total possibilities, total carbon chains. Then after that, check how many different types of carbons or how many different types of hydrogens are there. Then replace hydrogen by OH and check whether that hydrogen has been replaced from primary carbon or secondary or tertiary. If hydrogen has been replaced from primary carbon, alcohol will be primary alcohol. If hydrogen will be replaced by OH from secondary carbon, alcohol will be secondary alcohol. And if hydrogen will be replaced from tertiary hydrogen by OH, at that time you will get tertiary alcohol. After that, find total aldehydes and ketones for this one. Have a look. We know for aldehydes, it's very simple for aldehydes. Have a look. Aldehydes is having CHO formula, functional group CHO. Now, among this, if I have written CHO, remaining part will be C3H7. And we know C3H7 shows, or for C3H7 there are 2 possible structures. There will be 2 structures which are possible. Hence, 2 structural isomers will be of aldehyde. For ketones will be like that of ether. Have a look. Ketones. We know ketone is having C double bond O functional group. Just attach CH3 on right side of this. Now, 2 carbons are already there. Among 4, 2 are there. So remaining 2 is there. Among 8 hydrogens, 3 are there. That means remaining are 5. Among these 2, this one is larger. And we know this ethyl can show 1 structural isomer. After that, add CH2 from this side. C and C means C2. H3 and H2 means H5. After that, it is C double bond O. Here you have to add CH2, and from this side you have to subtract CH2. So it becomes C and then H3. But this C of C double bond O is having methyl and ethyl on 2 sides. This is also having methyl and ethyl on 2 sides. That means it is repeated. If it is repeated, we don't need this one. If it is different, then we will count it. So this formula is having 1 ketone and this formula is having 2 aldehydes. In total, it's having 2 plus 1, that means 3. But 3 are aldehydes and ketones. Among those, 2 are aldehydes, 1 is ketone. I hope this is clear. After that, there are carboxylic acids and esters having formula C4H8O2. Listen carefully. And by the way, these formulas are having du equal to 1, and whenever du is equal to 1, in this case, let me tell you, in this case du is equal to 1. du1 means there must be either pi bond or a ring. So as du is 1, we already have C double bond O. That means already pi bond is there in the functional group. Pi bond is already in the functional group. That's why other structure will be like this. Similarly, this is also having du equal to 1, and we know our carboxylic acid is having C double bond O, OH. That means already pi bond is there. So this is carboxylic acid. And among ester, there is already C double bond O. So remember, for carboxylic acid, what we have to do is, listen carefully. This is the carboxylic acid. What we have to do is, we will simply write down COOH. When I wrote COOH, remaining number of carbons will be C3. and H1 is there, so H7 is remaining. Now, tell me C3H7, how many isomers? 2 isomers for this one. Now, after that, have a look. After that, I will write down ester. For esters, what you have to remember is, write OCH3. Ester is this one. Write COO, write CH3 from right side, I mean say from oxygen side. After that, 2 carbons are already there. Among 4, 2 remains. So among these 2, this is, I mean say the larger one, so it forms 1 isomer. After that, add CH2 from this side. It becomes C2H5. Then O remain as such, C double bond O remain as it is. Here you have to subtract CH2. When you subtract CH2, it becomes CH3. But this is different than this. How this is different than this? Have a look. CH3 here is attached to O, but here CH3 is attached to C. Here it is C to which C2H5 is attached, but here C2H5 is attached to O. That means C2H5 is here attached to C, here it is attached to O. CH3 here it's attached to O, but here it is attached to C. That means these two are different. That means we have to count this as well. But this is methyl, this is ethyl, larger one is this one, and we know this also forms 1 isomer. This also forms 1 isomer. After that, we will add CH2. It becomes C3H7. Then it is O, then it is C double bond O. Then you have to subtract CH2. When you subtract CH2, it becomes H. Now, among H and C3H7, this is alkyl part, so look towards this part. C3H7 can form 2 isomers. Now, you will stop over here. That means for esters, you have to stop when this H is attached to C double bond O. That means here you have to stop. Why? Because you cannot subtract CH2 from this. You cannot subtract CH2 from this because from this side you have to subtract. So you have to stop here. So there are 2, 3, 4. 4 esters are possible. 4 esters are possible, and in total 2 plus 4 are possible. That means 6 number of, I mean say carboxylic acid and esters are possible for this one. I hope this is clear. I hope this is clear. Let me know in the chats, is this clear to each and every one, so that I can show this one as well. Let me know in the chats. Let me know in the chats, quick. Is this clear till now? Is this clear till now, so that I can show another question as well? Let me know. Okay, clear. That is great. Okay, my dear lovely students, have a look. If we talk about C4H11N, have a look. We know this is an amine. If this is an amine, amines are of 3 types. One is primary amine, another is secondary amine, another is a tertiary amine. You know that. Now we have to check primary amine, secondary amine as well as tertiary amine. For primary amine, formula is, I mean say functional group is NH2. If I write down NH2 first, remaining part will be C4H9. And this remaining part is having 4 isomers possible. So I will write down 4. For secondary amine, I will write down NH because this is the functional group. But on right side, I will write down CH3. So the remaining part will be, because 1 carbon is there, so remaining part will be C3H7. Among these 2, this is the larger one, so it will form 2 isomers. After that, add CH2 from this side. When you add CH2 from this side, it becomes C2H5. NH remain as it is. Here you have to subtract CH2, so it becomes C2H5 once again. Can I say this is different from this? So among these 2, you can take this one or this one because both are identical. This will show 1. After that, add CH2. When you add CH2, it becomes C3H7. And here, when you subtract CH2 from this, it becomes CH3. But listen, here N is attached to CH3, here N is also attached to CH3. Here N is attached to C3H7, here N is attached to C3H7. That means it has been repeated. So don't need this. Now tell me, how many total secondary amines are there? Total secondary amines are 4, and total what we call primary amines are 4. Total secondary amines are 3 in number. Now, what about tertiary amine? Tertiary amine is this one. Tertiary amine is N. So write CH3 on two sides now. The remaining part will become C2H5. So larger one is this one. So it forms one. After that, add, say for example, we will add CH2. We will add CH2 to this, and what will happen? It becomes C2H5. And then it becomes CH3. It remains as it is. Then this will be, say subtract CH2 from this side, it will become CH3. Now tell me, N is attached to ethyl and two methyl groups. N is attached to ethyl and two methyl groups. That means this is once again same. That means I will not take this one. Now, so this is not possible. Now, if I add CH2 to this, because I have added CH2 to this, if I add CH2 to this and subtract this from this, it once again becomes same. That means it is not possible. It's only one is possible. Only one isomer is possible for this. Now tell me, 1, 3 and 4. Total isomers possible. Total amines possible. 4, 3 plus 1. Answer is 8. I hope this is clear. I hope this is clear. After that, find total number of structural isomers for this one. Have a look. First of all, du is equal to, for this, you know, you have to compare it with same number of carbon containing alkane. That means same number of carbon containing alkane has a formula C4H10. That means 2 hydrogen atoms required. That means 1 molecule is required. That means du is 1. When du is 1, listen carefully, it means it contains 1 pi bond or it contains 1 ring. It contains 1 pi bond or it contains 1 ring. So if it contains 1 pi bond, that means those structures are open structures. So first of all, let's check open structures. Now have a look. This is the open structure and this is the open structure which is possible. And for this and this, they are similar, and this are similar. Similarly, these are same types of carbons and this is different type of carbon. Now, if you have to form a pi bond, that means a double bond, you can form double bond either between A and B. Then if you form double bond between A and B, don't form once again double bond over here because same compound will be obtained. Similarly, you can form double bond between B and B. That means there are two possibilities. Here, you can form double bond between either this or this or this. That means if you form here, don't form double bond over here. That means total possibilities of double bond 1, 2 and 3, which means one of the structure will be like this. You will form double bond over here. This is known as but1-ene. Another possibility is that you will form double bond between B and B. That means these are two possibilities of this. Similarly, there is the possibility like this. CH2 double bond C, CH3, CH3. So these are three alkenes which are possible when you put one double bond with this formula. Then after that, with respect to ring, what is possible? With respect to ring, 4 carbons with respect to ring means this one. It cannot be having 5-membered ring. It can have a maximum of 4-membered ring, or minimum it can be having 3-membered ring, but 1 carbon is missing. So you can put 1 carbon over here or here or here. That means it will be simply methyl cyclopropane. So 2 structures are cyclic structures and these 3 structures are what we call acyclic structures. That means total number of structural isomers possible are 5. I hope this is clear. After that, there is another, isomerism, that is tautomerism. It has different names, but few names are here. Number 1 is desmotropism, cryptomerism, allylotropism, merotropy, prototropy, reversible isomerism, dynamic isomerism. So you can remember these. But what is meant by basically tautomerism? Remember, it is that structural isomerism, or simply whenever you are having structural isomers which differ from each other with respect to their functional group, or which differ with respect to their structural formula, and the reason is only their hydrogen which is mobile. Basically, their hydrogen is oscillating. In nutshell, we can simply say structural isomers are interconvertible into one another due to hydrogen migration between 2 polyvalent atoms within the same molecule and are called tautomers, and the phenomenon is known as tautomerism, and tautomers are always in equilibrium with each other. What is meant by that? Have a look. Have a look. If I talk about this carbon, CH3, if we talk about this compound, say for example, CH3CHO. Now what will happen? If C and hydrogen bond is broken, carbon, say for example, carbon attracts its electron towards itself. Say for example, H loses as H positive. Then carbon becomes carbon negative. Now once this becomes carbon negative, it will form a double bond. Once it forms a double bond, this pi bond will be broken. That means, let me show like this. Can I show like this? Now here these electrons form a double bond. Double bond forms a negative charge. As this is negative charged species, it will attract this hydrogen towards itself. In nutshell, the structure will be like this: CH2, double bond C, single bond O, single bond H, and then H. Yes or no? Now similarly, if O and H bond is broken, O withdraws its electron towards itself, then it forms a pi bond with this. That means like this. H loses as H positive. Both these electrons go to this carbon. Then this carbon will attract H positive towards itself. In nutshell, what has happened? This hydrogen has been migrated from this carbon to oxygen, or from carbon to oxygen, from oxygen to carbon. Whenever hydrogen migration or proton migration takes place between two polyvalent atoms, polyvalent means more than, which can form more than one bond. So whenever hydrogen migration takes place between two polyvalent atoms within the molecule, remember, between two polyvalent atoms within the same molecule, then those compounds which are obtained, they differ in their what we call functional groups as well as in their structural formula. Such compounds which differ in their structural formula as well as in their functional groups, or which can be interconvertible into one another due to migration of, say this hydrogen as proton between two polyvalent atoms within the same molecule, these compounds are known as at that time what we call tautomers, and the phenomenon is known as tautomerism. Now listen once again, you can read this statement. What is this? Structural isomers which are interconvertible into one another. Due to hydrogen migration between two polyvalent atoms within the same molecule, they are called tautomers, and the phenomenon is known as tautomerism. But remember, tautomers are having different functional groups, they are having different structural formula. After that, tautomerism is of many types. Number one, it's of open system, ring system, and what we call valence system, but these two are not in syllabus. So our focus should be on open system. Open system is further of two types. One is catianotropy or prototropy, another is aninotropy. But remember, this aninotropy is generally studied. It is generally studied under the heading allylic rearrangement. It is generally studied under the heading allylic rearrangement. That means this is not important for us. So our important tautomerism is catianotropy or prototropy. Remember, catianotropy or prototropy is of two types. One is dyad system, another is triad system. Dyad system means 1-2 proton migration. 1-2 proton migration, my dear lovely students. What is meant by that? Have a look. Suppose carbon and hydrogen bond is broken. H will be lost as H positive. That H positive goes to this nitrogen, or nitrogen attracts that H positive towards itself. So it will become C having negative charge, and then N, as it donates electron towards nitrogen, it becomes this one. Similarly, if nitrogen withdraws its electron towards itself, H is lost as H positive, then this negative charge will accept this H positive. In nutshell, if this is 1, this is 2, adjacent positions. If carbon is 1, say for example carbon is 1, nitrogen is 2. Similarly, carbon 1, nitrogen 2, or nitrogen 1, carbon 2. So between 1 and 2 position, between adjacent positions, hydrogen migration takes place. This is known as simply dyad system of tautomerism. Similarly, if 1-3 proton migration takes place, because proton or cation has been migrated, that's why catianotropy or prototropy. Now, if this is 1, this is 2, this is 3. What is meant by 1-3? 1-3 means alternate position. Alternate position. What has happened? From 1, hydrogen has been migrated to, say third position. Similarly, from this 3, hydrogen has been migrated to, say first position. So this is 1-3 hydrogen or 1-3 proton migration, known as prototropy. Listen, prototropy is further of 12 types, but the most important type is Keto-Enol Tautomerism. Most important type is Keto-Enol Tautomerism. So what is Keto-Enol Tautomerism? Listen carefully. That type of tautomerism in which keto form gets converted to enol and enol gets converted to keto. Keto means where C double bond O group is present, but that C double bond O group generally is of either aldehyde or ketone or of ester. Whenever you are having C double bond O group of aldehyde, ketone or ester, that form is known as keto. And when you are having carbon-carbon double bond and to that double bonded carbon there is OH, that means if ene and alcohol is there, if ene and ol is there, that form is known as enol. So whenever your keto gets converted to enol and enol gets converted to keto, that type of tautomerism is known as Keto-Enol Tautomerism, and this is the most important type of, what we call triad system, or this is very important type of tautomerism or prototropy. Now, important thing is, what about Keto-Enol Tautomerism? Actually, Keto-Enol Tautomerism is actual type of 1,3 triad, proton migration, that means triad system, but sometimes this proton migration can be beyond 1,3. That means it can be 1,5, 1,7, 1,9, 1,11 migration. At that time, we call that type of tautomerism as space tautomerism. Now, have a look. Important condition for Keto-Enol Tautomerism. If you are having a keto form, suppose question is whether this keto form shows Keto-Enol Tautomerism or not. For keto form, you have to remember, first of all, you have to identify the keto form. Whenever you identify the keto form, after that keto form must contain at least one hydrogen attached to sp3 hybridized carbon. There must be at least one hydrogen but attached to sp3 hybridized carbon. And this hydrogen should be such that if hydrogen is removed as H positive, the negative charge on that carbon which was first sp3 hybridized, now this negative charge should be in conjugation with that of C double bond O. If it is like that, then we can say keto can be converted into enol. That means keto can form Keto-Enol Tautomerism. So have a look. There must be at least one hydrogen atom attached to sp3 hybridized carbon and that if this hydrogen is removed from sp3 carbon as H positive, it results in the formation of a carbanion which is in conjugation with that of C double bond group. Similarly, if you are having enol form, then you must remember there must be at least one carbon-carbon double bond, and to that double bonded carbon there must be at least one OH group. If it is like that, then these two conditions are fulfilled. But these two, in addition to these conditions, this is very, very important, but that if both conditions are valid, if this condition is present, you can say Keto-Enol Tautomerism is present. If this condition is present, you can say Keto-Enol Tautomerism is present, but only and only provided their stability is not affected drastically. What is meant by that? Have a look towards this question. Now, have a look. If we talk about this compound, this is keto form. This is keto form. Now, in keto, what we have to identify is, we have to identify whether there is sp3 hybridized carbon to which hydrogen is attached. As there is no sp3 hybridized carbon to which hydrogen is attached, so this will not show Keto-Enol Tautomerism. It will not show Keto-Enol Tautomerism. What about this? There is no sp3 hybridized carbon to which hydrogen is attached, hence it will not show Keto-Enol Tautomerism. What about this? It is having sp3 hybridized carbon. Have a look, my dear lovely student. It's having this sp3 hybridized carbon, but this sp3 hybridized carbon does not have any hydrogen. After that, it's having sp3 hybridized carbon, this one. This carbon is sp3, this carbon is sp3, but when hydrogen is removed from this sp3 hybridized carbon, have a look. If hydrogen has been removed from this, negative charge on this carbon is not in conjugation with this, hence it will also not show Keto-Enol Tautomerism. What about this? It is having hydrogen at sp3, and if this hydrogen is removed, negative charge over here is in conjugation with oxygen, hence it will show Keto-Enol Tautomerism. Similarly, if this hydrogens are here, have a look, hydrogens are here, so these are known as enolizable hydrogens. Now, if this hydrogen is removed, negative charge over here shows resonance and is in conjugation with C double bond O, hence it can show Keto-Enol Tautomerism. This cannot show, these two hydrogens cannot show, this can show. If this hydrogen is removed, this hydrogen, negative charge over here is in conjugation with this C double bond O, hence it shows Keto-Enol Tautomerism. What about this? Once again, C double bond O is there, but If this hydrogen is removed, negative charge is in conjugation with C double bond O, hence it can show Keto-Enol Tautomerism. Listen carefully, listen carefully. If this hydrogen is removed, negative charge over here, form double bond over here, double bond O minus, and then O minus will abstract H. That means its form, next form will be like this. Have a look. It will be like this. It will be like this. That means it can show Keto-Enol Tautomerism. It can show Keto-Enol Tautomerism. But here condition is that it is having sp3 hybridized hydrogen. If hydrogen is removed, negative charge is in conjugation. Negative charge is in conjugation. But my dear lovely student, listen carefully. Negative charge once again in conjugation can form this one. But remember, this is anti-aromatic, highly unstable. As this is highly unstable, it is not formed, and if it is not formed, that means our condition which is present. But remember, conditions are applicable only and only if stability is not affected drastically. Here stability is affected drastically. It becomes highly unstable. That's why this hydrogen will not migrate, so there will be no Keto-Enol Tautomerism. I hope this is clear. After that, this is an enol, double bond attached directly, OH is directly attached to double bond. That means it shows what we call Keto-Enol Tautomerism. But here, this is aromatic. This is aromatic. If it shows Keto-Enol Tautomerism, then what will happen? It will become double bond O and it will become like this. That means from aromatic it becomes non-aromatic. It will not prefer to go from aromatic to non-aromatic. That's why hydrogen will not migrate. There will be no Keto-Enol Tautomerism. Similarly, there are two hydrogens. One hydrogen is this, but this will not take part in what we call hydrogen migration. Here, these hydrogens can take part in hydrogen migration. In nutshell, this will show Keto-Enol Tautomerism. Now the question is why it will not show. Because if it shows hydrogen migration, listen carefully. If it shows hydrogen migration, then double bond will be over here, and this double bond is not possible. Why double bond is not possible over here? Because at bridgehead carbon, there can never be sp2 hybridization if ring is up to 8-membered ring. That means according to Britt's rule, this cannot be possible, but yes, double bond can be possible from this side and hydrogen can be migrated. That means it can show Keto-Enol Tautomerism. After that, my dear lovely students, compare enol content. That means first you have to form enols of these, and after that you have to compare which one is more stable. Its enol will be like this. Its enol will be like this. Have a look. Its enol will be like this. Can I say here enol is more stable because of more resonance? As enol is more stable, that means it can form more enol content as compared to this. So the answer of this question is simply 2 greater than 1. Answer is 2 greater than 1. Similarly here, enol will be like this. Enol will be like this. Here enol will be like this. Which one is more stable? This is aromatic. This is more stable. If this is more stable, once again 2 can form easily enol, or 2 can form more enol as compared to 1. You have to compare enol content. So enol content of 2 is more as compared to 1. Have a look. This is beta diketone. This is beta keto ester. Remember, beta diketone, beta keto ester. Its enol is like this. Its enol is like this. Its enol is like this. Listen carefully, listen carefully. Here, chelation is there. Intramolecular hydrogen bonding. Here, intramolecular hydrogen bonding. That means with respect to intramolecular hydrogen bonding, both are equally stable. With respect to, I mean to say bond energy, both are equally stable. But with respect to resonance, here, listen, here, it is extended conjugation. Or you can say linear conjugation. But here, it is cross conjugation. Here, it is cross conjugation. With respect to this double bond, it's cross conjugation. Listen carefully. It's cross conjugation. One conjugation is from this side, another is opposite to this. So this is cross conjugation, this is linear conjugation. Linear conjugation means more resonance, more stability. That means 1 greater than 2 will be the answer. Now here, when it forms an enol, it forms enol like this. which is anti-aromatic. It forms enol like this, which is non-aromatic. It forms enol like this, listen carefully, which is aromatic. Now tell me, aromatic is more stable than non-aromatic. Non-aromatic is more stable than anti-aromatic. So 3 can form enol content more as compared to 2. 2 can form enol content more as compared to 1. I hope this is clear. Just a moment, give me a second, because I'm going to on this one. Okay. Now I hope this is clear. I hope this is clear. So you just form enol and then compare stability of enol by using different concepts, like you can use aromaticity concept, you can use resonance concept, you can use hyperconjugation, you can use chelation, you can use, I mean to say, bond energies, everything you can use with the help of stability. You can tell me which one is the more stable. Okay, now one is keto, another is enol. Listen carefully. In general, keto form is more stable. Keto form is more stable than enol form. This is in general, but this is based on bond energy calculation. Let me tell you that keto forms basically loses 361 kilocalories per mole, 361 kilocalories per mole energy, and enol loses, I mean say, 343 kilocalories per mole energy. Try to remember this. That is why loss in energy is more over here as compared to this. So this is normal keto and this is enol. So this is less energetic because more energy has been lost as compared to this. So I will say 1 greater than 2. So stability order will be simply 1 greater than 2. Here, my dear lovely students, listen carefully. As per this keto, this enol and this enol is concerned, energy, bond energy will be simply 361 kilocalories per mole. Listen carefully. Here it is enol, so 343 kilocalories per mole. Here it is 343 kilocalories per mole. Because for enols, energy will be same. For keto, energy will be different. Now, this is according to bond energy. So this is bond energy calculation. After that, my dear lovely students, can I say here it is chelation? Here it is chelation. Listen carefully. So chelation is present in 2 and 3, not in 1. That means if we talk about chelation, it's absent over here. But here, because of chelation, force of attraction will be there. So approximately 7 kilocalories per mole energy is lost. 7 kilocalories per mole energy is lost. Done. After that, there is resonance. There is resonance. That means there will be resonance energy. Here, resonance energy is more. Why? Because this is in conjugation with this pi and this pi is in conjugation with this pi. But here, there is only this conjugation, there is no conjugation over here. So remember, here, resonance energy is approximately 11 kilocalories per mole. Here, it is less than 11 kilocalories per mole. Now tell me, total amount of energy lost is less than 361. Here, resonance is absent. So here it is 361. Here it is less than 361. Here it is more than 360. It is more than, I mean say, 361. Because it's not only 5. It is, let me write down, it's not 11. It is, sorry, it's 15. It's not 11. It's 15. Now, here it is more than 361. It is 365. Now, can I say, this is the species where energy is lost more overall. So more loss in energy means less energetic, means most stable. In nutshell, I will erase this one. Listen carefully what you have to remember. What you have to remember. This is, I mean say, the experimental data. Now, I will tell you the trick. How will you remember? Listen carefully. This is beta diketone. Because if this is ketone, this is alpha, this is beta. So this is beta diketone, and these are 2 enol forms of beta diketone. And in case of beta diketone, that enol is more stable than keto form, which is having pi bond in conjugation with C double bond O. That means this one is more stable. And another enol is less stable than keto form. That means 213 will be the answer. 213 will be the answer. I hope this is clear. After that, my dear lovely students, this one is, I mean, say keto form. That means this is a non-aromatic species, but this is an enol form. It's anti-aromatic species. Anti-aromatic species are less stable. So can I say it is simply one which is more stable than two? So aromatic, so here, this is anti-aromatic, this is non-aromatic. Non-aromatic is more stable than this one. Listen here, listen here. This is beta keto ester. What is this? This is beta keto ester. Remember, in case of beta keto ester, keto form is more stable than enol form. Remember this simply. So it's 1 greater than 2. Why? 2 is not that much stable. Reason is here is basically cross conjugation. Now, after that, among these two, this is non-aromatic and this is aromatic. Which one is more stable? Obviously, 2 is more stable than 1. Aromatic species is more stable than non-aromatic species. After that, this is normal ketone. This is normal ketone. This is not beta diketone or beta keto ester. This is normal ketone. In normal ketone, keto form is always more stable. So I will write down 1. After that, these two enols, have a look. Both are having similar amine resonance. But when we talk about hyperconjugation, this is having alpha carbon 3 and 3, 6 alpha hydrogens are there. This is having only 2 alpha hydrogens. So this is more stable as compared to this. So I will write down 2 and then 3. So this is the answer. I hope this is clear to each and every one. After that, my dear lovely student, there is another part, that is stereoisomerism. But before that, let me know in the chats if I am clear to each and every one till now. If I am clear to you till now. Is everything clear till now? Is everything clear till now? Let me know in the chats quickly. Let me know quickly. Let me know quickly. Come on, show some green hearts as well. Show some green hearts as well. You can show some green hearts as well. Come on, come on, come on, come on, come on, show some green hearts so that I may be very much motivated. Come on. Come on, my dear lovely students. Come on. Great, 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 great. That is great. That is great. That is great. Okay, now let's talk about stereoisomerism. What is meant by stereoisomer? Listen carefully. Those compounds which are having same molecular formula but which are having as well as same structural formula, but they differ in relative arrangement of atoms or groups in three-dimensional space, are known as structural. These are known as stereoisomers, and the phenomenon is known as stereoisomerism. That means they are having same molecular formula, same structural formula. Listen this. But they are having only different relative arrangement of atoms or groups in three-dimensional space. Now, it's of further two types. One is conformational isomer, another is configurational isomer. But in actual sense, conformational isomer is not actually the isomer, but you have to remember this because this is, everywhere, in different books. Now, what is meant by conformational isomer and what is configurational isomer? Listen. Conformational isomers are those stereoisomers which can be interconverted into one another by simple rotation about sigma bonds. But if stereoisomers cannot be interconverted into one another by simple rotation about sigma bonds, at that time we call that as configurational isomer. And this configurational isomerism is further of two types. One is geometrical, another is optical, but we will discuss geometrical and optical afterwards. But first of all, we will talk about what is meant by conformational isomerism. So what are conformational isomers? These are simply those stereoisomers which can be interconverted into one another by simple rotation about sigma bonds, and the phenomenon is known as conformational isomerism. So that means these are basically converted into one another by simple rotation about sigma bonds. And about sigma bond rotation is very simple because the amount of energy which is needed to rotate that sigma bond is already available in these surroundings. Now, listen carefully. But when we rotate the molecule on rotation, when one molecule, one form gets converted into another form because of rotation, we call those isomers as conformational isomers, or we can also call them as rotamers. During rotation, or remember, during this rotation, bond angle and bond length remains always same. That means bond length and bond angle in all conformers, rotamers or conformational isomers are same. But you have to remember, they can never be isolated. They can never be isolated from each other at room temperature. When they cannot be isolated, they cannot be distinguished, they cannot be, isolated from one another. Hence, in real sense, they cannot be called as isomers. But let me tell you that these are the conformational isomers, but they cannot be they cannot be isolated from each other at room temperature because they're always interconverted into one another. Point number one. Point number second, bond length and bond angle remain same in all conformations, or in all conformers, or in all conformations, or in all conformational isomers, or in all what we call rotamers. Now, first conformational analysis is of ethane, which is in your NCERT. Now, ethane means C2H6, that means CH3CH3. Say, for example, this is ethane, this is front carbon. Let's suppose this is this carbon, front carbon, and this is another carbon. Let's suppose this is the back carbon. Now, front carbon contains 3 hydrogens. So, front carbon contains 3 hydrogens, 1, 2, and 3. Back carbon contains 3 hydrogens. Now, listen carefully, my dear lovely students. Now, the bond angle between this CH of front carbon and CH of back carbon. That means bond angle between CH of front carbon and CH of back carbon. This is known as dihedral angle. This is known as dihedral angle, and it is denoted by theta. Here, what is the bond angle between CH of front carbon and CH of back carbon? It is 0. Whenever you are having a conformation in which CH bond angle, or we can say the bond angle of front carbon and or bond present at front carbon and bond present at back carbon, the angle between bond present at front carbon and bond present at back carbon, if it is 0, we call that conformation as eclipse conformation. Similarly, if we talk about this bond, say for example this bond, this bond and this bond. If we talk about these two bonds, that means one bond of front carbon, another bond of back carbon. If bond angle is 60 degree, minimum bond angle, if minimum bond angle is 60 degree, we call that as staggered form. That means, remember, if we talk about ethane, in case of ethane, infinite number of conformational isomers are possible. Infinite number of conformations are possible. Infinite number of rotamers are possible. But in those infinite number, 2 extreme forms are very important. One is eclipse form, another is staggered form. In eclipse form, dihedral angle is 0. In staggered form, dihedral angle is 60 degree. Now, there are other forms whose dihedral angle can be greater than 0 degree or whose dihedral angle can be less than 60 degree. Those forms are known as skew forms. Those are known as skew forms. Now, if we talk about these two forms, tell me, can I say this bond is having an electron cloud, this bond is having an electron cloud? As they are very close together, there will be more electronic repulsions there. So, electronic repulsions between two bonds of different, carbons, front carbon and back carbon, we can simply call such type of repulsions as they are known as what we call torsional repulsions, and the strain is known as torsional strain. So, in case of eclipse form, there is torsional repulsion or there is, torsional strain. Similarly, the repulsion between, two atoms or two groups present at two different carbons, present at front carbon and back carbon, due to, size, the repulsion because of size, repulsion because of mass is known as van der Waals repulsion or steric repulsion. So, here it will be hydrogen and hydrogen. They are very closer to each other. But here hydrogen and hydrogen are, not closer, they are far away from each other. So there will be no van der Waals strain, van der Waals repulsion or steric strain. Similarly, there will be no electronic repulsion between these two bonds. That means there will be no torsional strain. In nutshell, we can simply say staggered form is free from torsional strain, or here repulsions will be lesser as compared to eclipse form. So eclipse form is more energetic as compared to staggered form. So if we talk about energy, then eclipse form is having more energy as compared to staggered form, and approximately their difference in energy is 3 kilocalories per mole. If this is 3 kilocalories per mole, this is 0. If this is 0, this is 3. If this is 2, this is 5. There is, say the difference of 3 kilocalories per mole. So this is more energetic as compared to this. So we can simply say staggered form is more stable than the eclipse form as per ethane is concerned. Similarly, my dear lovely students, same thing happen in propane, but the only difference is here, repulsion, say between the CH3 and this H will be slightly more as compared to this H and H or this H and H. So here, energy difference will be slightly more. That means here, energy will be actually like this. It will be 3.3. That means more than 3. Slightly more than 3. So the difference between energy difference will be slightly more because of more, say steric repulsions over here. Now, similarly, once again, staggered form of propane is more stable than eclipse form. Once again, theta is 0. At that time, it's eclipse. Theta is 0. That means dihedral angle is 60. At that time, it is staggered. So during this rotation, bond angle remains same, bond length remains same, but dihedral angle changes. Remember that. After that, we will be having N-butane. Now, N-butane is having infinite number of forms, but these 4 forms are very important. Actually, these are 2 forms. One is eclipse, another is staggered. Now, have a look. Whenever theta is 0, we call eclipse. So this is eclipse, this is eclipse. This is theta 60, so staggered, theta 60, staggered. But these 2 theta forms where theta is 60 are staggered. These 2 theta is 0 are eclipse, but among these 2, this is known as fully eclipse and this is partially eclipse. Now, which one is fully eclipse? Remember that. If dihedral angle between 2 bulky groups is 0, it is fully eclipse. If theta between bulky groups is 120, it is what we call partially eclipse. If theta between 2 bulky groups is 60, then it is gauche. Then similarly, if theta between 2 bulky groups is 180, it's NT. That means staggered is having 2 forms. One is NT, another is gauche. Similarly, this eclipse is having 2 forms. One is fully eclipse, another is partially eclipse. And you can simply check which one will be more stable. This one becomes more stable because of lesser repulsions. After that, it will be gauche. That means staggered first, but among staggered, it will be NT first. After that, it is gauche. After that, it will be eclipse. But among eclipse, this will become more energetic because CH3 repulsion will be more as compared to this. So in nutshell here, steric repulsions will be more. So we can simply say first staggered, after that it's eclipse, but among staggered it is first NT, then gauche, and among eclipse it is first partially eclipse and finally it is fully eclipse. So this is written over here. So first staggered is more stable than eclipse, but among staggered it is NT and gauche. And among what we call eclipse form, it is partially eclipse first. After that, it is fully eclipse as per their stability is concerned. So first NT, gauche, partially eclipse, fully eclipse according to stability, but according to energy, just reverse this. That means fully eclipse, partially eclipse, gauche, and NT. These are the differences from NT form. If NT is 0, this is more energetic, 0.9 kilocalories more energetic than this, but this is 3.6 more energetic than this, and this is 5 kilocalories more energetic than this approximately. I hope this is clear. But there are few examples. Where staggered is more stable than eclipse. There is no doubt about that. But among staggered, gauche is more stable than NT. This is the example and this is the example. So I will simply mark over here. This is one. This is another example where gauche is more stable than NT, and this is another example. This is another example where gauche is more stable than NT. So you have to remember, if you are having a group like this and Z are these values, then in gauche there is electrostatic force of attraction between this positive part of hydrogen and negative part of whether it is O, whether it is F, whether it is Cl, whether it is N, whether it is O. So there will be simply electrostatic force of attraction or what we call chelation or intramolecular hydrogen bonding in gauche form, which makes gauche more stable as compared to NT. Similarly, here it is ion dipole interactions which makes it more stable. Here it is simply once again hydrogen bonding which makes gauche more stable. Otherwise, it is always what we call NT which is more stable. So try to remember these examples so that everything is clear to you. After that, my dear lovely students, there is conformational analysis of cyclohexane. This is not basically in your syllabus, but question can be asked. So you have to simply remember the stability order of this. Simply, it is shear form which is most stable. After that, it is twist boat. After that, it is boat. After that is half shear, and energy order will be reversed to that of this. So this is one thing what you have to remember. Second thing you have to remember is that among these conformations, infinite number of conformations are possible, but these are important. And among these important conformations, it is the only form, twist boat is the only form which is optically active or which is chiral form. Listen carefully. These 2 points, remember these 2 points only. That's it. Remember these 2 points only. Remember this. But sometimes you are having this cyclohexane, but to this cyclohexane there are substituents. Say for example, hydrogen has been replaced by different groups, methyl, bromine, chlorine, so on and so forth. So different alkyl groups may be there. Say for example like this. So for this you have to remember that more stable conformation is that in which bulky groups, listen this, remember this, that's it. No need to go through this in detail. Just remember this. More stable conformation is that in which bulky groups are present. At equatorial positions. Remember this, that's it. Remember this. Now have a look. This bond is known as axial bond. This is axial, but this bond is known as equatorial bond. This is equatorial. So bulky groups are both present on equatorial. Here one is equatorial, one is axial. Both are present on axial. So whenever bulky groups are present on equatorial position, it makes it more stable. So I will write down 3. After that it is 2. After that it is 1. So more number of bulky groups at more equatorial positions is more stable. So that is 3, then 2, then it's 1. After that, it's another one. Which of the following, yes, another thing. Which of the following can show conformational isomerism? For that, let me tell you this one. For conformational isomerism, there must be at least 3 sigma bonds without a pi bond. In continuity. There must be 3 sigma bonds in continuity without pi bond. Just a moment. Okay. You just write down. I will simply on my AC. It's very hot over here. Okay. Now have a look. What about this CH4? Have a look. It is like this. CH4 is like this. Now look towards this. This is one sigma bond. This is another sigma bond. Either this is the continuity or this and this. That means only 2 sigma bonds are in continuity. There are no 4 bonds. There are no 4 sigma bonds which are in continuity. There are no 3 bonds which are in continuity. There are only 2 bonds which are in continuity. Hence, it cannot show what we call conformational isomerism. What about this? It is HC triple bond C single bond H. Have a look. This is sigma, no doubt about that. This is also sigma, no doubt about that. But here are pi bonds as well as a sigma bond. Sigma bond should be without pi bond. So there are no 3 sigma bonds in continuity. So it will not show what we call conformational isomerism. What about this? It is like this. It is like this. Have a look. Have a look. This is one bond, this is second bond, this is third bond. That means 3 bonds are in continuity, which are sigma bonds. Similarly, after that, if I write down H, C, H, H, then O, then H, can I say this is also having 1 sigma, second sigma, third sigma without any pi? So yes. So 3 sigma bonds in continuity without any pi. Pi can be there, but after these 3 sigma bonds. Now, after that, have a look, have a look. If I write this one, C, H, 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 C, H, double bond C, H, H. Now have a look, have a look. This is 1 sigma, this is another sigma, this is another sigma. All are in continuity without pi bond. There is no pi bond here. There is no pi bond here. That means it can show. It can show. What about this? What about this? What about this? It is like this, C, H, H, double bond C, single bond H, single bond C, single bond H, double bond C, single bond H, single bond H. Have a look. It is this sigma, and this sigma. They are in continuity. They are in continuity. Hence, it can show. What about this? What about this? It is N, H, H, O, H. What about this? It can show like 1 sigma, another sigma, another sigma. It can show. What about NH2, NH2 hydrazine? What about this? What about hydrazine? Have a look. Have a look. Have a look. 1 sigma, another sigma, another sigma. All are in continuity. Hence, it can also show. I hope this is clear to each and every one. After that, minimum number of carbons required to show conformational isomerism for alkanes. For alkanes, how many? Minimum 2. Minimum 2. Have a look. Methane cannot show. Ethane can show. That means minimum 2 carbons are possible for alkane. But for any compound, we don't need any carbon because, have a look, it can show. It can show. NH2OH can show. But there is no carbon. Hydrazine can show. There is no carbon. So for any compound, no need of carbon is there. That means no need of carbon is there if we are talking about conformational isomerism. After that, beta, there are configurational isomerism, and we know configurational isomers are those stereoisomers which cannot be interconverted into one another by simple rotation. Now, these are of 2 types. One is geometrical isomerism, another is of what we call optical isomerism. So let's discuss geometrical isomerism first. What are geometrical isomers? These are those stereoisomers, or this is the stereoisomerism which arises because of restricted or hindered rotation about any 2 centers. That means, listen carefully. Listen carefully. Suppose if this is a center, this is a center. Among these 2 centers, listen carefully. Among these 2 centers, there should be restricted rotation. That means there should not be free rotation about these 2 centers. And when it is possible that there is not free rotation about 2 centers, it is possible if there is a double bond between these 2 centers, or if there is a triple bond between these 2 centers, or if there is a single bond but of a ring. If there is a single bond of a ring, at that time it is possible. So 2 centers should be either attached by means of a double bond, or by means of a triple bond, or by means of a single bond, but that single bond should be of a ring. At that time we can say 2 centers are joined together, but those 2 centers have what we call hindered or restricted rotation. I hope this is clear. So whenever this isomerism arises because of hindered or restricted rotation, we call that isomerism as what we call geometrical isomerism. But listen carefully, I will erase this now. But first thing is, there must be 2 centers where rotation is restricted or hindered. After that, each center, that means this center as well as this center must be, this must be two groups, this must be two groups. But these two groups should be different. Say for example, if this is A, this should be B. If this is A, this should be B. Similarly, listen carefully. Two centers should be there where rotation is restricted or hindered. After that, this center should be having two different groups. This center should be having two different groups. It's not like that these two should be having different groups. No. This center should be having two groups. This center should be having two groups, but these two groups are different. These two groups should be different. That means in total there should be four groups, and all these four groups, these two and these two, should be present. These should be present in same plane. These should be present in same plane. So first, there should be two centers where rotation is restricted or hindered. After that, each center should have two different groups. This center should have two different groups. This center should have two different groups. In nutshell, all these four groups should be what we call within the same plane. After that, there must be the areal distance between, say for example, A and A. Suppose if this distance is L1, then L1 can never be equal to L2. What is meant by that? Have a look. There should be two centers where rotation is restricted or hindered. After that, there must be two different groups, say for example A and B. Similarly, say for example B and A. That means two different groups. All these groups should be present in same plane. When compounds are like this. After that, this L1, that means distance between A and A, here is L1. Distance between A and A here is, let us suppose, L2. Listen carefully, this L1 can never be equal to L2. That means areal distance should be different. If all these conditions are fulfilled, then we can simply say such compounds show geometrical isomerism. So these are the conditions for geometrical isomerism, which is written over here. So there must be at least two centers about which rotation should be restricted or hindered, like this, like this. Then each center must have two groups. Two groups should be different but present within the same plane, and after that areal distance must be different. I hope this is clear. Now, geometrical in case of alkenes. We know in case of alkenes there is carbon-carbon double bond. That means first point is already fulfilled. After that, all the groups, say for example these two groups and these two groups, all these groups should be present within the same plane. They are already present within the same plane. That means in case of alkene, you have to check only groups. If here two groups are different, here two groups are different, then it can show GI. Similarly, in case of alkenes, you have to check only groups. If these two groups are different at one center, similarly groups are different at another center, it can show GI. Similarly, if two groups are different at one center and two groups are also different at another center, it can show GI. But if you are having an alkene in which this center is having different groups but this center is having similar group, it will not show GI. Or if it is having like this, it's having different group but this is having similar group, it will not show GI. In nutshell, each center must have different groups. So different here, different here. Like this, it can be same, but here it should be different, it should be different. Similarly, it should be different, it should be different. It should be different, it should be different. Or you can say like this. To this, it is A and B different. To this, it is A and B different. Similarly, A and B different. Here, A and B different. Now listen carefully. If you are having an alkene like this, in which, say for example, if I draw a line over here, an imaginary line over here, can I say this imaginary line divides the molecule into two equal halves such that from this side, A and A, identical groups are on same side across carbon-carbon double bond. BB, identical groups are on same side of carbon-carbon double bond. Whenever identical groups are on same side of carbon-carbon double bond, these two are identical, they are on one side. These two are identical, they are on another side. This type of isomerism, geometrical isomerism, is known as, this type of isomer, geometrical isomer, is known as cis isomer. Similarly, look towards this. Whenever identical groups are on opposite side, because this is one side, this is another side, A is here, A is here, that means A, both are identical, they are on opposite side. Similarly, B are on opposite side. We call this isomer as trans isomer. We call this as trans isomer. Remember, so cis and trans isomerism arises only if there are identical groups at two different centers. At two different centers, there are identical groups. When identical groups at two different centers are on the same side across carbon-carbon double bond, we call that as cis. And if identical groups are on opposite side, identical groups at two different centers or on opposite side across carbon-carbon double bond, we call that as trans isomer. But here we will use EZ isomerism. What is that? We will discuss that later. But these cannot show what we call geometrical isomerism. Similarly, this can show geometrical isomerism. Have a look. Here A at one center and A at another center or on same side across this. So this is also known as cis form. And here A at one center and A at another center, that means identical groups, or similarly B at this center and B at this center or opposite side across this carbon-carbon double bond, we can call this as trans isomer. So in nutshell, we can easily say cis and trans isomerism in alkenes. Whenever identical groups are present on same side across carbon-carbon double bond at two different centers, we call that isomer as a cis isomer, and that isomer in which, that geometrical isomer in which identical groups are present at two different centers but opposite together, opposite with respect to each other across carbon-carbon double bond, we call that as trans isomers. Suppose, for example, which type of isomerism shows this one? First of all, which type of isomer is this? Similarly, which type of isomer is this? This is cis isomer and this is trans isomer. Simple. Have a look. Cl at this carbon, Cl at this carbon, they are on same side, or hydrogen at this carbon or hydrogen at this carbon, they are on same side across carbon-carbon double bond, hence cis. What about this? What about this? Cl and Cl opposite, H and H opposite, hence trans. Similarly, if I write like this, H at this carbon and H at this carbon, they are on the same side across carbon-carbon double bond, so this is cis. Or CH3 at this carbon, CH3 at this carbon, identical groups are on same side, hence this is cis. Similarly, this is trans. HH, CH3, CH3, identical atoms or groups are on opposite side, so this is trans. So this is very easy. As per alkenes are concerned, we can easily say which one is cis, which one is trans, but there is another type of isomerism that is known as EZ isomerism that will be discussed after a few minutes. But is this clear till now? Is this clear till now? Let me know quickly. Is this clear till now? Is this clear till now? Let me know in the chats quick. Let me know in the chats quick, my dear lovely students, quick. Come on. Yes, that is quick. That is clear. That's clear. Great. God bless you. After that, we are having azo compounds. Now, what is meant by azo compound? Azo compound is this one. N double bond N. Now, look towards this. Say, for example, this is phenyl group. This is phenyl group over here. First of all, these two centers are having restricted rotation. This is having two groups. One is in the form of pH, another is in the form of lone pair. Whether I will show this lone pair or not, but lone pair is there. Similarly, lone pair is there. So these two are different groups, these two are different groups. So it can show GI. But remember, one of the groups is lone pair. Whenever lone pair acts as a group, we will never use cis and trans. We use syn and anti. Whenever lone pair acts as a group, we use syn and anti instead of cis and trans. What is meant by that? Have a look. Across this nitrogen-nitrogen double bond, tell me, identical groups, they are on same side, Hence this is syn, this is syn. Instead of cis, we use syn. Similarly, if I write down like this is pH and this is pH. Obviously, we know another is what we call a lone pair. Another group is in the form of a lone pair. Now tell me, pH, opposite side, lone pair, opposite side. So this should be trans, but as lone pair acts as a group, we will use NT over here. So one is syn, another is NT. Very, very, very simple. After that, my dear lovely students, it's oxime. Oxime is of two types. Have a look. Oxime is of two types. In oxime, once again, nitrogen acts as a lone pair. Oxime is of two types. One is that oxime in which carbon contains at least one hydrogen. That is known as aldoxime. That means, first of all, let's talk about aldoxymes. That means that oxime which has been obtained from aldehyde. So aldoxime. Now, different groups, restricted rotation, all groups within the same plane, and this is what we call, this shows geometrical isomerism. Now, have a look. Here you have to focus OH of nitrogen and H of, say, carbon. But that nitrogen and carbon which forms double bond. You have to check their position with respect to carbon double bond nitrogen. With respect to carbon double bond nitrogen, you have to check the position. Position of what? Position of H and OH. These are on the same side. Hence, this is syn. Why syn? Why not cis? Because lone pair will act as a group. Now, similarly, if I write like this, C double bond N, then it's OH. This is lone pair. This is CH3. This is H. Once again, this is an aldoxime. In aldoxime, we have to check the position of OH and position of H. Now, as they are what we call opposite with respect to each other or across carbon double bond nitrogen, they are opposite. Hence, this is what we call NT. So, this is very, very simple as per aldoxymes are concerned. But in case of ketoxymes, if we talk about ketoxymes, so this was about aldoxymes. About ketoxymes, what we have to remember is, listen carefully. First of all, how can we identify whether this is ketoxyme or aldoxyme? First of all, C double bond NOH should be there. If this C, which forms a double bond with nitrogen, does not contain any hydrogen like this, then it is ketoxyme. If it contains at least one hydrogen, then it is aldoxyme. Now, this is ketoxyme. Listen here. I will write down the name. Say, for example, the name of this compound is methyl phenyl ketoxyme. Listen carefully. In case of ketoxyme, we will write down the name methyl phenyl ketoxyme, or we can write down phenyl methyl ketoxyme. Phenyl methyl ketoxyme. Now, in case of ketoxyme, you have to check the name of the group which comes first. Name of the group which comes first is methyl. That means you have to check methyl. And the position of OH attached to nitrogen, that means this one. And the position of OH attached to nitrogen, that means this one. What is the position? That means the group which comes first in name. During naming, the group which comes first, its position and position of OH, they are opposite with respect to each other. That means its name becomes simply NT. So this is NT methyl phenyl ketoxyme. Or have a look. This phenyl comes first. If name is phenyl methyl ketoxyme, now I have to check what we call phenyl. I have to check phenyl. I have to check the position of phenyl and position of this group known as what we call OH. Position of phenyl and OH, they are on the same side, then this is known as syn. Phenyl methyl ketoxyme. So, in case of ketoxyme, check the name of the first group and OH. Name of the first group and OH. If first group and OH, they are opposite, then NT. If first group and OH, they are on the same side, then it is syn. I hope this is clear. After that, GI in cycloalkanes. Now listen carefully. there must be at least 2 sp3 hybridized carbon. There must be at least 2 sp3 hybridized carbons, to which, or we can simply say there must be at least 2 sp3 hybridized carbons, and each sp3 hybridized carbon must have 2 different groups. Must have 2 different groups. Remember this. If this condition is possible, at that time cycloalkane show GI, otherwise cycloalkane never shows GI. What is meant by this? Have a look. If you are having this one, this is the cyclopropane. Now, this is sp3, this is sp3, this is sp3. But this is having hydrogen and hydrogen, this is having hydrogen and hydrogen, this is having hydrogen and hydrogen. That means this sp3 is having 2 groups, but both are identical, both are same. This is having 2 groups, both are same. This is having 2 groups, both are same. That means there is no carbon which is having 2 different groups. This can never show GI. It can never show GI. But if I write down like this, now have a look. This is sp3 hybridized carbon. To this sp3 hybridized carbon, there are 2 different groups. Yes or no? But this sp3 hybridized carbon is having H and H. That means they are having similar group. This is having similar group. So it will also not show GI. What about this one? What about this one? There must be at least 2 sp3 hybridized carbons. So there are 2 sp3 hybridized carbons, and each sp3 carbon, that means this one is having 2 different groups, this one is having 2 different groups, hence it will show GI. So GI here is absent, GI here is absent, GI here is present. Now, a ring can be 3-membered, 4-membered, 5-membered, 6-membered, 7-membered, 8-membered. It can be any ring. Say for example, if I draw an 8-membered ring like this, and if I draw like this, have a look. If I draw like this, it is Cl. If I draw like this, it is Cl. Now tell me, can I say this sp3 center is having Cl and hidden hydrogen is also there? So let me draw hydrogen as well. So this is having 2 different groups. Similarly here, hydrogen is also there. So this is having also 2 different groups. So this can show GI because of this and this carbon. So there must be at least 2 sp3 hybridized carbons. There are 8 sp3 hybridized carbons, but we need those 2 hybridized sp3 hybridized carbons to which different groups should be attached. So it can show GI, it can show GI, it cannot show, it cannot show. I hope this is clear to this, everyone. Now, after that, GI in endocyclic double bonds in cycloalkenes. Listen carefully. That means we are talking about this one. This is cycloalkene. It's having a double bond within the ring. So this is endocyclic double bond. This is endocyclic double bond. Similarly, this is endocyclic double bond. Listen carefully. This is endocyclic double bond. This is endocyclic double bond. So up to 7-membered rings. Up to 7-membered rings. Remember, up to 7-membered rings. GI in endocyclic double bond. GI in endocyclic double bonds is absent. That means this cannot show GI, this cannot show GI, this cannot show GI as per double bond is concerned. As per double bond is concerned. As per double bond is concerned, it cannot show GI. Listen carefully. Listen carefully. As per double bond is concerned, it cannot show GI. Why? Because these all are cis forms. Their trans form is not possible. GI is possible only if cis and trans both are possible. But these compounds contain only cis form. Their trans form is absent. Hence, there can never be GI possible across carbon-carbon double bond. But if I talk about this, have a look. If I talk about this, double bond cannot show GI. But listen carefully, this double bond cannot show GI because this is the double bond, endocyclic double bond of 4-membered ring. 3-membered, 4-membered, 5-membered, 6-membered, 7-membered double bonds cannot show, I mean to say, GI. But is this sp3 hybridized carbon? Answer is yes. Is this sp3 hybridized carbon? Answer is yes. So this carbon sp3 is having two different groups. This is having two different groups. So because of this, GI is possible. In nutshell, this can show GI overall. This compound can show GI because of this, not because of double bond. I hope this is clear. So up to 7-membered rings, double bond cannot show GI, but 8-membered ring, 8-membered ring and onwards can show GI as per endocyclic double bonds are concerned. Why? As per double bonds are concerned. Why? Because, have a look, this is 8-membered ring. This is 8-membered ring. This form is cis form. And we can draw its transform as well. We can form its transform as well. This is 1, 2, 3, 4, 5, 6, 7, 8. So this is hydrogen. This is hydrogen. These are transform. This is transform. But this transform is not possible up to 7-membered ring. That is why this double bond can show cis and trans. That means 8-membered, 9-membered, 10-membered, 11-membered, 12-membered can show cis and trans across carbon-carbon double bond in case of cycloalkenes. But you have to note this one. From 8 to 11-membered rings, it is cis which is more stable than trans, because in case of trans ring there is little bit strain, but once ring becomes 12 or more than that, 12 or more, then it becomes trans which is more stable as compared to cis. Trans at that time is more stable as compared to cis. After that, GI in cumulines. First of all, what is meant by cumulene? Cumulines are those compounds in which pi bonds are present at adjacent positions. Say for example, this is the cumulene. This is the cumulene containing only carbon. Sometimes cumulene contains nitrogen. Sometimes cumulene contains oxygen. So this can be one of the examples of cumulene. But in this cumulene, there are even number of pi bonds. And remember, when cumulene contains even number of pi bonds, their groups, that means groups present at this center and this center, that means groups present at end center, they are always perpendicular. That means they are present in different plane. If they are perpendicular with respect to each other, our condition for GI is not fulfilled, because condition for GI should be that these groups and these groups all should be present within the same plane. So we can simply write down one line that GI in cumulines with even number of pi bonds is always absent. And what is the reason why it's always absent? Because such cumulines have groups at their end centers which are not within the same plane. Listen carefully. After that, if we are having cumulene with odd number of, say pi bonds, such bonds are present in same plane. Now, what you have to check is, you have to check only end center. If this end center is having different group and this end center is having different group, GI is present, otherwise GI is absent. Now, so can I write GI in cumulines? GI in cumulines with odd number of pi bonds can be present. It can be present. It is not always present. It can be present if, for that there is the condition. If each end center has different groups, if each end center has different groups, otherwise GI is absent. Otherwise GI is absent. Have a look. If I write down A over here, B over here, A over here, B over here, we can simply say GI is present. We can simply say GI is present. But if we write down once again a cumulene with odd number of pi bond, this is A, this is B, this is D, this is D. So we can say GI is absent. Because this should have different, this end center should have different groups. Here different groups are there, but this end center is not having different groups. Here groups should be different, here groups should be different. Similarly, if I write down C double bond, C double bond, C double bond, C, here it is D and D, here it is A and B. Once again, it cannot show GI because these groups are different, but these groups are similar. Similarly, if I write C double bond, C double bond, C double bond, C, here it is A and A, here it is B and B. It can also not show geometrical isomerism. So geometrical isomerism in case of cumulene with even number of pi bond, whether these groups are different, whether these groups are same, they're always absent. So GI in cumulene with even number of pi bond is always absent, but GI in cumulene with odd number can be possible, can be present if this end center have different group and this end center have different group. If this is having different group, this is having different group, GI is present, otherwise GI is always absent. Otherwise GI is always absent. I hope this is clear. After that, GI in spirons. What is meant by spiron? Spiron means series of spiro compounds. And what are spiro compounds? Bicyclic compounds in which one atom is common between two rings. Say for example, bicyclic compound in which one atom is common between two rings. For example, this one. This is the bicyclic compound and this is one atom which is common between two rings. But here end center is this center and this center. These are the end centers. Why? Because from this you can say a ring has been started and from this a ring has been ended. So remember, their centers, end centers have these two groups, but they are not present within the same plane. Once again, they are parallel. That means if spiro compound is such that it's having even number of rings, then GI is always absent. So I will write down GI is always absent. GI is always absent in spiro compounds. With even number of rings. That means this with even number of rings, GI absent. This with even number of rings, GI absent. But if you are having spiro compound with odd number of rings, remember, then all these groups are present in same plane. When these all are present in same plane, if this center is having different group, if this center is having different groups, then GI is present. That means here once again, like that of cumulene, GI in spiro compounds with odd number of rings, can be present if each end center has different groups. Otherwise GI is absent. Have a look. That means if these two are different, these two are similar, GI is absent. These two are similar, these two are different, GI is absent. These are similar, GI is absent. These are different, GI is present. I hope this is clear. After that, my dear lovely students, GI in substituted biphenyls. Have a look. First of all, This is one phenyl ring and this is another phenyl ring. So both are known as biphenyl rings. But if bulky groups are present at this position, this position, this position and this position, what will happen? Have a look. Suppose bulky groups are there. Say for example, it is G1, group 1, group 2, these are bulky, group 3 and group 4. These are the bulky rings, bulky groups. What will happen? These bulky groups will repel, their electron clouds will repel each other. That means steric repulsion will take place. When bulky groups are closer, steric repulsion will take place. So what will happen? This carbon-carbon bond will rotate. When carbon-carbon bond will rotate, now groups, few groups will become here and few in another plane. That means these groups become in now different plane. First they were present in same plane, so there will be repulsion. When rotation takes place, because to minimize this repulsion, this bond has to be rotated. Now groups are in different plane. When groups are in different plane, there is, no repulsion at all. Now when groups are in different plane, repulsion is minimized. That means molecule becomes stable, so it will never rotate once again to this position, because here it is unstable. So it will remain always like this. That means these two rings are always perpendicular. Two rings are always perpendicular. That means these groups are always perpendicular. If groups are always perpendicular, we can say GI is absent. GI is absent. Now, what about this? Is rotation here restricted? Answer is yes. Why? Because to minimize the repulsion, these rings are now perpendicular to each other. They will never rotate once again, because if they rotate from this position to this position, once again there will be repulsion. So there will be restricted rotation always between two rings. But as these two groups, these two planes, these two rings are perpendicular, hence this G3, G4 will be perpendicular to G1, G2. So there will be no, GI, because for GI, we know these centers where rotation is restricted, these centers must have this group and this group. Similarly, this should have this group and this group. All these four groups should be present within the same plane, but these groups are in one plane, these groups are in another plane, so there will be no GI at all. After that, GI in substituted terphenyls. Have a look. If we talk about once again phenyl rings, but terphenyl means three phenyl rings. 1, 2 and 3. And if these phenyl rings are having groups, say for example G1, say for example G2, say for example this is G3, say for example this is G4, suppose this is G3, suppose this is G4, suppose this is G1, suppose this is G2. Now listen carefully. If we talk about this center and this center, this center and this center, tell me, what is the rotation between these two? Restricted, and these two are perpendicular to each other. These two are perpendicular to each other. What about these two? These two are in same plane. These two rings will be in same plane, because these two are perpendicular, these two are perpendicular. Hence, these two are within the same plane. Now listen. If we talk about this center and this center, these two centers, rotation is restricted. Rotation is restricted because it cannot rotate. Because if it rotates, there will be more repulsion. So these two centers are restricted. These two centers are having restricted rotation. What about this? This group is like G1. This group is like G2. That means this is having two different groups. What about this one? G1 here, G2 here. That means this is also having two different groups. So this is having two different groups. This is having two different groups. Still, there is what we call restricted rotation. Hence, in this molecule, GI is present. GI is present in this molecule. So can I say this molecule shows isomerism? This molecule shows isomerism, but this molecule shows only isomerism if there is restricted rotation. And this restricted rotation is because of steric repulsion. So that isomerism which arises because of restricted or hindered rotation as the result of steric repulsion, that is known as atrope isomerism. That is known as atrope isomerism. So what is atrope isomerism? It is simply isomerism It is simply isomerism which arises due to restricted or hindered rotation. Due to restricted, or you can say hindered rotation, due to restricted rotation as a result of steric repulsion. Remember, so here GI is present only if there is what we call restricted rotation between these two centers, and this restricted rotation is possible only due to steric repulsion. Because of steric repulsion, these two rings are perpendicular, hence these are in what we call parallel with respect to each other. So that isomerism which arises due to restricted rotation or hindered rotation as a result of steric repulsion is known as trop isomerism. So here isomerism, geometrical isomerism, is because of what we call restricted rotation as a result of what we call steric repulsion. After that, which can show GI? Now tell me which among these can show GI. Very simple. This cannot show GI because of two similar groups. This is having two different groups, H and lone pair, two different groups, so this can show GI. What about this? This carbon-carbon double bond. Let me check first at carbon-carbon double bond and after that at ring. At ring, there are not, two sp3 hybridized carbons to which two different groups are attached. This is sp3 but HH similar, HH similar, HH similar, HH similar, HH similar. That means this ring cannot show. Now what about this double bond? Have a look. What about this double bond? Let me draw like this. Let me draw a line like this. Now, as per this carbon is concerned, H and CH3, there are two different groups at this carbon. But what about this carbon? At this carbon, this part of ring and this part of ring, they are identical, hence it cannot show GI. What about this? As per this double bond is concerned, have a look. These two are different and this ring part is different because this is having CH3 and this ring part is different. So we can say this double bond can show GI. But ring cannot show GI. In nutshell, one of the, centers, one of the position show GI, hence it can show GI. This double bond cannot show GI because of hydrogen and hydrogen, similar groups. But what about this carbon? This is having Cl and H. Similarly, this is having Cl and hidden hydrogen is there. So let me show that. This is sp3 hybridized carbon. This is sp3 hybridized carbon. Two sp3 hybridized carbon in a ring which contains two different groups. Here different groups. So this part, because of this part, it shows GI. What about this? Pi bond at adjacent positions. So this is cumulene. Cumulene with 1, 2, 3 pi bonds. That means this is cumulene with odd number of pi bonds. Cumulene with odd number of pi bonds, you have to check end centers. This end center is having HH, this end center is having HH, so it cannot show GI because end centers must have different groups. Have a look. This is a 6-membered ring. In this ring, endocyclic double bond is there. So 6-membered ring with endocyclic double bond cannot show GI at endocyclic double bond. But what about other part of the ring? Can I show GI? No, because for other part, you must have two sp3 center to which two different groups. To this center, two different groups should be there, or to this center, two different groups should be there, but there is no different group. Okay. Similarly, what about this? This is sp3 center, two different groups are there, but no other sp3 center is there which is having two different groups. That means this ring can also not show GI. But what about this double bond? What about this double bond? Have a look. This double bond can show GI. Why? Because to this double bond, this part and this part, they are two different parts. Similarly, this part is having Cl, this part is not having any Cl. That means these two are also different. Hence, it shows GI. What about this? This is 10-membered ring. Double bond at 10-membered ring can show GI. That means it can show GI. This cannot show GI, this double bond, because this cannot show GI because, have a look. Because this part is having Br, this part is having Br, that means these are two similar, this similarly, this and this, they are similar, so it cannot show GI. But this and this can show GI. How? Because it's having H and Br, two different groups. This is having H and Br, two different groups. sp3 center, two different groups. sp3 center, two different groups, and it's part of ring, hence it can show GI. Now, as per Spiro compound is concerned, this is having even number of amines rings, so it cannot show GI as per what we call Spiro compound is concerned. But if we look towards this ring, this center is sp3, this center is sp3. This is having I and H, this is having I and H. That means this part can show GI. As this part can show GI, hence overall molecule can show GI. I hope this is clear. I hope this is clear. So the minimum number of carbons required to show GI is 0. Minimum number of carbon required to show GI. Have a look. It can show GI. But there is no carbon in this. Okay. There is no carbon. Have a look. Have a look. There is no carbon. It can show the GI. There is no carbon in this. So it can show GI. It can show GI. So the answer is 0. As it can show GI, this is what we call syn form. You can make its anti-form as well if you write down like this. If you write down like this. Have a look. This is anti. This is its syn form. That means it can show GI. If it can show GI, it's not having any what we call carbon. So minimum number of carbons required to show GI is 0. After that, minimum number of carbons required to show GI in alkenes. Alkene means there must be only carbon and hydrogen. This is not alkene. Sometimes you write down like this and say only 2 carbons are there which can show GI. But this is not alkene. For alkene, you must know there must be only carbon and hydrogens. That means here it should be carbon and hydrogen. It should be carbon and hydrogen. So 1, 2, 3, 4. There must be at least 4 carbons. So there must be at least 4 carbons. This is cis form. You can form its trans form as well. Okay. GI in cycloalkanes. In cycloalkanes, number of carbons. In cycloalkanes, number of carbon. In cycloalkane, number of carbon. But listen, if I write down this is not cycloalkane. This is substituted cycloalkane, but we want basically, if question is only, that means substituted cycloalkane, and that substituent can be any group, that can be Cl, Br, then it is only 3 carbons. But if we want our cycloalkane such that it should be ring as well as there must be only carbon and hydrogen bonds, then 1, 2, 3, 4, 5, at least 5 carbons should be there. At least 5 carbons should be there. CH3 on the same side, so cis, you can form its trans as well. After that, minimum number of carbons required to show GI in cycloalkenes. This is cycloalkene. Cycloalkene. Minimum number of carbons required. But remember, cycloalkene should be such that it should be made up of only carbon and hydrogen. Then it can be like this. So minimum number can be 6. 1, 2, 3, 4, 5, 6. That means it can be 6. But it should be, cycloalkene should be made up of only carbon and hydrogens. Then it's 6. After that, it is EZ isomerism. Let me tell you, this E comes from a word, and that is a German word basically, which means entgegen, means across or opposite. It means across or opposite. Similarly, Z comes from a word which is once again a German word, means zusammen, means same side. That means what should be opposite and what should be same side? Identical priority groups. Identical priority groups. If identical priority groups are on the same side of what we call a center which can show GI, then we call that simply, if it is on same side, we call that as zusammen, that means Z, otherwise we call that as E. Let us discuss EZ isomerism in case of alkenes. But let me tell you, this E and Z name was given by a scientist, a chemist, that is known as Blackwood. It was given by Blackwood. But this priority can be say find out with the help of rule, and that rule is CIP rules. C means Kahn, Ingold and Prelog. These are three more scientists. Kahn, Ingold and Prelog. These form rules. With the help of these rules, we will find out, say priority. And after that, if identical priority, if 1, 1 is on the same side and 2, 2 is on the same side, then we will simply call such, say isomer as Z isomer. And if 1, 1 is opposite, 2, 2 is opposite, then we will call that isomer as what we call E isomer. Now, what are the rules? Rule number 1. Rule number 1 is, first rule is that priority of the groups which are basically attached to that center which can show GI is directly proportional to atomic number. It is directly proportional to atomic number. Priority of the groups which are directly attached to that center we show GI. So for example, if we talk about alkene, I will write down C double bond C. Then if I write down here, it's H, here it is Cl, here it is Br, here it is I. In this case, we cannot say whether it is cis, whether it is trans. For that, we modify Cis-Trans Isomerism in the form of Ez isomerism. And this Ez isomerism can be written over here. It can be written over, in case of cis-trans, we can use Ez as well. In case of syn-NT, you can use Ez as well. That means Ez can be used everywhere. But cis-trans cannot be used over here. Syn-NT cannot be used over here. For this, what we have to do is, we know these are the centers. This is the center at which GI is possible. This is the center at which GI is possible. Now, the groups attached to GI center, let's suppose, first of all, let's suppose this center. Let's suppose we are talking about this center. To this center, these two groups are attached. One group is Cl, another group is H, which is having atomic number highest. It is chlorine, so priority number 1, and this is having priority number 2. Similarly, if we talk about this one, this is having priority number 1 and this is having priority number 2. Now, have a look. If we talk about this carbon-carbon double bond, let me write, let me use another color. Now, if we talk about this carbon-carbon double bond, now tell me, first priority and first priority of one center and first priority of another center, identical priority of different centers, 2 and 2. That means 2 of this center, 2 of this center, they are on same side across carbon-carbon double bond. So we can simply call this as Z isomer. We call this as Z isomer. Similarly, if I take an example like this, H and Cl, then I and Br. Now have a look. This is 1 because at this center this is 1, at this center this is 2. At one center, 2 groups, 1, 2. At this center, this is 1, this is 2, because I is having more atomic number as compared to Br. Now, across this carbon-carbon double bond, tell me, 1 and 1 are opposite, 2 and 2 are opposite, so we will simply call it as E. So one is E, another is Z. So this is very easy. So this is very, very, very easy. Is this clear to you? Let me know in the chats. Is this clear to you? As this is very easy. Is this clear to you? Is this clear to you, my dear lovely students? Tell me. Is this clear? Is this clear? Yes. I will give you break. Give me 15 to 20 minutes maximum. I will finish this chapter and after that we will take a break. We will take a break after that. Now, is this clear? Let me know quickly. Okay, this is clear. Have a look. After that, we will be having another rule, that is rule number 2. If similar atoms of different groups, are attached to GI center, to GI center. If similar atoms of different groups are attached to GI center, then atom next to these atoms is considered. Atom next to these atoms is considered. Next to these atoms is considered till first point of difference. Till first point of difference is reached. Till first point of difference is reached. Then priority is given. Priority is given on the basis of atomic number. Basis of atomic number. That means priority is given according to rule number 1. What is meant by this? Have a look. If you are having C double bond C, then here it is CH3, here it is CH2CH3. Listen carefully. Suppose this is I, this is Cl. Now, have a look, my dear lovely students. Here to this center it is carbon which is attached to this, and here it is carbon which is attached to this. That means groups are different, but among these two different groups, similar atoms are attached to this GI center. Then what will we do? Have a look. Have a look. We will go to next atom. But which one is the next atom? Because this carbon and carbon, they are similar. Next atom will be hydrogen, hydrogen and hydrogen here. Because all are identical. But here, all are not identical. Two are hydrogens, one is carbon. Atom. It's not CH3 is not an atom. Atom is carbon which is attached to this. To this carbon, there are two hydrogens and one carbon. Among two hydrogens and one carbon, which is having highest atomic number? Write that first. That is carbon. After that, hydrogen and hydrogen. Now compare. Compare this first with this first. They are different. If point of difference is there, now use rule number 1. That means give priority to them according to, on the basis of atomic number. We know this is carbon, this is hydrogen. Carbon is having highest atomic number. So this is 1. Hydrogen is having lowest atomic number. This is 2. This is I, 1 and Cl is 2. 1, 1 on opposite side, 2, 2 is on opposite side. So we can simply say this is E. Similarly, my dear lovely students, have a look. C double bond C. Here let me write down C. After that it is CCl3. Here it is C. Then it is CCl2 and F. Listen carefully. Here it is C. Then it is Br3. Here it is C. Then it is Br2 and Cl. Now listen. We have to give priority to these, but this carbon and carbon are same. Groups are different, but these are same. After that, next atom is Cl, Cl and Cl. But here next atom is Cl, Cl and F. But what will be that atom which is having highest atomic number? It is Cl. So I will write down Cl, then F. It's not FCl, because among these atomic number is highest of Cl. Now compare these two. Cl and Cl, same. Go to next atom, Cl and Cl, same. Go to next atom, it is Cl and F. That means we have to compare next atom till first point of difference is reached. Now first point of difference has been reached. This is Cl, this is F. This is having highest atomic number as compared to this. So this will become 1, this will become 2. Similarly, what about this? Carbon and carbon, similar atoms or groups of different groups. Similar atoms of different groups are attached to GI center. Here, Br and Br are other atoms. What about this? Here it is Br and Cl. Now compare one by one. Br and Br, same atoms. Br and Br, same atoms. Br and Cl, different atom. That means first point of difference has been reached. Now, this is Br, this is Cl. Highest atomic number, lowest atomic number. So, this part will become 1, this part will become 2. 2, 2 on the same side, 1, 1 on the same side. So, this is Z. So, I hope this is very easy. This is easy. Another is rule number 3. If different isotopes are attached, remember, if isotopes are attached to GI center, then as we know isotopes have same atomic number, then priority is based on mass number, then priority is directly proportional to mass number. That means that group whose mass number is more is given more priority. Say for example, simple, C double bond C, this is H, this is D, isotopes are there. This is I, this is Br. These are not isotopes. These are not isotopes. If these are not isotopes, use rule number 1, atomic number. This is 1, this is 2. But these cannot be separated with the help of atomic number, so use mass number. We know deuterium is having highest mass number as compared to hydrogen. So 1, 1 on opposite side, 2, 2 on opposite side. So this is simply E. Similarly, this is C, double bond C, this is H, this is D, this is, I mean to say, Br, this is I. Very, very simple. Deuterium is having highest mass number as compared to protium, so 1 and 2. This is having 1, this is having 2, but this 1, 2 is based on mass number, this 1, 2 is based on atomic number. So 1, 1, 2, 2 on the same side, so this is Z. So I hope this is very easy. After that, we will be having rule number 4. Rule number 4, if groups attached to GI center contains double bond or a triple bond, then each center, or we can simply say then each atom of a double bond is duplicated and each atom of a triple bond is triplicated. What is meant by this? For example, you are having an example like this, C double bond C, single bond C double bond OH, and you are having C triple bond N, and then this is I, this is Br. Now have a look. This is the GI center to which this group is attached, and this group already contains double bond, and this group already contains triple bond. Then what to do? You have to duplicate this and you have to triplicate this. How to duplicate and how to triplicate? Have a look. First of all, I will write down this part as it is. Because there is no double bond or triple bond from this side. Now, from this side, what will we do is like this. First of all, we will draw single bonds. Only. Now, I will mark those atoms which form double bond. Now tell me, this carbon and oxygen form double bond. If I form single bond between carbon and oxygen, tell me, can I say carbon and oxygen forms two bonds, but in this carbon and oxygen forms only one bond? That means one bond of carbon is less, one bond of oxygen is less. So I will form one single bond of carbon, I will form one single bond of oxygen. But carbon forms two bonds over here with oxygen. This is one single bond, I will form another single bond with another oxygen. Similarly, oxygen forms two bonds with carbon, but here oxygen forms only one bond with carbon. I will add one more carbon over here. That means carbon has been duplicated, oxygen has been duplicated. But these two were original atoms. That means this carbon and oxygen were originally present. But this carbon and this oxygen were not originally presented. We have added them. These are known as phantom atoms. These are phantom atoms. So this is phantom atom. This is also phantom atom. Now, we know carbon can form four bonds. Here it is only one bond. Add three hydrogens to satisfy the valency. Similarly, we know oxygen can form two bonds. Here it is only one bond. Add one hydrogen to satisfy the valency. So in this way, you can duplicate both carbon and oxygen. But here carbon and nitrogen forms three bonds. So let me write down first that these form three bonds. Among three bonds, I will show only one. I will show only one, and I will mark this carbon and this nitrogen. We know carbon and nitrogen forms 3 bonds, but in this case, they form only 1 bond. That means carbon is having 2 bonds lesser. So as carbon is having 2 bonds lesser, form 2 single bonds. Similarly, nitrogen is having 2 bonds lesser, form 2 single bonds. But carbon forms 3 bonds with nitrogen. Now carbon form only 1 bond with nitrogen. That means these 2 bonds should also be formed with nitrogen. That means nitrogen has been triplicated. Similarly, nitrogen forms 3 bonds with carbon. Here, nitrogen forms 1 bond with carbon. That means these 2 bonds should also be formed with carbon. That means, once again, 1, 2, 3 carbon. Carbon has been triplicated. 1, 2, 3 nitrogen. Nitrogen has been triplicated. Now, satisfy the valency. Nitrogen forms 3 bonds. Here it's only 1 bond. So add 2 hydrogens. Carbon forms 1 bond, but it can form 4 bonds. So add 3 hydrogens. So these are phantom atoms which we add, and these are the real atoms which are already present. Now have a look. This is the carbon which is attached to this the GI center. This is the carbon which is attached to GI center. Now both these atoms are same. Now we have to go to next atom. Which one is the next atom? It is oxygen, hydrogen and oxygen. But oxygen, hydrogen and oxygen, we have to write down first. That atom which is having highest atomic number, that means 1 oxygen. After that, another oxygen. After that, I will write down hydrogen. What about this one? This carbon is attached with nitrogen, nitrogen and nitrogen. So I will write down here. It is N, N and N. Now compare one by one. This is oxygen. This is nitrogen. So this is having highest atomic number as compared to this. And this part is this one. That means this is having highest atomic number as compared to this one. Similarly, this is 1, this is 2. So have a look, 1, 1 on the same side, 2, 2 on the same side. So this is Z. In nutshell, let me write down over here. In nutshell, remember, whenever you are having a triple bond between 2 atoms, say for example A and B, and if same atoms are having double bond, and if same atoms are having single bond, then priority will be like this. Priority will be like this. Triple bond got preference over double bond got preference over single bond. But if, for example, if you are having carbon-carbon triple bond, say for example, I will not satisfy the valency, then it will got preference over carbon-carbon double bond, it will got preference over carbon-carbon triple bond. But my dear lovely students, if you are having carbon-carbon triple bond, then you are having carbon-carbon, carbon double bond oxygen. One is having triple bond, another is having double bond. But here, as we know, this is oxygen. So it will got preference over this one. Similarly, if you are having carbon-carbon triple bond and you are having carbon double bond nitrogen, it will got preference. Similarly, if you are having carbon-carbon triple bond and you are having carbon-carbon triple bond nitrogen, once again triple bond nitrogen will got preference. If you are having carbon double bond oxygen and you are having carbon double bond nitrogen, double bond will got preference. So no need to duplicate or triplicate always, because you should remember these things as well. Now after that there are few compounds and you have to tell me which one is E and which one is Z. Have a look. Very, very simple. To this carbon, there is chlorine and fluorine. So chlorine is 1, fluorine is 2. To this carbon, bromine is 1, hydrogen is 2. So across this carbon-carbon double bond, 1, 1 is on same side, 2, 2 is on same side. So this is Z. This is Z. Now, what about this? We know this is syn. But we do not have to say whether it is syn or NT. We have to say whether it is E or Z. Now, this nitrogen is having hydrogen and lone pair. Lone pair got always lowest priority. So this is 2, this is 1. This is 1, lone pair got lowest priority, so 2. 1, 1 on same side, 2, 2 on same side across this nitrogen double bond. So it is simply Z. Similarly, my dear lovely students, this is lone pair. Lone pair got lower number, so it is 2. So across carbon double bond nitrogen, 1 and 2 are here. This is 1, this is 2. So 1, 1 opposite, 2, 2 opposite. So my dear lovely students, it's E. What about this beta? It is cis. But we do not have to say that whether it is cis or trans. We have to check which one is, say E, which one is Z. So across this, at this carbon, CH3 is 1, H is 2. Across this, CH3 is 1 and H is 2. So 1, 1 and 2, 2. So it is simply Z. It is simply Z. What about this one? What about this one? What about this one? On below the plane, it is 1. Above the plane, it is 2. Below the plane, it is 1. Above the plane, it is 2. That means below the plane, same side 1, 1. Above the plane, same side 2, 2. So it is Z. What about this? This carbon double bond carbon, it's carbon triple bond carbon. Triple bond will got preference over double bond. So 1 and 2. This is 1, this is 2. 1, 1 opposite, 2, 2 opposite. So it is E. And I want answer of this, this, this and this from your side. And let me tell you that this is E and this is Z. But you have to answer me this. You have to try this. This is Z. This is also Z. This is E, this is E. After that, this will be having 1, this is 2. This will be having 1, this is 2. 1, 1 opposite, 2, 2 opposite, this is E. But I want 7, 8, 9, 10. You should try and you will check whether this is correct or not. After that, calculation of GI. Remember, if molecule is unsymmetrical, if molecule is unsymmetrical, at that time, number of GI is equal to 2 raised to the power n. Remember this formula. This is point number 1. Point number 2. If molecule is symmetrical, my dear lovely students, listen carefully. If molecule is symmetrical, at that time, number of GI is equal to 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Now the question is, what is p? P is n by 2. P is n plus 1 by 2. Now it is n by 2 if n is even. And it is n plus 1 by 2 if n is odd. Now the question is, what is n? N means number of GI areas. N means number of GI areas. Now, let's use these over here. Here, this is cumulene with even number of pi bonds, so there is no GI, so no, geometrical isomer is possible for this. But from this center, this is the end center, and this is the end center of cumulene containing odd number of pi bonds. This is having H and CH3. This is having H and CH3. That means this becomes GI area. So this becomes GI area. That means here n is equal to 1. Whenever n is equal to 1, no need to write down the formula. Directly, you just write down answer. That means number of GI is equal to 1, is equal to 2. Now, here, this is one GI area. This is another GI area. This is another GI area. That means n is equal to 3. But molecule is, you can divide this molecule into 2 equal halves. That means molecule is symmetrical. Molecule is symmetrical. Now, if molecule is symmetrical, you can use simply number of GI formula, and formula is simply 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Here, as n is 3, that means n is odd, so p is equal to n plus 1 divided by 2, which means it is 3 plus 1 is 4, 4 divided by 2, answer is 2. So p is 2, n is 3. Now use this formula. It becomes 2 raised to the power 3 minus 1 plus 2 raised to the power 2 minus 1. So it is equal to 2 raised to the power 2 plus 2 raised to the power 1. Answer is 4 plus 2, answer is 6. So here it's 6. Similarly, this is one GI area, this is another GI area, this is another GI area, that means n is equal to 3. But remember beta, this is unsymmetrical. As this is unsymmetrical molecule, number of GI is simply 2 raised to the power n, which means 2 raised to the power 3. Answer is 8. Now listen carefully. This double bond cannot show GI, but GI is possible because of this. So here, this is the GI area. GI area is only 1. Therefore, number of GI, no need to write down formula. Number of GI is 2. One will be E, another will be Z. Now, here GI is possible because it's 8-membered ring, double bond, endocyclic double bond in 8-membered ring. GI is possible. Here GI is possible, here GI is possible. That means this is the one area, another area, another area. This is another area. Here GI is not possible. From this and this position, sp3, to which this group and H is attached, this group and H is attached, that means this is another area. That means this is one area, second area, third area, fourth area, and fifth area. That means here N is equal to 5. But molecule is unsymmetrical. Molecule is unsymmetrical. So number of GI is equal to 2 raised to the power n, means 2 raised to the power 5. So it is 2 raised power 2 is 4, 2 raised to the power 2 is 8, raised to the power 2 is 16, raised to the power 2. That means 2 raised power 3 is 32. 2 raised power 2 is 4, 2 raised power 3 is 8, 2 raised power 4 is 16, and 2 raised power 5 is 32. After that, differentiation between cis and trans on the basis of physical properties. Listen carefully. When we talk about cis and trans molecules in general are considered more symmetrical. When trans molecules are more symmetrical, that means during their crystal lattice, there will be more close packing. More close packing, more force of attraction, more melting point. So remember, trans in general is having more melting point as compared to cis. Now, what about density? We know density is mass per unit volume. When we talk about cis and trans of the same compound, that means their mass is same, but volume is different. Trans molecules are more closely packed, that means volume is less. Volume is less, density is more. That means it is once again trans greater than cis. Trans greater than cis. After that, lattice energy. Now, tell me, if you are having a crystal lattice of trans, crystal lattice of cis, which one is easy to break? Now, it is basically cis which is easy to break. For trans, you need much more energy. That means lattice energy of trans is more than what we call cis. So it will be like that, trans greater than cis. After that, in general, trans molecules, say for example, this is a trans molecule. In general, this is the trans molecule. Now have a look. Positive to negative, that means trans molecules dipole moment will be simply subtracted in general. There are few molecules where in case of amine, say trans molecule dipole moment is more, but in general trans molecules have lesser dipole moment, or it can have zero dipole moment as well. So we can simply say cis is having more dipole moment than trans. But if cis is having more dipole moment than trans, that means cis is more polar. Cis is more polar but having lesser force of attraction, hence its solubility will be also more. Now, this will be the answer. After that, my dear lovely students, what about boiling point? As cis molecules are more polar means there will be more boiling point simply. So it is cis which is having more boiling point than trans. I hope this is clear to each and every one. There. So this was all about, geometrical isomerism. Now, next part of stereoisomerism is actually optical isomerism. But let me tell you, my dear lovely students, optical isomerism is basically part of 12th organic chemistry. So optical isomerism will be discussed in 12th organic chemistry. Now, the last part of today's session is hydrocarbons, but let's take hydrocarbon. We will discuss hydrocarbon exactly at 6 p.m. So there will be a break till 6 p.m. let's discuss hydrocarbons exactly at 6 p.m. Till then, you can have some food, you can rest a little bit. So we'll meet once again exactly at 6 p.m. But I would want each and everyone among you to be present at 6 p.m. So till then, take care. Bye-bye. See you at 6 p.m. Love you all. Love you all. Love you all. Take care. Take care. Take care. So we'll meet exactly at 6 p.m. So be here exactly at 6 p.m. So I welcome you once again to this wonderful channel. Now, let me know in the chats. Good evening, good evening. Let me know in the chats if I'm audible and visible to each and every one. Let me know quickly so that we will move ahead and we'll start our next chapter, that is very, very, very important chapter of organic chemistry, and that is hydrocarbon. Am I audible and visible? Let me know quickly. Let me know quickly. Am I audible and visible? Come on, my dear lovely students. Let me know quickly. Okay, that's great. That is great. Now, are you ready for this chapter? Are you ready for this chapter? So, should we start this chapter? Are you ready for this? Yes or no? Let me know quickly. Let me know quickly. Are you ready for this chapter? Are you ready for this chapter? Let me know quickly. How is the Josh? How is the Josh? How is the Josh for this chapter? How is your Josh for this chapter? So should we start this chapter? Come on, let me know quickly. Let me know quickly in the chats. Josh is high. That's good. Okay. So let's get started. Let's get started. Our first reaction over here is its methods of preparation of alkanes. That means how can we prepare alkanes? Number first preparation is from unsaturated hydrocarbons. This is unsaturated hydrocarbon. Unsaturated hydrocarbon. So have a look. It's unsaturated hydrocarbons. Now, say for example, you are having an alkene, and with the help of alkene, we have to prepare alkane. We have to prepare alkane. Have a look. What we have to do is, we have to simply add hydrogen. That means this is hydrogenation simply. That means we have to break this pi bond and we have to add hydrogen and hydrogen over here. That means this is hydrogenation. So remember, from unsaturated hydrocarbon, that means from alkenes and alkynes, we can prepare alkane by hydrogenation. Or we can say by reduction, because hydrogenation or addition of hydrogen means reduction. But this hydrogenation or reduction takes place in presence of a catalyst, and catalysts generally used are either platinum or palladium or Raney nickel. But you can use ordinary nickel as well, but at high temperature of about 523 to 573 Kelvin. And you can convert alkenes to alkanes. So alkanes can be prepared from alkenes by catalytic hydrogenation. Similarly, alkanes can be prepared from alkynes as well. Can be prepared from alkynes as well by once again hydrogenation. That means by using H2 in presence of catalysts like platinum, palladium or Raney nickel. Or instead of Raney nickel, you can use nickel, ordinary nickel, but at high temperature, approximately 523 to 573 Kelvin. Then you will get alkane. But remember, when alkane is obtained from alkene, we need 1 mole of, hydrogen. But if you want to convert 1 mole of alkyne to 1 mole of alkane, you need 2 moles of hydrogen. Here you have to break 2 pi bonds and you have to add 2 hydrogens over here, 2 hydrogens over here. And remember, this is the reaction basically. Now, listen carefully. Hydrogenation of alkene to alkane by using nickel at high temperature, or hydrogenation of alkyne to alkane by using nickel at high temperature, this reaction is known as Sabatier-Senderon's reaction. So let me write down over here. Reaction is Sabatier-Senderon's. So what is Sabatier-Senderon's reaction? Let me write down over here. Sabatier-Senderon's reaction is actually hydrogenation of unsaturated hydrocarbons in presence of nickel at high temperature, in presence of nickel at approximately 523 to 573 Kelvin temperature. This is point number one. Point number second, remember, you must know this, that hydrogenation reaction is used to manufacture वनस्पति ghee from edible vegetable oils. Point number third, this reaction, that means hydrogenation, is an example of syn addition reaction. It's an example of syn addition reaction. That means hydrogens will be added across carbon-carbon double bond or carbon-carbon triple bond from the same side. That means if this hydrogen is added above the plane, this will be also added above the plane. So all these hydrogens will be added from the same side. And reaction takes place, this reaction takes place via a four-membered cyclic transition state. Just remember this. It's a very, very easy reaction, very simple reaction. Whenever you are having an alkene or alkyne, just break the pi bond and add, instead of one pi bond, add one hydrogen to both, these, one hydrogen to this, one hydrogen to this carbon. Similarly, if you break two pi bonds between two carbons, then add two hydrogen on one carbon, two hydrogen on another carbon. Very, very simple reaction. After this, my dear lovely students, there is another reaction with the help of which you can prepare alkanes. But you can prepare alkane from alkyl halides. How? By reduction of alkyl halide to alkane. Have a look. If you are having an alkyl halide, you can convert this alkyl halide to alkane. That means what you have to do is you have to replace this X by H. But the reagents used over here are reducing agents like zinc or active metal in acidic medium, say for example in HCl, or active metal in acetic acid. Similarly, metal, say for example zinc copper, we call this as zinc copper couple in alcohol. Here alcohol will act as an acid, or it can also take place in basic medium. You can use reducing agent like HI in presence of red phosphorus as well. You can use hydrogen in presence of a catalyst. Generally, a better catalyst is palladium with small amounts of carbon. What you have to do is you have to simply replace X by hydrogen. So with the help of these, you can convert alkyl halide to corresponding alkane. After that, next is reaction with metals, reaction with magnesium. Have a look. Whenever you are having an alkyl halide and if it is treated with magnesium, remember, whenever magnesium reacts with CX bond, Magnesium is incorporated between CX bond. Reaction generally takes place in presence of dry ether. So we will get RMgX. This is known as alkyl magnesium halide, and this alkyl magnesium halide is one of the examples of organometallic compound known as Grignard's reagent. And in this Grignard's reagent, this is negative part, this is positive part. Now, whenever this Grignard's reagent comes in contact with water, or any other compound which can donate H positive, that means any acidic hydrogen containing compound, then what will happen? This H positive will be abstracted by this negative part. That means this will act as a base and this is acid. Normal acid-base reaction will take place and it results in the formation of RH, means alkane. R minus will abstract this H, so alkane will be obtained. Remember this reaction in which Grignard reagent is treated with any acidic hydrogen containing compound, say for example water. This reaction is known as, and resulting in the formation of alkane, this reaction is known as Zeri-Vetanov's reaction. This is known as Zeri-Vetanov's reaction. So first we will react alkyl halide with magnesium, resulting in the formation of Grignard reagent, and if we want to prepare alkane, then Grignard reagent has to react with any acidic hydrogen containing compound, for example water, so that normal acid-base reaction takes place and we will get alkane. After that, reaction with sodium. Let me tell you, reaction of alkyl halide with sodium is known as Wurtz reaction. This is known as Wurtz reaction. And remember, my dear lovely students, Wurtz reaction can be either intermolecular, it can be either intramolecular. And intermolecular can be of two types. One is simple or self. Another is mixed or crossed. Now, say for example, you are having an alkyl halide like this. And if it is treated with sodium, now what we have to do is, listen carefully. Whenever CX bond is there and reaction is with sodium in presence of dry ether, what we have to do is, we have to simply break this CX bond and we have to form radical at carbon to which X is attached. After that, normal combination or coupling will take place and it will result in the formation of RR. So it will result in the formation of R radical will combine with R radical, it will result in the formation of RR. This reaction of alkyl halide with sodium in presence of dry ether resulting in the formation of alkane is known as Wurtz reaction. Now, this reaction can also be written like this. If we are having alkyl halide, we are having sodium and we are having alkyl halide. But suppose alkyl halide is of only one type, then we can call this Wurtz reaction as simply simple or self intermolecular Wurtz reaction. Have a look. This will break, R radical will be formed. This will break, R radical will be formed. R radical, both are identical radicals. They will combine and result in the formation of RR. Side product will be Na positive X minus, that means twice NaX. So this is basically whenever alkyl halide is only of one type, reacts with sodium, resulting in the formation of, alkane in presence of dry ether. This is simply known as self or simple intermolecular Wurtz reaction. But simple example of this is, for example, if you are having simple example, CH3Cl, this on treatment with sodium in presence of dry ether, what will happen? Just break this bond, form a radical on carbon to which this halogen is attached. So it is CH3 radical. Now combine CH3 radical with another CH3 radical. So it will result in the formation of CH3, that means an alkane. That means that alkane is obtained which is dimer of this radical. Whatever alkyl part is there, dimer of that will be formed in this fashion if reaction is simple intermolecular Wurtz reaction. After that, my dear lovely students, if reaction takes place like this, that we are having different alkyl halides. Say for example, one is having Rx, another is R prime X, and now they react with sodium in presence of dry ether. Then what will happen? Let's assume that R is not equal to R prime. Let's assume R is not equal to R prime. That means at that time different alkyl halides are reacted together in presence of, say dry ether with sodium. Now this will be, this bond will be broken and R radical will be formed. Similarly here bond will be broken and R prime radical will be formed. Now two different radicals are there. When two different radicals are there, there are three possibilities of combination. Number one, this R can react with another similar type of radical, so it will result in the formation of RR. So this is an alkane which is obtained by combination of similar type of radical. Similarly, this radical can combine with another similar type of radical and it will result in the formation of RR prime, R prime, R prime. But another possibility is that these two different radicals will combine together and they will result in the formation of this one. But remember, the alkane which is obtained by combination of two different type of radicals is always minor product as per Wurtz reaction is concerned. So this is always minor. This is always minor product. Now the question is, here intermolecular Wurtz reaction takes place, but between two different alkyl halides. This is known as mixed or what we call crossed intermolecular intermolecular Wurtz reaction. For example, if we take an example of this one, CH3, then what we call CH2Br, and then it is CH3Br. Then what will happen? What will happen? Have a look. In presence of dry ether, they react with, sodium, and what will be the product over here? This bond will be broken and it will result in the formation of CH3 radical. This bond will be broken, it will result in the formation of CH3-CH2 radical. Now two different radicals are there, so three possibilities are there. This radical, ethyl radical, can combine with another ethyl radical, so we will get butane. We will get butane. One of the alkanes is butane. Another CH3 radical can combine with CH3 radical. That means we will get ethane, another product. And another product can be that methyl and ethyl radicals will combine together. Then they will result in the formation of CH3, CH2, CH3. But remember, this will be minor product. Why minor? Because this alkane has been formed by combination of different radicals. Listen carefully. This alkane containing even number of carbon is known as symmetrical alkane. This alkane with even number of carbon is known as symmetrical alkane. This alkane with odd number of carbon is known as unsymmetrical alkane. During Wurtz reaction, during this reaction, this and this all are present in the mixture. That means these all are impure. They cannot be separated from each other as their boiling points are almost same. So there is very less difference between their boiling points, so they cannot be separated by fractional distillation. Hence, this butane, ethane and propane, they are all present within the mixture. That means they are present in impure form. But we can prepare this butane in pure form with the help of Wurtz reaction. How? If we combine, have a look. If we combine ethyl bromide with ethyl bromide, we will get this. If we combine in pure form, if we combine methyl bromide with methyl bromide, we will get ethane in pure form. But this can never be formed in pure form. Whenever this is formed, it will be always formed in mixture. That means that alkane, which is obtained by combination of two different radicals, is always formed only in mixture, that can never be prepared in pure form during Wurtz reaction. That means, can we say this can be prepared in pure form? This can be prepared in pure form. That means Wurtz reaction is considered as better method to prepare symmetrical alkanes. It is not better method to prepare unsymmetrical alkane or that alkane which is obtained by combination of two different what we call radicals. So let me write down over here. Limitations of Wurtz reaction. Limitations of Wurtz reaction. Limitation number one is that during normal Wurtz reaction, during normal Wurtz reaction, that means during combination reaction, I mean to say, methane cannot be obtained. Methane cannot be obtained. This is first limitation. Number second, unsymmetrical alkanes or alkanes which are obtained by combination of different radicals, can never be obtained in pure form during Wurtz reaction. Point number third, tertiary alkyl halides. Remember this as well. Tertiary alkyl halides do not react during Wurtz reaction. These are the three important limitations you should remember. And very important point, if unsymmetrical alkanes or alkanes which can be obtained by combination of different radicals cannot be obtained in pure form, that means this reaction, I mean say Wurtz reaction, remember this point as well. Wurtz reaction is considered as best method to prepare symmetrical alkanes, or we can say alkanes which are obtained by combination of same or similar radicals or identical radicals, combination of same radicals. So this is considered as best method to prepare symmetrical alkanes or alkanes which are obtained by combination of same radicals or similar radicals or identical radicals. Now after that, we will be having another, that is intramolecular Wurtz reaction. In that, what will happen? Have a look. Say for example, you are having more than one CX bond, say for example like this. And if it is treated with sodium in presence of dry ether, what will happen? This bond will be broken. Now, it will result in the formation of a diradical. Now, this radical and this radical, they will combine together and they will result in the formation of a bicyclic compound like this. And side product will be NABR, obviously. So this takes place within the same compound. That's why this is known as intramolecular Wurtz reaction. So Wurtz reaction is simply reaction of alkyl halide with sodium resulting in the formation of alkane. After that, my dear lovely students, next reaction is reaction with zinc. Remember, whenever alkyl halide reacts with zinc, it basically results in the formation of R2Zn. This R2Zn is known as Frankland's reagent. Now, once Frankland's reagent is obtained, this on treatment with once again an alkyl halide, this R will act as a nucleophile and it will attack this, X minus will lose. That means it will simply perform a normal SN2 reaction and it will result in the formation of RR, that means a symmetrical alkane. Or simply, you can simply remember this with the help of this trick. Whenever alkyl halide is there, zinc is there. Remember, zinc and CX bond, when they are together, break CX bond, form a radical. This is not the mechanism, this is the trick. Form a radical and then combine this with another similar type of radical. So you will get alkane of same type. That means symmetrical alkane is also obtained with the help of this reaction. And this reaction is known as Frank-Land's reaction. So this reaction is known as Frank-Land's reaction. This is known as Frank-Land's reaction. After this, reaction with Gilman's reagent. What is meant by Gilman's reagent? Gilman's reagent is actually lithium dialkyl cuprate. Lithium dialkyl cuprate. Now have a look. This is lithium dialkyl cuprate. When this is treated with Rx, let us suppose this R is different or this is similar depending upon the value. It may be different from this R, it may be same as compared to this R. When this is treated with this Gilman's reagent is treated, this lithium dialkyl cuprate is treated with alkyl halide, a normal SN2 reaction will take place. That means this R acting as R minus will act as a nucleophile, it will attack and X will be lost. Now, it will result in the formation of RR prime. That means an alkane plus RCU plus this Li and X, that means LiX. Now, this can be either symmetrical or it can be unsymmetrical alkane. That means with the help of this reaction, we can prepare symmetrical alkane in pure form as well as unsymmetrical alkane can be also prepared during this reaction in pure form because this alkane can be easily separated from RCU and LiX. So this reaction is known as Corey's-Haas reaction. So this is Corey-Haas reaction. So we can simply say Corey-Haas reaction is better method to prepare unsymmetrical alkane as compared to Wurtz's reaction or as compared to Frank-Land's reaction, because Wurtz's reaction or Frank-Land's reaction is not the best method to prepare unsymmetrical alkane. So if you have to prepare unsymmetrical alkane, remember it's this Corey-Haas reaction which is preferred over Wurtz's reaction or what we call Frank-Land's reaction. After that, my dear lovely students, reaction of alkyl halide, that means this Rx, with metal hydrides. Now listen carefully. One metal hydride is lithium aluminium hydride. You can also write that as LaH. Second metal hydride is NaBH4, known as sodium borohydride. You can write down that as SBH. Another metal hydride is triphenyl tin hydride. So with the help of these, simply replace X and you can introduce H there. So alkyl halide can be converted to alkane with the help of these metal hydrides. But what you have to remember is that if alkyl halide is primary alkyl halide on treatment with SBH, that means sodium borohydride, cannot produce alkane. That means if you want to convert alkyl halide to alkane by using sodium borohydride, it should be either secondary alkyl halide or tertiary alkyl halide. This is point number one. Point number second, tertiary alkyl halide. For example, this one, CH3C, CH3 and X. If it is treated with, say lithium aluminium hydride, that means LiAlH4 or LaH, then remember, no alkane is obtained. No alkane is formed. Instead of that, alkene is obtained. And that alkene is simply like this. Let me draw the structure over here. CH2 double bond C, CH3, CH3. So from this type of alkyl halide, this alkene is obtained. Alkane cannot be obtained. That means if you want to convert alkyl halide to alkane by using lithium aluminum hydride, this alkyl halide should be either 1 degree alkyl halide or it should be 2 degree alkyl halide. After that, from aldehydes and ketones, have a look. If you are having C double bond O but of aldehyde, or it's of having, it's what we call a ketone, then what you have to do is, listen carefully, you can convert this into CH2. That means you can convert C double bond O to CH2 by using HI in red phosphorus. That means this is reduction of aldehyde or ketone to hydrocarbon. Similarly, you can convert C double bond O but of aldehyde or ketone to, I mean to say, CH2 once again by using zinc amalgam in acidic medium, but that acid can be HCl as well, or it can be H positive. Now, this reaction is known as Clemenson's reduction. But this reaction takes place in acidic medium. If aldehyde or ketone is sensitive towards acid, then this is not the better reaction. This is better reaction only if this aldehyde or ketone is not sensitive towards acid. If that is sensitive towards base, then this is the better reaction. Similarly, if you are having an aldehyde or a ketone, you can convert this C double bond O of aldehyde and ketone to CH2, and nitrogen gas will be evolved if it is treated with hydrazine, NH2, or you can write down N2H4 in basic medium and at high temperature. Sometimes ethylene glycol is given as solvent. Now, what will happen? This reaction is known as Wolff-Kishner reduction. This is known as Wolff-Kishner reduction. And remember, Wolff-Kishner reduction takes place in basic medium. That means only that aldehyde or ketone is converted to this, or this reaction is preferred if this aldehyde or ketone is not base sensitive. That means if it is acid sensitive, you can use this. If aldehyde or ketone is acid sensitive, Wolff-Kishner reduction is preferred. If aldehyde or ketone is base sensitive, then Clemenson reduction is preferred. After that, there is another reaction, that is from carboxylic acid. From carboxylic acid, we can obtain alkane by decarboxylation. That means loss of carbon dioxide. And that decarboxylation can be done either by using soda lime or by using electrolysis. By using soda lime, this reaction is known as Oakwood process. This reaction is known as Oakwood process. Now have a look. First of all, if we are having a carboxylic acid, it is treated with sodium hydroxide. That means acid and base reacts together and it will result in the formation of a salt. That means sodium salt of carboxylic acid first. Now, this sodium salt on treatment with soda lime. What is soda lime? Soda lime is NaOH and CaO in the ratio of 3:1. Soda lime is NaOH and CaO in the ratio of 3:1 at high temperature. What will happen? This bond will be broken and it will result in the formation of R negative. That means carbanion will be obtained. Carbanion is obtained in RDS, rate determining step. That means rate of decarboxylation. That means rate of decarboxylation of any acid or its sodium salt is directly proportional to simply the carbanion, that means R minus, formed in RDS. So this is what we call the rate determining step. That's why rate of decarboxylation depends on that R minus which is obtained from this by removing CONA or by removing COH. So if COH is attached to carbon, you just broke this bond and form a carbanion over here, or just broke this bond and form carbanion over here. So that carbanion, if that is very much stable, then rate of decarboxylation will be fast. Otherwise, it will be very slow. Now, you can simply say here it will result in the formation of this one. That means Na2CO3 is obtained. That means one alkane is obtained plus Na2CO3 is obtained. Here it's Na positive, CO3 2 minus. That means here loss of carbon dioxide has been taken place, but in the form of CO3 2 minus ion. Now, for example, we are having an acid like this, CH3COH, and we are having another acid like this, that is CH3CH2COH. Suppose we have to compare rate of decarboxylation among these during, reaction of this with soda lime. What will happen? Remember, you just break this bond, remove COH and form a carbanion over here. Carbanion is formed on that carbon to which COH group is attached. So carbanion will be formed. Now tell me, this is carbanion, but this carbanion is attached to plus I group. This is less stable, this is more stable carbanion. So this is the stability order. This is the stability order of carbanions. So rate of decarboxylation of that carboxylic acid is more, which can form more stable carbanion during RDS. That means rate of decarboxylation will be simply, my dear lovely students, like CH3COH will show faster reaction as compared to CH3CH2COOH. I hope this is clear. Now, after that, what you have to remember is that whenever you are having, say for example, a reaction like this, suppose CH3COH, and after that it's like this, NaOH, CaO and heat. Just remove this bond, just break this bond and form a carbanion and give H to this. That means it will result in the formation of methane plus Na2CO3. Simple. Similarly, if you are having a reaction like this, CH3, CH2, either COH or CONA, whatever, whether it is acid, whether it is sodium salt of acid, in presence of soda lime at high temperature, just break this bond, form a carbanion over here and give hydrogen to this carbanion. That means it will result in the formation of CH3 plus Na2CO3. I hope this is clear. After that, we will be having another decarboxylation, that is by using electrolysis. Reaction is known as Kolb's electrolysis or Kolb's electrolytic method. Now have a look. If you are having carboxylic acid, and from that carboxylic acid we form a sodium salt or a potassium salt. It can be either sodium salt, it can be either potassium salt, any salt, whether sodium salt, whether potassium salt. Remember this, whether sodium salt, whether potassium salt. If this is treated with water, let's balance the reaction. After that, electrolysis, it undergoes, electrolysis. Then what will happen? Break this bond, whether it is RCOH, break this bond, whether it is RCONA, break this bond and form radicals over here. So radical form will be R radical. Now R radical is formed, combine that radical. That means combination of R radical means RR will be obtained, and this will be obtained at anode. Remember this, at anode alkane is obtained. Similarly, this will lose carbon dioxide and I will balance the reaction. So I will lose 2 carbon dioxide molecules will be evolved. Once again, this carbon dioxide gas is evolved at anode. After that, hydrogen gas is evolved at cathode. Remember this. After that, my dear lovely students, if you take RCONA, then solution contains NaOH. And if we take RCOK, that means potassium salt of carboxylic acid, then it is KOH which is present in the solution. That means for this reaction, pH will be greater than 7 because this is alkaline in nature. But remember, if R is equal to H, that is, if you take HCOONA or HCOOK, at that time, instead of alkane, instead of RR, that means instead of alkane, we get HH, that means H2, at anode as well. That means at that time, this will become H2 at anode, carbon dioxide gas evolved at anode, H2 is evolved as at cathode. That means if this is the sodium salt of acid, then H2 gas is evolved at anode as well as cathode, and carbon dioxide gas is evolved at anode. I hope this is clear. After that, we will be having chemical reactions of alkanes. First reaction is halogenation. What is meant by halogenation? Halogenation means introduction of halogen to alkane. And remember, you should remember this one. This halogenation reaction is actually free radical. This is a free radical substitution reaction. This is an example of free radical substitution reaction. This is an example of free radical substitution reaction, which means intermediate of this reaction is free radical. This reaction is free radical. So intermediate is free radical. And remember, free radical reactions get completed in 3 steps. Step 1 is chain initiation, or you can say initiation. And number 2nd step is chain propagation, or you can say propagation. And 3rd step is chain termination, or you can simply say termination. So whenever you are having free radical reaction, that gets generally completed in 3 steps: initiation, propagation, and termination. Now, what is the reaction? Reaction is basically of alkane and halogen. That means reagent here is halogen and substrate here is alkane, and this reaction takes place in presence of light, whether it is HNO or it is UV, in presence of light or at high temperature. What will happen? It will simply, this halogen will replace this H, and it will result in the formation of Rx plus HX. So this is the reaction. Here X2 can be, this X2 can be F2, Cl2, Br2 and I2. So remember, among halogens, reactivity order towards this reaction will be, it's F2, which is very reactive as compared to chlorine, as compared to bromine, and bromine is very reactive as compared to iodine. Remember this order of halogens towards this reaction. Number 2nd point, here among hydrogens, reactivity order will be, because it is the hydrogen which has been replaced by amine, say halogen. So among hydrogens, reactivity order is 3 degree hydrogen is very much reactive as compared to 2 degree hydrogen, as compared to 1 degree hydrogen, because when you remove hydrogen from 3 degree carbon, it will result in the formation of a 3 degree carbon radical, which is more stable. That's why 3 degree hydrogen is more reactive as compared to 2 degree, as compared to 1 degree. Now, how will this reaction takes place? Have a look. I mean, say, what about mechanism? Now listen carefully. First of all, step 1 is chain initiation or initiation step. In initiation step, remember, formation of free radical always takes place from reagent. Our reagent is this one, halogen. In presence of light, whether it is HNO or UV, or at a high temperature, homolytic cleavage first of all takes place, and it will result in the formation of a radical over here. After that, this radical formed from reagent in first step, that means chain initiation step, will now attack on the substrate, and that reaction is known as propagation. Now have a look. This is our substrate alkane. This is the radical which has been formed over here. This radical breaks this carbon-hydrogen bond homolytically. And once hydrogen radical is formed with any other radical, hydrogen radical is more reactive. So this X will react with hydrogen and it will result in the formation of a new radical, R radical plus HX. This is first step of propagation. Then second step of propagation is R radical, once obtained in first step, will react with reagent once again. And reagent is XX. So because of this radical, homolytic cleavage takes place. X radical will be formed and it will react with R. So Rx will be obtained. That means our product will be obtained during propagation step. Now listen carefully. As product is obtained during propagation step, this product should be less energetic. Hence, all the propagation steps must be exothermic. So thermodynamic condition, favorable condition is that all the steps of propagation must be exothermic so that less energetic or more stable product is obtained. After that, as product is obtained, now we don't want to propagate reaction further. We want to stop the reaction. That's why all those radicals which are obtained during propagation will combine together. That means R radical can combine with R radical because this is R radical and it will result in the formation of an alkane. Similarly, X radical can react with X radical and it can form X2. Similarly, X radical can react with R radical and it can form once again a product. But major product is formed, major portion is formed in propagation step. So in this fashion, there is no radical. If there is no radical, so no radical will attack substrate and there will be no propagation, reaction will stop. So this is what we call halogenation of alkane. Now, listen, my dear students. Now, if halogenation is chlorination, say for example, we are talking about chlorination of alkane. For example, halogenation is chlorination. Say for example, we are talking about chlorination of alkanes. Now what will happen? What will happen? Let me write down a simple example. CH4, that means methane plus chlorine. Tell me, in presence of light or heat, what will happen? First of all, Cl radical will be obtained. That Cl radical will remove this H radical. In nutshell, H will be replaced by Cl. So it will result in the formation of this one. But if we take this CH3Cl and it further reacts with chlorine, that means if chlorine is taken in excess, then what will happen? What will happen? It will replace another hydrogen by once again Cl. So it will result in the formation of CH2Cl2 and HCl. Then once again this CH2Cl2 will react with Cl2 and it will result in the formation of CHCl3. Just a moment. So after that, this CHCl3 will react further with Cl2. Once again, a free radical substitution reaction takes place and it will result in the formation of CCl4. But listen carefully. As now there is no hydrogen present in this CCl4, so it will not react further. That means, can I say, this chlorination of methane in presence of excess of chlorine, basically in presence of excess of chlorine, in presence of light or in presence of heat, basically has formed CH3Cl, it has formed CH2Cl2, it has formed CHCl3, it has formed CCl4, but CCl4 will be the major product. Because once Cl2 is taken in excess, Cl radical will be formed in excess. Cl radicals are formed in excess. That means it will replace all the hydrogens and it will form CCl4. Or we can simply say halogenation or chlorination of alkane is actually polyhalogenation reaction. Now, tell me, if methane is taken in excess in this reaction, let me write down a very important point. If CH4 is taken in excess, if CH4 is taken in excess, not Cl4, not Cl2. If CH4 is taken in excess, remember, then CH3Cl will be the major product. At that time, CH3Cl will be the major product. CH3Cl will be the major product. I hope this is clear. After that, listen one more thing. Number of monochloro products or monochloro derivatives obtained from an alkane during chlorination is equal to number of different types of hydrogens present in an alkane. Remember this formula as well. This is very, very important formula. That means if you have this reaction, say for example methane plus chlorine in presence of light or heat, and you have to form monochloro products. Listen carefully, it's having only one type of carbon. That means it's all hydrogens are only having one type of hydrogen. So this is having one type of hydrogen. Just remove one hydrogen by one chlorine. So this will be the product of this reaction. This will be the monochloro product of this reaction. Only one monochloro product is obtained. But this formula is applicable excluding stereoisomers. This formula is applicable excluding stereoisomers. That means without stereoisomerism, this formula is applicable. Similarly, if you write down ethane, listen carefully. Ethane is also having 6 hydrogens, but all 6 hydrogens are only of one type. Similarly, if you react it with chlorine, as only one type of hydrogen is present, only one hydrogen among these 6 will be replaced by chlorine. So it will result in the formation of ethyl chloride. But listen carefully. For this and this formula is applicable excluding stereoisomer as well as including stereoisomer, because there is no stereoisomerism. When your monochloro derivative does not show any stereoisomerism, then it is applicable for both excluding as well as including stereoisomerism. But sometimes your alkane is like this. But let me show you one more example. CH3, CH2, CH3. This is having 2 different types of hydrogens. So here monochloro derivatives will be simply like this. CH3, CH2, CH2, Cl. That means you can replace hydrogen by chlorine from A position, that means this is A product, or you can replace hydrogen from B position like this. So this is the another product like this. So there are 2 products formed from this. 2 monochloro products will be obtained. Similarly, my dear students, if instead of alkane, cycloalkane is there, this reaction is applicable to that also. All these carbons, all these hydrogens are only one type. That means any one hydrogen, you can replace any one hydrogen and this will be the product. This will be the product. Side product will be HCl. Similarly, if this is the alkane, then remember, this and this are similar type. This is different, this is different, this is different. That means this is having 4 different types of carbons. That means 4 different types of hydrogens are there. So first remove hydrogen from A and replace that hydrogen by Cl. So A product will be like this. So A product will be like this. So this is A. Now replace B hydrogen by Cl, then product will be like this. B product will be like this. So this is B, my dear lovely students. Now if we replace C hydrogen, then C product will be like this. This is C product. And if we replace D hydrogen, then a reaction product will be like this. Now the question is, how many hydrogens, how many monochloro products are obtained over here? Here, answer will be different. Excluding stereoisomerism, answer is 4, but including stereoisomerism, answer is 6. Here, answer is different. Here, answer is different. But here, including stereoisomerism as well as excluding stereoisomerism, answer is same. Why answer is different over here? Have a look. This carbon is a chiral center. And whenever chiral center is there, that means sp3 center to which 4 different groups are attached is there, it can have this structure as well as its, say enantiomer. That means as well as its what we call mirror image. That means one is this, another is its mirror image. Then similarly, this is the chiral center. This will be one product, another will be its mirror image. That means this and mirror image, that means 4 products, 5 products, 6 products in total, including stereoisomerism, there will be 6 products. One will be A, another will be its mirror image, another will be B, another will be C, another will be mirror image of C, another will be D. That means in total there are 6 what we call products. But remember, this will be the major product. This one is the major product. Why is it so? Have a look. Have a look. Actually, 3 degree hydrogen is more reactive than 2 degree hydrogen, is more reactive than 1 degree hydrogen. But remember, 3 degree hydrogen is 5 times more reactive than 1 degree hydrogen, and 2 degree hydrogen is 3.8 times more reactive than 1 degree hydrogen with respect to chlorine. With respect to chlorine. Now, if we talk about this alkane, how many A hydrogens are there? 3 and 3, 6. That means if I write down like this, if I say type A hydrogens are 6 in number, Type B hydrogens, in this alkane, type B hydrogen is only 1 in number. It is 1 in number. Type C hydrogens, in this alkane, have a look, they are 2 in number. In this alkane, type C hydrogens are 2 in number and type D are 3 in number. And type D hydrogens are 3 in number. Now, which type of hydrogens are these? Have a look. A and D are 1 degree hydrogens. B is tertiary hydrogen. C is secondary hydrogen. That means this is 1 degree hydrogen. This is 1 degree hydrogen. This is 3 degree hydrogen. And this is 2 degree hydrogen. Now have a look. What is the reactivity of 1 degree hydrogen? It is 1. What is the reactivity of 3 degree hydrogen? It is 5. What is the reactivity of 2 degree hydrogen? It is 3.8. What is the reactivity of 1 degree hydrogen? It is 1. So this is the reactivity of 1 degree hydrogen, 1, 2 degree hydrogen, 1, 3 degree hydrogen, 1 degree hydrogen. But we have 6 1 degree hydrogen, so I will multiply it by 6. We have 1, so I will multiply it by 1. We have 2 hydrogens which are 2 degree, I will multiply it by 2. We have 3 1 degree hydrogens, so I will multiply it by 3. So here answer is 6, here answer is 5, here answer is 7.6, here answer is 3. When we add all these, so it becomes 21.6. 21.6. 21.6 is the total reactivity of all these hydrogens. But what is the reactivity of this among 21.6? So it is 6 divided by 21.6 multiplied by 100. So you can calculate this. You can calculate its percentage. Similarly, you can calculate percentage of this. You can calculate percentage of this. You can calculate percentage of this. And you can calculate percentage of this as well. And you will see the more percentage compound is this one. That means type C hydrogen. If type C hydrogen is replaced, that means if type C hydrogen is replaced by Cl, product formed will be the major product. That means this is the major product. That's why I have written over here, this is the major product. But listen, these A and D, these are 1 degree carbon. Hydrogen attached to that is 1 degree hydrogen. If 1 degree hydrogen is removed, 1 degree carbon free radical is obtained. If 2 degree hydrogen is removed, 2 degree carbon free radical is obtained. And if 3 degree hydrogen is removed, 3 degree carbon free radical is obtained. Among 1 degree carbon radical, among 2 degree carbon radical and 3 degree carbon radical, remember 3 degree carbon free radical is more stable. That means that reaction where major product is always obtained, from more stable carbon free radical. That means from this tertiary carbon free radical, that reaction is known as selective reaction. But in this reaction, in this chlorination, major product is not formed from that carbon free radical which is most stable carbon free radical. That's why this is not selective reaction. So we will simply say chlorination. Chlorination of alkane. Chlorination of alkane is non-selective reaction. That means the major product during chlorination of alkane is not necessary that major product will be always formed from more stable carbon free radical. Remember this. After that, we will be having another reaction, that is bromination of alkane. And remember, this bromination takes place. It takes place in similar manner. It takes place in similar manner as that of chlorination. That means everything here is same as that of chlorination except few points. Point number one. We know 3 degree hydrogen here is more reactive than 2 degree hydrogen like that of chlorination than 1 degree hydrogen, but the reactivity order is something different. I mean, say that that relative reactivity is something different. This is 1600 times more reactive than 1 degree hydrogen, and 2 degree hydrogen is more reactive, 82 times more reactive than 1 degree hydrogen. This is when we talk about bromine, with respect to bromine. This is basically at different temperatures, but you just try to remember this. Point number one. Point number second is that bromination is a selective reaction. Compared to chlorination. That means during bromination, that means if same reaction takes place, but instead of chlorine, bromine is there, then major product will be always formed from this more stable carbon free radical. That means this one here, if it is Br, then this will become the major product. That means if we use bromination, then among A, B, C, D, B will be the major product. That means bromination is a selective reaction, but chlorination is non-selective reaction. Remember that. Otherwise, all these reactions will be similar type of reaction will take place. Similar type of formula will be there as per chlorination is concerned. As per bromination is concerned, similar type of reaction, similar type of formulas. Everything will be similar as that of chlorination. Now, after that, number third is fluorination. Fluorination of alkane. Remember, fluorination of alkane. Remember this. Direct fluorination of alkane is not possible. Direct fluorination of alkane is not possible. Because this reaction is too violent to be controlled. Actually, fluorine is very much reactive. That's why this reaction is too violent to be controlled. Fluorine is very much reactive. Because of that, reaction is highly exothermic. So tremendous amount of energy is evolved. Because of that, carbon-hydrogen as well as carbon-carbon bonds of alkane will rupture and different undesired products will be formed. That means the reaction will become uncontrolled one and explosive one. That's why direct fluorination is not possible. After that, it's iodination of alkane. After that, it's iodination of alkane. Listen carefully, my dear lovely students. Direct iodination is not possible. Direct iodination of alkane is not possible because reaction is reversible. Because reaction is reversible due to formation of HI. Due to formation of HI, which acts as a reducing agent, and converts alkyl iodide back to corresponding alkane. Converts alkyl iodide back to corresponding alkane. I mean to say, whenever iodination of alkane takes place, it's a reversible reaction because during this reaction, alkyl iodide is formed, but there is HI also formed, which acts as a reducing agent. It reduces this CH3I back to CH4. That means it is a reversible reaction. As it is reversible reaction, so we cannot obtain alkyl iodide. We cannot, do what we call iodination of alkane. But this iodination of alkane is possible. That means formation of alkyl iodide is only possible if we remove this HI, and this HI is removed only in presence of oxidizing agents. That means direct iodination can be possible. Direct iodination can be possible only in presence of oxidizing agents like HNO3, HGO, or you can say HiO3, iodic acid, or you can use HiO4 as well, that is periodic acid, etc. That means, my dear lovely students, if you want to convert methane into methyl iodide, it is possible only and only if HI is not there, and HI will be removed only by either HNO3 or by HGO or by HiO3, or you can also use HiO4. These will convert HI to either HgI2 or to iodine. That means there will be no HI, hence reaction will not be reversible, it will be an irreversible reaction. I hope this is clear. After that, my dear lovely students, there is another reaction after iodination, chlorination, bromination. That means after halogenation of alkane, there is another reaction, that is combustion. Now have a look. We know whenever you are having a hydrocarbon CXHY and there is X plus Y by 4 of oxygen, because what is combination? It's simply burning off, substance in presence of excess of oxygen is known as complete combustion. Then it will result in the formation of X times carbon dioxide plus Y by 2 water. Now plus amount of heat. And remember, due to evolution of large amount of heat, due to evolution of large amount of heat during combustion, hydrocarbons can be used. Hydrocarbons can be used as fuels. Can be used as fuels. Now, you can take simple example. If X is 1, Y is 4, that means it is CH4. It is CH4. Say, for example, value of X is 1 and value of Y is 4. It becomes CH4. Then, this becomes 1 plus 4 by 4, that means 1 plus 1, that means 2. It is twice O2. It gives X, that means 1 times carbon dioxide, plus Y by 2, that means 4 by 2, that means twice H2, plus large amount of heat. Now have a look. Is reaction balanced? 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, oxygens, 2, 4, here oxygens are 4. So this is the balanced reaction. Similarly, if alkane is heated in limited supply of oxygen, that means incomplete combustion, during incomplete combustion, here we get carbon black plus, you can say, twice H2. This carbon black is used in manufacture of ink, you can say printer ink, you can say black pigments, you can say filters, etc. So this is all about combustion. After that, there is controlled oxidation. Have a look. If you are having an alkane, say for example methane, for example ethane, it's in NCERT it's written methane, I have written over here ethane. But reaction or oxidation takes place by using copper at 573 Kelvin and 100 atmospheric pressure. So what is the trick? Remove one of the hydrogens from one of the carbons by one OH. That means you will get alcohol. Similarly, if same alkane is treated with molybdenum oxide, MO2O3, then what will happen? This will oxidize this in this fashion. Remove 2 hydrogens from the same carbon by 2 OH groups. When you remove 2 hydrogens from the same carbon by 2 OH groups, this compound, which is an unstable compound, it will be first formed, but once it formed, it will lose water molecule. It loses water molecule, and finally, product will be an aldehyde. CH3, C double bond O and H. Product will not be this, product will be this. Similarly, if you use manganese acetate, as an oxidizing agent, this will replace 3 hydrogens from the same carbon by 3 OH groups. Have a look. Once again, this is an unstable species. So we will simply result in the formation of, this will lose water molecule and it will simply result in the formation of carboxylic acid. So it will result in the formation of carboxylic acid. That means this will be converted to carboxylic acid, this will be converted to aldehyde, this to alcohol. But alkanes show resistance towards KMnO4. That means KMnO4 oxidizing agent cannot reduce generally alkanes, but if alkanes contain tertiary hydrogen, then they can be oxidized by KMnO4. At that time, they can be oxidized by KMnO4. Have a look. That means if we are having an alkane in which there is at least one tertiary hydrogen, this is tertiary hydrogen attached to tertiary carbon, then it is oxidized by using KMnO4 to alcohol. That means H is replaced by OH group. Remember this. So KMnO4 cannot oxidize alkane unless and until it contains at least one tertiary hydrogen. After that, we will be having nitration. And this nitration is known as vapor phase nitration. Vapor phase nitration. This is known as vapor phase nitration. Have a look. If you are having an alkane, say for example methane, this on treatment with fuming nitric acid at a temperature of approximately 673 Kelvin results in the formation of, this is simple free radical substitution reaction. H will be replaced by NO2. So it will result in the formation of CH3NO2. But if we take an alkane having more than one carbon, then it will result in the formation of a mixture of nitroalkane. Have a look. Either CH bond will be broken, and when CH bond is broken, H radical will be lost with this OH, and there will be CH3CH2 radical, and to that CH3CH2 radical, NO2 radical will be attached. That means it will result in the formation of this if CH bond is broken. But if CC bond is broken, CH3 radical will be obtained, and that CH3 radical will combine with NO2 and it will result in the formation of CH3NO2. That means nitroalkanes are obtained, but in different nitroalkanes will be obtained. That means in mixture. And here, once again, as this is free radical reaction, 3 degree hydrogen is more reactive than 2 degree, is more reactive than 1 degree hydrogen. After that, sulfonation. Once again, a free radical substitution reaction. Alkanes generally do not show this reaction until and unless normal alkane contains 6 carbon atoms, or our alkane must contain at least tertiary hydrogen. Either it should contain tertiary hydrogen or it must contain more than 6 carbons. This is having 1, 2, 3, 4 carbon but having tertiary hydrogen. Now, this on treatment with H2SO4 at high temperature approximately 773 Kelvin. Once again, a free radical reaction. So H radical will be replaced and SO3 H radical will come instead of, sulfonation. Introduction of sulfonic acid group has been taken place. That's why this is sulfonation reaction. After that, my dear lovely students, it's isomerization. That means conversion of one compound into another, but both are isomers of one another. Have a look. If you are having N-butane, on heating with AlCl3HCl, what will happen? This N-butane without, branch gets converted to 2-methyl propane. That means one isomer gets converted to another isomer. This is known as isomerization. Similarly, 1, 2, 3, 4, 5, 6, that means N-hexane on treatment with this can result in the formation of this one. This is 2-methyl pentane, or it will result in the formation of this one known as 3-methyl pentane. That means one isomer gets converted to another isomer. This is simply known as isomerization. After that, aromatization. Aromatization is very, very simple. That N-hexane over here. That means this reaction is shown by alkane which contain at least 6 carbons. 1, 2, 3, 4, 5 and 6. N-hexane. N-hexane on treatment with oxidizing agents. Say for example, Cr2O3 or MO2O3 or V2O5, Cr2O3 or MO2O3 or V2O5, any one oxidizing agent supported over alumina. That means alumina will be a catalyst over here. At a temperature of 773 Kelvin and at a pressure of 10 to 20 atmospheric pressure will result in the formation of benzene. That means N-hexane gives benzene with 4 moles or 4 molecules of H2. Similarly, if N-heptane is there, if N-heptane is there, or my dear lovely students, it is 2-methylhexane. Listen carefully. 1, 2, 3, 4, 5, 6, 2-methylhexane, 1, 2, 3, 4, 5, 6, 7, N-heptane. During similar conditions, it will result in the formation of methylbenzene, or we can call toluene. So toluene is obtained from N-heptane or 2-methylhexane, but benzene is obtained from N-hexane during aromatization. Similarly, if you are having N-octane, 1, 2, 3, 4, 5, 6, 7, 8, that means if you are having N-octane, at that time, under similar conditions, we will get ethylbenzene, and its isomers like 1,2-dimethylbenzene or orthoxylene, 1,2-dimethylbenzene or orthoxylene. Similarly, 1,3-dimethylbenzene or metaxylene, or 1,4-dimethylbenzene or paraxylene. I hope this is clear to each and every one there. After that, reaction of alkane with steam. That means if you are having a simple alkane, methane, and it's heated with water, that means steam is there, at a temperature of 1273 Kelvin in presence of nickel, then what will happen? It will result in the formation of carbon monoxide and hydrogen. It will result in the formation of this. After that, pyrolysis. Pyrolysis of alkane is also known as cracking. Now, what is meant by pyrolysis? Pyrolysis means breakdown of higher alkane to lower alkane and alkenes. Say, for example, if you are having propane, and now at high temperature, say for example 773 Kelvin, what will happen? It can result in the formation of propene and H2, or it can form simply methane plus ethene. That means higher alkane has been converted to lower alkane and alkenes. Similarly, if you are having butane, it will result in the formation of prop-1-ene plus hydrogen, or it can result in the formation of prop-2-ene plus hydrogen if CH bond is broken. But if CC bond is broken, it will result in the formation of, I mean say propene, CH3CH, double bond CH2 plus CH4. It will result in the formation of propene plus CH4 if this bond is broken. And if this bond is broken, then it will result in the formation of ethane and ethene. It will result in the formation of this as well. Ethane plus ethene. In nutshell, higher alkane is converted to lower alkane, or it can be higher alkane can be converted to lower alkane or into alkene with the help of temperature. So this is known as thermal cracking. Sometimes we use, catalyst. At that time, we can say it is catalytic cracking. Now, I hope this is all clear. This was all about methods of preparation of alkane. Now, let me know in the chats, is this clear to each and every one till now? So that we will start alkene, which is very, 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 very important. Just a moment, give me 2 minutes. I will drink something. I will drink this, water. I hope till now everything is clear. No need of mechanism for aromatization at the rate of SR. No need of mechanism at all. Whatever I am saying, this is for your revision. Try to listen, try to revise your things so that everything will be clear to you. There is no need of mechanism if I am not showing the mechanism. If I am not showing the mechanism, there is no need of mechanism at all. Okay. Now, let's discuss methods of preparation of alkenes now, because alkenes are very, very, very important. Now, have a look. Have a look, my dear lovely students. Have a look. Here, first of all, it's from alkynes by partial hydrogenation. Now, how? Have a look. If you are having an alkyne like this, when alkynes are treated with H2 in presence of PDC, or H2 in presence of PDCaCO3 plus small amounts of sulfur or quinoline. This is known as Lindlar's catalyst, or H2 in presence of PDBaSO4 with small amounts of sulfur or quinoline. This is known as Rosenmund's catalyst. You can use this one as well, or you can use P2 catalyst. P2 catalyst is known as nickel boride, Ni2 and B, nickel boride. So any one among these catalysts can be used so that alkyne can be converted to alkene, but that alkene from which these hydrogens have been added from the same side, that means cis alkene. So alkene from alkyne will be obtained, but cis alkene. Similarly, if this alkyne is treated with sodium in liquid ammonia, or you can use lithium in liquid ammonia. So by the way, this reaction is known as Birch reduction. At that time, we will get an alkene, but this alkene will be a trans alkene. This will be a trans alkene. Remember this. That means both are addition of hydrogens, partial addition of hydrogen, partial reduction, but one will give cis alkene, another will give what we call trans alkene. After that, my dear lovely students, next reaction is from alkyl halide by dehydrohalogenation. What is meant by dehydrohalogenation? Dehydrohalogenation means removal of hydrogen and halogen. That means this is elimination reaction. Here, reagent reagent we use, or the reagent which NCERT has given, is alcoholic potassium hydroxide. Whenever alcoholic potassium hydroxide is there, remember this elimination is E2 elimination. That means this is a bimolecular elimination reaction. Now have a look. If you are having CH3, CH2 and X, this X is a leaving group. Attached to carbon is known as alpha carbon, and after that this is the beta carbon. Whenever alcoholic potassium hydroxide is there at high temperature, because high temperature favors elimination, you have to remove leaving group from alpha position and you have to remove hydrogen from beta position. That means you have to remove hydrogen and halogen. You will get this one. So this is what we call a product. This is the product of this reaction, and this reaction is simply E2 reaction. But listen carefully. Listen carefully. Among alkyl halides, reactivity order of this reaction, as this is the E2 reaction, reactivity order will be simply 3 degree alkyl halide is more reactive than 2 degree, is more reactive than 1 degree alkyl halide. Remember this point. Remember this point. This is very, very important point. Similarly, among Ri, RBr, RCl and RF, reactivity order will be will be like this. It will be Ri greater than Rbr greater than RCl greater than Rf. And this order is based on the leaving group ability, because rate of E2 is directly proportional to the leaving group ability of the group. I minus is a better leaving group as compared to Br minus, as compared to Cl minus, as compared to F minus. That is why Ri shows faster E2 reaction as compared to Rbr, as compared to RCl, as compared to Rf. So this is the reactivity order towards this reaction, which is an E2 reaction. Listen carefully. Now, my dear lovely students, remember, number of products formed during this reaction is simply equal to number of different types of hydrogens present at beta positions. That means different types of beta hydrogens, because hydrogens present at beta position means different types of beta hydrogens. You have to check different types of beta hydrogens in this alkyl halide. If alkyl halide is having only one type of beta hydrogen, only one alkene will be obtained, only one product will be obtained. For example, if you are having a structure like this, listen carefully. And suppose this X is not equal to F. That means X is either equal to Cl or Br or I. Then what will we do? Have a look. Then if reaction takes place with alcoholic potassium hydroxide, first of all, we have to find out alpha and beta positions. From alpha, you have to remove halogen, leaving group, and from beta, we have to remove hydrogen. Now, when we compare this beta and this beta is having 2 hydrogens and this beta is having 3 hydrogens. So with respect to beta hydrogens, here beta hydrogens are more. So this is rich with respect to beta hydrogen and this is poor with respect to beta hydrogen. And remember, if base removes hydrogen from this beta position which is rich, then this beta and alpha will form double bond. That means this will be the product at that time. And product or alkene formed from that beta which is rich is always known as Hofmann's product. So this is Hofmann's product. Similarly, product formed from that beta position which is poor with respect to hydrogen, that product is like this, and that product is always named as Sad-Zep product. This is Sad-Zep's product or Zatsev's product because its actual name was Alexander Zatsev and Sad-Zep was its, nickname. So these products will be obtained. But during this reaction, if it is not, Cl, if it is not F, if it is Cl, Br or I and base is like this, then remember this will be the major product over here. This will be the major product and this will be the minor product over here. During this reaction, this is major product, this is minor product. How many products are obtained? 2. Why 2? Because there are 2 different types of beta hydrogens. Now, the question is, if we are having same substrate, the only difference is that we will be having fluorine over here. Remember, if you are having fluorine in case of alkyl fluoride, leaving group is fluorine. Fluorine is not, F minus is not a good leaving group at that time. What is the trick? How can we say which one is minor and which one is major? Listen carefully. First of all, this is alpha, this is beta, this is beta. And this is rich beta. That means this is the position which is rich with respect to hydrogen. And this is the beta which is poor with respect to hydrogen. So first of all, what will be the products? One of the products will be CH2 double bond CH, single bond CH2, single bond CH3. This will be the Hofmann product. And another product will be Sad-Zep. That means Sad-Zep product is always formed from poor beta position. Now, which one among this is minor and which one among this is major? How to find out that? In this case, you can simply say major product is that, product which is more stable. As this product is more stable, have a look. This is more stable because this is having 3 and 3, 6 alpha hydrogens, but this is having only 2 alpha hydrogens. Have a look. This is having only 2 alpha hydrogens. So this is less stable, this is more stable. So more stable product, that will be simply a major product. This is not exact reason, but this is the trick. But for this one, how to remember which one is major and which one is minor? Have a look. For whenever alkyl fluoride is there, that means F minus is the leaving group, you just form a carbanion at beta position. Form carbanion at beta position. Listen, this carbanion is more stable as compared to this one. As we know, this carbanion is more stable as compared to this one. So carbanion, which is more stable, the product formed from that will be obviously major. So this will be major product, because it has been formed from most stable carbanion, and the product which is formed from less stable carbanion is always minor product. So here, this is the minor product. So it depends upon which one is major, which one is minor. It depends upon the stability of carbanion if fluorine or F minus is the leaving group. Remember this. For example, another example. Let's take another example like this. If we are having this one, once again it is F, leaving group is poor leaving group. Now what to do? Have a look. Once again, it's alcoholic potassium hydroxide. Once again, an E2 reaction. This is alpha, this is beta. But this beta is having 2 hydrogens. This beta is having 3 hydrogens. So this is rich with respect to hydrogen. This is poor with respect to hydrogen. Now, first of all, let's form product. If this hydrogen has been removed, beta and alpha will form double bond. So one of the products will be like this. CH, double bond CH, single bond CH3. This product has been formed from poor, so this is as a product. Then another product will be like this. From this one. So it will be like this. CH2, CH, double bond CH2. So this is what we call Hofmann product. Now, listen carefully. Which one among these is major product? It will not be decided by the stability of the product. It will be decided basically by the stability of the carbanion. So we will form carbanion over here. One carbanion is this, another carbanion is this. This carbanion is resonance stabilized. That means this is more stable carbanion. So product formed from that is this one. That means this is major product. This is major, and obviously this product is formed from less stable carbanion. Hence this product is what we call minor. So whenever leaving group is F minus, sometimes it is Hofmann product, which is major product. Sometimes it can be, ZF, which is major product. It depends on actually stability of transition state, but I have given you the trick. It depends on stability of carbanions formed at beta position. I hope this is clear. This is all about what we call dehydrohalogenation of alkyl halides. After that, from vicinal dihalides. What is meant by vicinal dihalide? Vicinal dihalide means in which 2 halogens are present at 2 adjacent positions. That means 1,2 dihalides. When these 1,2 dihalides are heated with zinc, remember, it will simply lose X2 and it will form an alkene. So this is very, very simple reaction. This is also an E2 reaction, but you just remember like this, that remove X, form a double bond between these two. Very, very simple. After that, another is from alcohols by acidic dehydration. Remember, this reaction is actually the example of E1 reaction. It's an example of E1 reaction. Have a look. Whenever you are having an alcohol, like this, let me write down like this. Whenever this alcohol is heated with acid, suppose H2SO4 or H3PO4, protonic acid like this, or you can use, I mean, say catalysts like alumina as well, but here it is acidic dehydration. So let me write down concentrated H2SO4 or concentrated H3PO4 at high temperature. Then this OH and H will be lost and it will result in the formation of an alkane. It will result in the formation of an alkene. That means this is dehydration. But this dehydration takes place in presence of acid. So have a look. If we are having a primary alcohol like this, if we are having a primary alcohol like this primary alcohol on treatment with H2SO4 at a temperature of about 443 Kelvin undergoes intramolecular dehydration. That means from this position OH will be lost, from this position, I mean, say hydrogen will be lost. Now have a look. Then it will result in the formation of, I mean, say ethene plus water. But this is if primary alcohol is there. If we talk about secondary alcohol, secondary alcohols are more reactive. That's why reaction can take place at, I mean, say only 85% of acid. Let us suppose 85% of H3PO4 and temperature of 440 Kelvin. Then it will result in the formation of an alkene like this. That means OH from this, H from this, that means water. So once again, intramolecular dehydration. Similarly, if we talk about tertiary alcohol, tertiary alcohols are much more reactive. So tertiary alcohols are much more reactive towards this reaction. This reaction takes place at 20% of acid. That means concentration of acid is less and at a temperature of 358 Kelvin. That means towards normality, reaction goes towards normality and reaction product is like this. So with the help of these reactions, it is clearly understood that dehydration of tertiary alcohol is fast as compared to secondary, as compared to primary. Why is it so? Have a look. Actually, what happens? Actually, what is the mechanism? Let me show the mechanism with the help of a tertiary alcohol. First of all, protonation will take place. That means this H positive can be from either H2SO4 or H3PO4. So protonation of alcohol first of all takes place. Now, once protonation will take place, this OH becomes OH2 with a positive charge. Let me tell you, this OH is not a good leaving group. This is poor leaving group, I can say. Now, this H2O positive is a good leaving group now. That means first of all, it becomes a good leaving group. Now, this leaving group will leave. It will leave in the form of water. And it will result in the formation of a carbocation. Listen carefully. This carbocation formation, that means this step, is the slowest step of the reaction and hence this is the rate determining step of the reaction. That means rate of dehydration of any alcohol depends on this step. That means rate of dehydration of any alcohol depends on how much stable carbocation that alcohol can form. Tertiary alcohol can form more stable carbocation as compared to secondary, as compared to primary. That's why tertiary shows much faster reaction as compared to secondary, as compared to primary. Now after this, then simply this has been obtained. After that, H positive will be lost. Either from this carbon adjacent to the carbocation or from this carbon or from this carbon. That means H positive, once used, finally lost, it will act as a catalyst. So H positive will be lost either from this or from this or from this. Suppose from this one, H positive is lost. That means it becomes like this. So this alkene is obtained. So can we say, this is very, very important point then. Can we say that rate of dehydration of alcohol, it is directly proportional to stability of carbocation formed in RDS. This is very, very, very important point. Very, very, very important point. Remember. Now tell me, if you are having tertiary, secondary, primary alcohol, which can form more stable carbocation? Tertiary. After that, secondary. After that, primary. So that is why reactivity, or rate of dehydration among alcohols will be simply 3 degree greater than 2 degree greater than 1 degree. Similarly, my dear lovely students, if these are the alcohols, say for example, this is alcohol number 1, this is alcohol number 2, and this is alcohol number 3. Tell me, what will be the rate of dehydration among these 3? Have a look. Alcohol containing OH first gets converted to OH2. Finally, this will be lost. That means OH attached to carbon break this bond and form a carbocation. Now have a look. Just break this bond and form a carbocation, because finally carbocation will be formed over here. Break this bond and form a carbocation. Finally carbocation will be formed over here. Break this bond and form a carbocation. Now tell me, my dear lovely students, which among these carbocations is most stable? This is most stable because of more resonance as compared to this. And this is more stable as compared to this because this is having hyperconjugation, this is having resonance as well as hyperconjugation. So this is the most stable carbocation. If this is the most stable carbocation, then this is stability order. Stability order of carbocation. Now tell me, rate of what we call dehydration of alcohol is directly proportional to stability of carbocation formed in RDS. So can I say among these 3, it will be 3 greater than 2 greater than 1. This will be the rate of reactivity towards dehydration, or this is rate of dehydration. This is order for rate of dehydration. Yes or no? This will show faster reaction as compared to this, So this was all about dehydration of alcohol. After that, there are chemical reactions of alkenes. And remember, the characteristic chemical reactions of alkenes are electrophilic addition reactions. And remember, alkenes can show electrophilic addition reactions, that means EAR. And these EAR are of 2 types. Either electrophilic addition reactions can take place via classical carbocation. That means one is classical carbocation mechanism. Electrophilic addition reaction which takes place via classical carbocation is known as classical carbocation mechanism. Another is non-classical carbocation mechanism. What is meant by this? That electrophilic addition reaction which takes place via classical carbocation is known as shows classical carbocation mechanism. Now the question is, what is meant by classical carbocation? Classical carbocation means carbocation in which positive charge is fully developed. That means, point number 2, that means rearrangement can take place. That means we have to check whether carbocation undergoes shift rearrangement or not. Because if after shift carbocation becomes more stable, we have to rearrange that carbocation. Similarly, my dear lovely students, generally shown, this type of mechanism is generally shown by reagents which are highly polar. For example, according to our NCERT, example is HX. That means if HX is added to alkene, reaction takes place via classical carbocation. Similarly, H2SO4 Similarly, H3O positive, that means addition of water in presence of acid. These three reactions are given in your NCERT. That means these three reaction takes place via electrophilic addition reaction, but via classical carbocation. Similarly, there is a non-classical carbocation mechanism. So first of all, we must know what is meant by non-classical carbocation. Non-classical carbocation means carbocation in which positive charge is not fully developed, in which positive charge is not fully developed. That means it is partially developed. It's not fully developed. If positive charge is not fully developed, listen carefully, there will be no rearrangement. No rearrangement. And reagents used generally this type of mechanism is shown. Generally, this type of mechanism is shown by reagents which are non-polar or less polar, and electrophilic part of reagent, electrophilic part of reagent generally contains lone pair of electron. Generally contains lone pair. For example, if you are having X2 in presence of, say for example, CCl4, that means X2 is the reagent. So it's non-polar reagent. Similarly, if you are having X2 in presence of water, or you can simply say HOX, this is polar, but this is not highly polar. This is slightly polar. This is less polar, slightly polar. Similarly, you can use, say oxymercuration, demercuration reaction as well. So these all, whether it is halogenation in presence of non-polar solvent, halogenation in presence of polar solvent, or oxymercuration, demercuration, these all reactions takes place via non-classical carbocation, and there will be no rearrangement, and that is an example of electrophilic addition reaction. So let's take these reactions one by one. Have a look. First of all, addition of HX. Addition of HX to alkene. Let's say this is an alkene. This is HX. What will happen? Have a look. Have a look. In presence of this reagent, electromeric effect takes place, and this H positive gets, added to this carbon-carbon double bond. So when it adds to carbon-carbon double bond, X minus will be lost. This step is slowest step and hence rate determining step of the reaction. So it will result either in the formation of this one. Have a look. Have a look. That means this H positive can be added to this. At that time, carbocation will be formed like this. Similarly, my dear lovely students, H will be added to this carbon. So it will become CH2, and this will form CH2 positive like this. But listen, among these two, this is more stable carbocation. This is more stable carbocation. And this is less stable carbocation. That means a reaction prefers to go via this as compared to this. Both can be formed, but this will form more as compared to that. After that, my dear lovely students, you have to rearrange these types of carbocations. So rearrange if possible. Rearrange if possible. You have to rearrange if possibility is there. If after rearrangement carbocations becomes more stable, then you have to rearrange. Then after that, my dear lovely students, this X minus will act as a nucleophile, and it will be a very fast attack. That means this nucleophile will attack to carbocation, this and to this, and can form two products over here. One is CHX, CH3. Another is RCH2, CH2X. But this one will become the major product, and this will be the minor product. But our main focus will be now on major product only. But There are possibilities of formation of this as well, but this will be the major product because this is formed from more stable carbocation. Now listen carefully, listen carefully, listen carefully. This is an unsymmetrical reagent and this is unsymmetrical substrate. Whenever unsymmetrical reagent is added to unsymmetrical substrate during electrophilic addition reaction, generally product formation takes place. That means generally major product formation takes place via Markovnikov's rule or according to Markovnikov's rule. What is meant by Markovnikov's rule? Listen carefully, listen carefully. But before that, you must know this one. Among HX, but before Markovnikov's rule, you must know among HX, reactivity order will be HI greater than HBr, greater than HCl, greater than HF. Point number one. Point number one. Second point is among alkenes, rate of reactivity depends on stability of carbocation. Among alkenes, remember, rate is directly proportional to stability of carbocation formed in RDS. That means if 4 alkenes are given, just form carbocation from 4 alkenes but without rearrangement. The alkene which can form more stable carbocation is more reactive towards this reaction or towards HX. Now after that, this is point number 1, this is point number 2. Point number 3. In general, whenever unsymmetrical reagent is added to the unsymmetrical substrate, addition takes place. According to Markovnikov's rule. Now, what is meant by Markovnikov's rule? What is the statement of Markovnikov's rule? Let's start its statement, or let's write down its statement. Markovnikov's rule states that, so I will simply write down, it states that, first of all, it's only and only applicable if unsymmetrical reagent is added to unsymmetrical substrate. Remember that. So it states that negative part of addendum. Addendum means molecule to be added. Or we can simply say reagent because we have to add reagent. So negative part of addendum or negative part of unsymmetrical reagent goes to that carbon-carbon double bond or carbon-carbon triple bond. But in our case, it is carbon-carbon double bond. Goes to that carbon-carbon double bond or carbon-carbon triple bond which is having lesser number of hydrogens. For example, if you want to add HX to this propene, here, remember, the major product will be simply that negative part of this goes to that carbon-carbon double bond which is having lesser number of hydrogen. That means this is the major product of the reaction. This product, which is the major product of reaction, this is according to Markovnikov's rule. So I can say this is Markovnikov's product because this is according to the Markovnikov's rule. But listen carefully. There are exceptions to Markovnikov's rule. That means Markovnikov's rule is not valid when, point number one, if rearrangement takes place during the reaction. If rearrangement takes place during the reaction, then major product can never be according to Markovnikov's rule. Point number second. If electron withdrawing group is attached to carbon-carbon double bond. That means if rearrangement takes place, at that time major product can never be according to the statement of Markovnikov's rule. Similarly, if electron withdrawing group is attached to carbon-carbon double bond, at that time major product can never be according to the statement of Markovnikov's rule. What is meant by that? Have a look. For example, you are having this one. You are having this alkene. You are having this alkene. What is the expected product? What is the expected product during this reaction, or what is the expected major product of this reaction? Expected major product of this reaction is that negative part should go to this, obviously positive part should go to this. But what will happen over here? Have a look. First of all, it will result in the formation of this one. This is slowest step. That means rate determining step. Listen carefully, my dear lovely students. It will result in the formation of this one. It will result in the formation of this one. This is the carbocation. Now, as this carbocation can undergo rearrangement like this, it can undergo 1,2-methyl Carbanion shift, because after this shift, it will result in the formation of more stable carbocation. It will result in the formation of more stable carbocation. It will result in the formation of more stable carbocation. How? Have a look. This carbocation is more stable because of 7 alpha hydrogens. This carbocation is stable because of only 3 alpha hydrogen and inductive effect of this group. But this is stable because of 7 alpha hydrogen. That means this is more stable. More stable means shift is possible. After that, finally, as this is the most stable carbocation of this reaction, finally X minus will attack. X minus will attack to this carbocation and we will get this one. CH3C, CH3. Here it is X. Here it is CH, CH3. Then CH3. Was this product expected according to Markovnikov's statement? Answer is no. Because according to Markovnikov's statement, X should go to this carbon. But X goes to this carbon. So this product is known as rearranged product. Rearranged product. Here is the major product. This is the rearranged product, or we can say this is an unexpected product as per statement of Markovnikov's rule is concerned. So this is unexpected product. And this is the major product of this reaction. So remember, whenever addition of HX to alkene takes place, major product is always that product in which negative part of HX goes to that carbon which can form most stable carbocation. Any carbon which can form most stable carbocation, negative part of HX, that means X goes to that, and that will be always the major product. So Markovnikov's product is not always the major product. So here Markovnikov's product is not the major product. That means why Markovnikov's product is not the major product? Because here rearrangement takes place. So this is point number one. Point number second. Let's discuss point number second. Let's discuss point number second. If you are having an electron withdrawing group, say for example NO2, which is attached to carbon-carbon double bond. Now, my dear lovely students, what will happen? First of all, addition of HX takes place to this carbon-carbon double bond. But listen carefully. This step is slowest step, rate determining step. So First of all, we will form positive charge. If we form positive charge over here, that is unstable because of electron withdrawing group. So we will form positive charge over here. That means H will go to this carbon. So positive charge will be formed over here because this is the most stable carbocation of this reaction. So there will be no rearrangement. After this, X minus will attack. X minus will attack to this carbocation. Obviously, our product will be this. So was this product, according to this, is this product according to the statement of Markovnikov's rule? Answer is no. Because according to Markovnikov's rule, X minus should go to this. But for that, this carbon should be having positive charge. But this carbon is not forming positive charge because of, I mean to say, electron withdrawing group, because that electron withdrawing group destabilizes the carbocation over here. That means that is less stable carbocation as compared to this. So more stable carbocation will form always major product. So this is the major product of the reaction. This is the major product of the reaction. So major product here is not formed according to the statement of Markovnikov's rule. I hope this is clear. I hope this is clear. One more thing. Whenever you are having CH3CH double bond CH2, whether reaction takes place, listen carefully, whether reaction takes place with HF, just a moment, give me a second. Whether reaction takes place with HF in absence of peroxide, or in presence of peroxide. Listen carefully. Whether reaction takes place with HF either in presence of peroxide or absence of peroxide. In presence of peroxide or absence of peroxide. Product will be always according to Markovnikov's statement over here. That means intermediate of this reaction will be carbocation and reaction is electrophilic addition reaction. Similarly, if you use HCl or HI, whether reaction takes place in absence of peroxide or in presence of peroxide, reaction will be always electrophilic addition reaction and intermediate will be always classical carbocation. Remember this. But my dear lovely students, this is point number one. Point number second. If you are having an unsymmetrical reagent like this and reaction takes place with HBr. If reaction takes place in absence of peroxide, product will be Markovnikov's product, and in presence of peroxide, remember, in presence of peroxide, product will be anti-Markovnikov's product. That means you have to add Br to this, H to this in this case, and you have to add Br here and H here in this case. Here reaction takes place via classical carbocation. This is electrophilic addition reaction and this is free radical addition reaction. Remember this. That means peroxide effect is only taking place if it is HBr and unsymmetrical reagent. There will be no peroxide effect. I hope this is clear. After that, we will be having another reaction, that is addition of H2SO4. Have a look. This is an alkene and this is H2SO4. Now tell me, what will happen? What will happen, my dear lovely students? First of all, addition of hydrogen takes place and it will result in the formation of more stable carbocation first. So it will result in the formation of this one. This will become CH3 now. This will be a positive charge and OSO3H minus will be lost. This will be the slowest step or rate determining step. That means similar type of reaction. After this OSO3H minus will attack. And this will be a very fast reaction. This will attack on carbocation and it will result in the formation of this one. This is known as, listen carefully, this is known as alkyl part. This is hydrogen and this is sulfate. So we will get alkyl hydrogen sulfate as the product. We will get alkyl hydrogen sulfate as the product. But listen, my dear lovely students, here you have to rearrange carbocation if possible. If after rearrangement carbocation becomes more stable, you have to rearrange. That means similar type of reaction. Instead of HX, you have HOSO3H. Otherwise, same type of reaction takes place. But listen, Whenever H2SO4 reacts with alkene, this is the product. But sometimes it is written like this. It is written like this. Now it is H2O and then boil. If after this is also there, if this is also there, then this will not be the product. Then replace this by means of OH. That means at that time we will get alcohol as the product. At that time we will get alcohol as the product. We will get alcohol as the product. Otherwise, if this is not there, then we will get alkyl hydrogen sulfate as the product. After that, acidic hydration of alkenes. Now have a look. Say for example, this is alkene. What is meant by acidic hydration? That means you have to treat it with, say for example, H3O positive. Because when water is there and acid is there, both will result in the formation of H3O positive. So this is water and acid, acidic hydration. So first of all, this water will, this H positive will be added. H positive will be added to this. Once again, water will be lost. This step will be the slowest step, rate determining step. Formation of carbocation will take place. So carbocation will result this one. So rearrange if possible. Once again, same type of reaction. Rearrange if possible. Same type of reaction, my dear lovely students. Same type of reaction. Electrophilic addition reaction taking place via classical carbocation. Instead of X, it is OH2 positive here. Now, after this, water will attack now. Water will attack now. That means nucleophile here is water. Water will attack. Water will attack and it will result in the formation of this one. Finally, what will happen? Water will lose, say this OH positive will lose H positive. That means finally H positive will be lost. H positive used here, lost here. That means H positive will act as a catalyst. Now, it will result in the formation of RCH3 and this is OH. Now, whatever will be the value of this R, you can perform reaction easily. So, these reactions, mechanism is very, very, very important for these reactions because you can result in the formation of a carbocation which can undergo rearrangement. That's why mechanism is very important over here. After that, my dear lovely students, addition of halogen. Remember, this addition of halogen can be addition of halogen in non-polar solvent. First one, it can be addition of halogen in non-polar solvent. Listen carefully. Listen carefully. That means if you are having an alkene, what you have to do is very, very simple reaction. What you have to do is, this is very, very simple reaction. Have a look. X2 is there in presence of CCl4, say for example. Just break pi bond and add halogens. That's it. Break pi bond and add halogen. But listen carefully. Addition of halogen is here anti-addition reaction. This is anti-addition reaction. Similarly. Second reaction. Second reaction is addition of halogen in polar solvent. Listen carefully. In polar solvent. Say for example, it's RCH double bond CH2. Then it's like this. X2 and water. Or simply we can say hypohalous acid like this. But listen. What will happen over here? Once again, product will be like this. But here it will be, this was vicinal dihalide. This is halohydrin. But OH and X will be added from opposite side. Once again, an addition reaction. Generally, X2 is Cl2 or Br2. Generally, here X is either Cl or Br. It can be I2 as well over here. But listen carefully, whenever X2 is Br2, if X2 is Br2, So listen carefully, listen carefully. Whenever you use X2 as Br2 or you use Br2 water, that means bromine water or here bromine, then bromine is having reddish brown color. Reddish brown color is decolorized. When reddish brown color is decolorized, that means by using bromine, we can distinguish. That means using bromine is a distinguishing test, or this is test for unsaturation. It is test for unsaturation because reddish brown color during these reaction will be decolorized. So using bromine is basically test for, I mean to say, unsaturation. After that, we will be having oxymercuration, demercuration of alkenes. Now listen, if you are having an alkene and reagent is this, HgOAc whole 2 mercuric acetate and then water. Second is sodium borohydride in basic medium. Whenever these types of reagents are there, you have to add water across carbon-carbon double bond according to Markovnikov's rule. No rearrangement at all. No rearrangement at all. Simple. Break pi bond and add water. Break pi bond and add water according to Markovnikov's rule. That means this will be the product. Negative part of water, OH goes to this, and positive part of water, H goes to this. So this is indirect hydration of alkene. Simple. This is also electrophilic addition reaction taking place via non-classical carbocation mechanism. Here, cyclic mercurinium ion basically results in the formation of that. First, here it is cyclic halonium ion where reaction takes place. So, no need to remember that. You just remember this only. After that, we will be having a reaction known as hydroboration oxidation. Now, what is this hydroboration oxidation? This is also indirect hydration of alkene, but this is very, very important reaction because in this case, water is added across carbon-carbon double bond indirectly by using diborane or borane in a solvent tetrahydrofuran followed by H2O2 in basic medium. Whenever you see these types of reagents, remember we have to add at that time, we have to add water across carbon-carbon double bond. Why across carbon-carbon double bond? Because substrate is double bonded, I mean say species. So you have to add water across carbon-carbon double bond according to anti-Markovnikov's rule. Not according to Markovnikov's rule, according to anti-Markovnikov's rule. That means it will be like this. That means it will be like this. That means negative part goes to that carbon-carbon double bond which is having more hydrogen, and positive part goes to that carbon-carbon double bond which is having lesser number of hydrogens. No need of mechanism, no need of anything. So this will be the product of this reaction. After that, free radical reactions of alkenes. First of all, it's peroxide effect. Have a look. Peroxide effect is also known as Kharash's effect. It is also known as Kharash's effect. It is also known as Kharash's effect. What will happen during this reaction? Have a look. An unsymmetrical alkene is treated with HBr in presence of peroxide. Peroxide can be any peroxide, but for example, I am taking benzoyl peroxide. I am taking benzoyl peroxide, but peroxide can be anyone. Now, what will happen? Anti-Markovnikov's product will take place. So whenever you are having peroxide, HBr and unsymmetrical alkene, add HBr according to anti-Markovnikov's product, according to anti-Markovnikov's rule. Now, it will be like this. So it will be like this. So product will be formed according to anti-Markovnikov's rule. That means anti-Markovnikov's product will be formed. And remember, this reaction is an example of free radical addition reaction. This is an example of free radical addition reaction, and obviously intermediate of this reaction is free radical, and anti-Markovnikov's product is formed on the basis of stability of carbon free radical. After that, we will be having allylic halogenation. Now have a look. Any alkene which contains at least one hydrogen at allylic position, say for example this one, on treatment with X2 in presence of, I mean say light or X2 at a temperature of 773 Kelvin, that means high temperature. This X2 can be either chlorine, Cl2 or bromine. That means what will happen? First of all, it will result in the formation of a radical at allylic position. Now, this radical undergoes, resonance. It will form another radical, but same type of radical. As this substrate forms only one type of allylic radical, that's why only one type of product will be formed. So this allyl radical is replaced by X. So we will get allyl halide. If this is Cl2, we will get allylic chlorination. If this is Br2, we will get allylic bromide. That means allylic bromination takes place. In addition to that, remember, if we want to perform allylic chlorination, we can use sulfuryl chloride, SO2Cl2, in presence at a temperature of 475 Kelvin and in presence of, light or traces of peroxides. Or you can use like this Cl2 at high temperature, Cl2 in presence of, what we call light, or NCS, N-chlorosuccinimide. At that time, this will be the product. This will be the product. But if this is treated with Br2 in presence of light, Br2 in presence of high temperature, or what we call NBS, N-bromosuccinimide. This was N-chlorosuccinimide. This is N-bromosuccinimide. Let me show you. This is basically N-bromosuccinimide. If you replace this Br by Cl, then it will become N-chlorosuccinimide. Now, if we treat this with this, then allylic hydrogenation takes place. This allylic chlorination or bromination takes place. So it will result in the formation of this one. So allylic bromination takes place either by using NBS or Br2 in presence of light or Br2 at high temperature. Similarly, allylic chlorination can take place by using Cl2 in presence of light, Cl2 at high temperature, sulfuryl chloride in presence of what we call high temperature and light and traces of peroxide, or NCS, that means N-chlorosuccinimide. Now after that, we will be having ozonolysis, that means reductive ozonolysis. First of all, what are the reagents over here? Reagents over here are number 1, ozone. Number 2, it can be zinc water. Or number 1, it can be ozone. And number 2, it can be dimethyl sulfide. Generally, these two are used, but generally this one is used. So what will happen during this reaction? Have a look. Whenever you are having an alkene, and this alkene is treated with number 1, ozone, and number 2, zinc water. What you have to do? Very, very, very simple. Just break this bond. Break both these bonds and add double bond O to this, add double bond O to this. Simple. Now tell me what will be the product? C double bond O plus O double bond C. Very, very simple. Now for example, let's take few examples. What will be the product over here then? CH2 double bond CH2. What will be the product? Come on, tell me. Very simple. Similarly, what will be the product? Tell me quickly. What will be the product? Let's take few examples. What will be the product, my dear lovely students? Very simple. Just break this, give double bond O to this, double bond O to this, break this, give double bond O to this, double bond O to this, break this, give double bond O to this, double bond O to this. So product will be simply like this. C double bond O, then it is H over here, and that twice because both are same. Here it will be CH3 CHO plus it is O double bond CH2. That means one is formaldehyde, another is acetaldehyde. Here 2 moles of acetaldehyde will be obtained. I hope this is clear. Similarly, if you are having this one, if you are having this one. Now, what will happen? What will happen during reductive ozonolysis? Just break double bond. Give double bond O to this, double bond O to this. That means product of this reaction is simply like this. Give double bond O to this and double bond O to this. This is already having H, because this is already having one H. So this is the product. It's very, very simple. Similarly, if you are having a structure like this, what will happen? What will happen? What will happen? Very easy. Just break this bond, give O to this, O to this, O to this, O to this. Very, very simple. Very, very simple. So it will be like this. Give double bond O, double bond O, double bond O, double bond O. This is already having hydrogen and hydrogen. This is already having hydrogen and hydrogen. Very simple. Very simple. Sometimes product is given. You have to find out X. Say for example, what is X? If this upon reductive ozonolysis, your product is given. It gives 2 moles of HCHO. We have to tell what is X. Very simple. Try to form this aldehyde in such a way that both these molecules face, their oxygen will face towards each other like this. That means like this. Now remove this double bond O and form a double bond over here, because double bond carbon double bond was there, you form double bond O. If double bond O is there, that means remove oxygen, form carbon double bond. That means our X is simply this one. Our X is simply ethene. So from this is known as retro reductive ozonolysis. Very, very simple. For example, if you are having this one, as the product, if this is the product, now tell me, if this is the product formed during reductive ozonolysis, then what will be this Y? Y is the hydrocarbon, and you have to tell me what is Y. If during ozonolysis or reductive ozonolysis, this is the product. Now listen carefully. This is having CHO. That means this is having C double bond O and H. This is also C double bond OH. Now, in between these two C double bond O, there are 4 CH2 groups. So this is one CH2. This is another CH2. This is another CH2. This is another CH2. So remove these C double bond O and form a double bond over here. That means this is actually this one, cyclohexene. From cyclohexene, we will obtain this one. So either alkene is given, you have to form the product, or product is given, you have to form alkene. This is very, very easy now. After that, we have another reaction, that is oxidative ozonolysis. Listen, my dear lovely students. Oxidative ozonolysis, for oxidative ozonolysis, the reagent is ozone and number second is water. Or we can say it is ozone and number second is H2O2. Now listen. Whenever you are having double bond CH2 during oxidative ozonolysis, convert this into carbon dioxide plus water. Convert this into carbon dioxide and water. If you are having double bond CH and R, this double bond CH will be converted to COH and R is already there. So it will result in the formation of R, this one, and this double bond COH will be converted to COH. And if you are having already C with double bond and 2 R groups are there, then form this in the form of ketone like this. Very, very simple. This is the trick. Remember this. Remember this so that we can simply remember this so that we can simply form products. Have a look. Listen this. Remember this and have a look. Suppose you are having CH2. Suppose you are having CH2 double bond CH2. Suppose you are having CH3 single bond CH double bond CH2. Suppose you are having CH3 CH double bond CH single bond CH3. Suppose you are having CH3, single bond CH, double bond C, CH3, single bond CH3. Then, during oxidative ozonolysis, what will be the product? Have a look. Have a look. O3 and H2O. What will be the product? This is oxidative ozonolysis. Now listen carefully. Break this. And this double bond CH2 is converted to carbon dioxide water. This is carbon dioxide water. That means it is twice carbon dioxide plus twice water. Break this. This is CH2 double bond CH2 is converted to carbon dioxide water. This CH is converted to COH. CH3 is there. So it will result in the formation of CH3, COOH plus carbon dioxide plus water. Now break this. Double bond CH is converted to COH, double bond CH is converted to COH, CH3 is attached to this, CH3 is attached to this, so it is twice CH3, COOH. Now, what about this? Convert this CH to COH, CH3 is attached, that means it first becomes CH3COH. After that, this will become ketone because this double bond carbon is not having any hydrogen, so it will result in the formation of ketone known as acetone like this. Now, after that, oxidation of alkene by using KMnO4 H positive, K2Cr2O7 H positive, hot KMnO4, hot, this is OR, this is OR, this is OR, this is OR, or hot K2Cr2O7. Remember, this is OR. This is same as that of oxidative ozonolysis. Same as that of oxidative ozonolysis. Same products will be obtained from same alkenes. This alkene will give this, this will form this, and this will form this. That means same products will be obtained from these alkenes if these reagents are used. After that, oxidation by using Bayer's reagent. Have a look. First of all, what is meant by Bayer's reagent? It means cold, dilute, alkaline, KMnO4 solution. And whenever you are having an alkene, and if this alkene is treated with dilute KMnO4, that means Bayer's reagent, what we have to do is just break pi bond. Just break pi bond and add OH. That means this is hydroxylation. Add OH groups. OH means hydroxyl. Addition of hydroxyl group means hydroxylation. So we will get 1,2-diol or dihydric alcohol, which is known as vicinal glycol. So this will be the product. This will be the product. But this addition is syn addition. Similarly, if you use, instead of this Bayer's reagent, if you use osmium tetroxide, same product will be obtained. But remember, my dear lovely students, by using Bayer's reagent, this reaction can be used as a test for unsaturation, because during this reaction, when we use Bayer's reagent, KMnO4, its pink color of KMnO4 is discharged because it will result in the formation of MnO2, a brown precipitate. As pink color is discharged, so this is used as a test for unsaturation. But dear students, let me give you some more information over here. If you are having an alkene and you want to add, you want to react this with peracid. Peracid, it's not RCOOH, one oxygen is more in this, followed by hydrolysis. This is also hydroxylation reaction. Remember this. This is also hydroxylation reaction, but this is anti-addition reaction. These are what we call, by using Bayer's reagent or osmium tetroxide, this is syn hydroxylation, but this is anti-hydroxylation or anti-addition reaction. After that, methods of preparation from alkynes. Have a look. But before that, let me know first, is this clear till now? Let me know in the chats quickly so that Next topic will be alkyne, and after that it will be aromatic hydrocarbon, and this will be end of class 11th organic chemistry. Now tell me, is this clear? Is this clear? It will take maximum, I think, half an hour or maximum 40 minutes. Is this clear? Tell me quickly. Is this clear? Okay. It will take maximum half an hour. Now, have a look. Have a look now. Have a look. Let's take methods of preparation of alkynes. Have a look. So from calcium carbide, first of all, we must know that calcium CaCO3, calcium carbonate, upon heating results in the formation of CaO plus carbon dioxide. This CaO on treatment with carbon, it results in the formation of CaC2 plus what we call carbon monoxide. Now CaC2 plus water results in the formation of acetylene or ethine, C2H2 plus CaOH whole twice. After that, another reaction is from vicinal dihalide and geminal dihalide. Have a look. This is vicinal dihalide. This is simple example of vicinal dihalide. When vicinal dihalide is there, this is first treated with alcoholic potassium hydroxide. That means it is a normal E2 reaction. It first results in the formation of vinyl halide, but vinyl halide does not undergo E2 reaction very fast. That's why we use a stronger base than alcoholic potassium hydroxide. That means sodamide. We can use alcoholic potassium hydroxide as well, but yield will be less and reaction will be very slow. And after this will be another E2 reaction. Consecutive two E2 reactions take place, and it will result in the formation of an alkyne. Like this. Similarly, if geminal dihalide is there, have a look. That means both the halogens are present to the same carbon. Then same type of reaction takes place, and first it will result in the formation of CH2, that hydrogen from this position and X from this position, so CH double bond CHX. After that, similar type of reagents are used, and we will get this one, C triple bond CH, alkyne. We cannot use NaNH2 first, because NaNH2 is also a stronger nucleophile. That NH2 will replace this X, so there will be no elimination. But we want elimination so as to form alkyne. After that, from halo form by dehalogenation reaction. This is halo form. Have a look. This is halo form. This is halo form. Whenever this is treated with silver upon treatment with CX breaks CX bond. So have a look. It breaks CX bond. And we can simply say like this. That it will result in the formation of acetylene or ethine. It will result in the formation of acetylene. Have a look. So dehalogenation, this is dehalogenating agent. After that, chemical reactions of alkynes, that means acidic nature of alkynes. So this is basically terminal alkynes. That means those alkynes in which hydrogen is attached to sp hybridized carbon. For example, if you are having this one, this is having two acidic hydrogens because this is having hydrogen attached to sp and hydrogen attached to sp. If this is treated with sodium, first one hydrogen is replaced, after that second hydrogen is replaced. So we will simply say it will result in the formation of disodium acetylide. So it will result in the formation of this one. Plus hydrogen gas will be evolved. If this is used, as this is having only one hydrogen, only one acidic hydrogen, so it will result in the formation of monosodium alkene. Monosodium alkene. Similarly, my dear lovely students, if this terminal alkyne is treated with a base like NaNH2, sodamide, then what will happen? What will happen over here? This is positive, this is negative part. This NH2 minus will attack this H and this H will be lost. So first it will result in the formation of this one, negative charge, and this Na positive, and this H will be lost in the form of ammonia. Then second molecule will abstract this hydrogen, then this hydrogen will be also lost in the form of ammonia with this NH2, and it will form another structure like this. Plus that means ammonia, twice ammonia. Because NH2 minus H positive ammonia, NH2 minus H positive ammonia. Here, only one acidic hydrogen will be lost. So it will result in the formation of this one. Similarly, if you are having this alkyne, and if it is treated with Tollens reagent, say for example Ag NH3 whole 2 OH, this is, or we can say it is AgNO3 in and NH4 OH medium, then what will happen? H will be replaced by heavy metal, that means it will be replaced by silver, and we will get a white precipitate over here. White precipitate will be obtained. Now, you can form side products yourselves. Now, similarly, this alkyne having one acidic hydrogen can form this one. That means hydrogen will be replaced by silver. So once again, a white precipitate will be obtained. But if same type of alkynes are treated with CuNH3 whole 2 OH, that means Cu2Cl2 NH4 OH, then what will happen? It will result in the formation of this one. This is red precipitate will be obtained. Red precipitate will be obtained. Red precipitate will be obtained. And these products are possible only if alkyne loses H positive. That clearly indicates their acidic nature of alkyne. I hope this is clear. After that, addition reactions of alkynes. Now have a look. This is alkyne. If addition reaction takes place in alkyne, what will happen? What will happen? What will happen? Have a look. Have a look. The Z minus will be lost and it will result in the formation of this. It will result in the formation of vinyl carbocation. But whenever addition reaction takes place in alkenes, what will happen? Their carbocation is like this. Their carbocation is like this. Their carbocation is like this. So this carbocation is more stable as compared to vinyl carbocation. That means this is less stable. And we know rate of electrophilic addition reaction is directly proportional to stability of carbocation Now tell me, if rate of electrophilic addition reaction is directly proportional to stability of carbocation, this is more stable carbocation, this is less stable, can I say alkenes can show more, say faster electrophilic addition reaction as compared to alkyne. So that's why reactivity towards electrophilic addition reaction among alkynes and alkenes will be alkenes greater than alkynes. It will be alkenes greater than alkynes. Remember this. Remember this. Now have a look. Addition of HX. Say for example you are having an alkyne like this. You are having an alkyne like this. And you want to add HX. You want to add HX to this. What will happen? Addition of H first will take place. So add H, that means add H to that and X to that, which is say Markovnikov's addition. That means add HX according to Markovnikov's rule. That means you will simply convert triple bond into double bond and add X over here, H over here. After that, add one more molecule of HX to this molecule in such a way that X goes to that position which is already having X. That means according to Markovnikov's rule, and add H to that which is already having H. That means this is having CH2, one more H will be added, it will result in the formation of CH3. So we will get geminal dihalide. That means both halogens will be added to the same carbon. Very, very simple. After that, addition of H2O. That means hydration of alkyne is known as Kocharov's reaction. It's known as Kocharov's reaction. Now have a look. What will happen over here? Alkyne, you have to add water to alkyne. Reaction generally takes place in presence of HgSO4, or you can say Hg2 positive and H2SO4 dilute at high temperature, approximately 333 Kelvin. Add water to carbon-carbon triple bond according to Markovnikov's rule. That means you have to add OH over here and H over here. Negative part goes to this, positive part goes to this. Negative part of water is OH, so enol will be formed. So this is enol. But this enol undergoes tautomerization because its keto form is more stable, so it will result in the formation of this one. Very, very simple. Very, very simple. After that, addition of halogen. Very simple. Whenever you are having halogen which you want to add, say for example addition of halogen is taking place in non-polar solvent, then add halogen. First of all, break triple bond into double bond. Add one halogen to this, one halogen to this. After that, another molecule of X2 in presence of non-polar solvent, it will result in the formation of X and X, then X and X. Tetrahalide will be obtained. Tetrahalide will be obtained. Similarly, if you want to add, this is first reaction, if you want to add once again halogen, but you want to add halogen in polar solvent, that means you want to add hypohalous acid. This is negative part, this is positive part. So addition takes place according to Markovnikov's rule, so it will be like this. Then add another molecule in such a way that the carbon-carbon double bond which is having OH, add another OH to the similar carbon. Add another OH to the similar carbon, so it will result in the formation of this. But two OH groups to the same carbon is unstable, so that's why it will lose water molecule. It will lose water molecule. Once it will lose water molecule, it will result in the formation of this one. It will result in the formation of this one. Very, very, very easy. After that, hydroboration oxidation, very easy. Whenever you are having an alkyne and you are having reagents like B2H6 THF, you are having H2O2 OH minus. Whenever you are having reagents like this, you have to add water. So add water now across carbon-carbon triple bond according to anti-Markovnikov's rule. Now, when you add water across carbon-carbon triple bond according to anti-Markovnikov's rule, you will add OH to this one and you will add H to this one. Now, this is enol. It undergoes tautomerization as keto is more stable than this. So it will result in the formation of RCH2. Then it is C double bond O and H. So if this R value is different, or if this H is not different, here instead of H there is R, different product will be obtained. Very, very simple reaction. Oxymercuration, demercuration. Have a look. You are having an alkyne. You are having an alkyne. And if this alkyne undergoes oxymercuration, demercuration, that means mercuric acetate is there, water is there, and then NaBH4 OH minus is there. So these reagents, whenever these reagents are present, we have to add what? Once again water. We have to add water across carbon-carbon triple bond, but according to Markovnikov's rule. Very simple now. That means you have to add water according to Markovnikov's rule, means OH goes to this and H goes to this. Once again, this is an enol and it undergoes tautomerization. Its keto form is more stable, so it will result in the formation of this one. Very simple, my dear lovely students. After that, it's ozonolysis. Once again, reductive ozonolysis. Have a look. Whenever you are having an alkyne, which undergoes reductive ozonolysis, that means ozone is there, zinc and water is there, what will be the product? How to form a product? Simple. Break two bonds, give oxygen to this, oxygen to this. So, it will result in the formation of R, C double bond O, C double bond O and R. So there can be different values of this R. Put different values of R products. It's very, very, very easy to find that product. So without wasting time, let's say oxidative ozonolysis. For oxidative ozonolysis, remember, you have to convert triple bond CH to carbon dioxide and water. You have to convert triple bond Cr to RCOOH. That's it. Now, if you are having an alkyne like this, CH3, C triple bond CH, then what will be the product upon oxidative ozonolysis? Listen, it's O3 and it is H2O. Now, what we have to do is, we have to break this bond and then we have to convert CH into, say carbon dioxide and water. We have to convert this part into COH. That means the product of this reaction will be CH3COOH plus carbon dioxide plus water. What will be the product over here? If it is HC triple bond CH, what will be the product? What will be the product? Break this, convert CH into CO2 and water, convert CH into CO2 and water. That means CO2 will be twice and water will be twice. What will be the product if it is CH3, C triple bond C, CH3? Come on, tell me. Come on, tell me. H will be simply break this bond, convert this part into COOH and CH3 is attached that. COH and CH3 is attached to that. That means it is twice CH3, COOH. Very, very simple. After that, this is same as that of oxidative ozonolysis. Same as that of oxidative ozonolysis. Now, after that, oxidation by using Bayer's reagent. Remember, if you are having triple bond CH, convert that into COOH. If you are having triple bond CR, convert that into C double bond O and then R. If you are having like this, C double bond O and COOH group, then you have to convert it into COOH plus carbon dioxide after oxidation. Now, have a look. If you are having CH triple bond CH, what will be the product? If you are having CH3, single bond C, triple bond CH, if you are having CH3, single bond C, triple bond C, CH3, then what will be the product? Listen carefully. Listen carefully. And here it is Bayer's reagent. Bayer's reagent, dilute KMnO4. Dilute KMnO4. What will we do? Break this, break this, break this. Then triple bond CH is converted to COOH. Triple bond CH is converted to COH. But as triple bond is, common in between these two COH and these two CH groups, then single bond will be also common. That means it will result in the formation of oxalic acid. Similarly, triple bond CH is converted to COH and this part is converted to CO. So it will result in the formation of CH3CO, COOH first, but this will undergo further oxidation. This will undergo further oxidation and it will result in the formation of CH3. This part is converted to COH, so it will be converted to COH plus carbon dioxide. Now, this part is converted to CH3, then it is converted to, C double bond O, then C double bond O, and then CH3. So this is the product of this reaction. After that, polymerization of alkynes, linear polymerization. If you are having an acetylene, two molecules of acetylene, first, in presence of, CuCl NH4Cl, results in the formation of vinyl acetylene, which on treatment with another acetylene group, in presence of, CuCl NH4Cl, results in the formation of divinyl acetylene. Divinyl acetylene. Divinyl acetylene. That means this H has been replaced by vinyl group. This H has been replaced by vinyl group. So H has been replaced by vinyl group. Now, I hope this is clear. After that, cyclic polymerization. Remember, if you are having acetylene, it trimerizes. It trimerizes if it is treated with red hot iron tube. Red hot iron tube. At a temperature of approximately 873 Kelvin, it results in the formation of benzene. And if it is propine, then under similar conditions, it results in the formation of 1,3,5-trimethyl benzene, commonly known as mesitylene. I hope this is clear. So this was all about, alkynes. Now, last part will be there, and that will be aromatic hydrocarbon. Just a moment. I will drink water. I will take some water. This will be the last part. And I'm going to share PDF on Telegram channel of Unacademy NEET English, as well as on Telegram channel, on my Telegram channel, which I have basically formed few days before, and the address of that Telegram channel is, let me tell you the address of, Telegram channel. Just a moment. It is, you can search it in Google, t.me/K, and after that it is small SIR, then chemistry. Only these two these two K's are capital, all other alphabets are small. Chemistry class. So I will share these notes, I mean a PDF of these notes on this Telegram channel. You can join this Telegram channel if you have not joined yet. Because this is new Telegram channel, I have formed this for you people. So you can join this Telegram channel. You can join this Telegram channel. Now, this is the Telegram channel where I'm going to, share PDF. You can search it on Google. This is t.me/K. Then it is Sir Chemistry class, but Sir Chemistry class is in small alphabets. Now, have a look. Have a look now. Here it is from alkanes. That's aromatization. We have already done this reaction during alkanes. This is done during alkanes. After that, from alkynes by cyclic polymerization, just right now. We have done this right now. Have a look, just now. We have completed it just now. Have a look. It is this one, just completed. After that, another reaction is by Diels-Alder reaction. This is also known as 4+2 cycloaddition. 4+2 cycloaddition reaction. What is this reaction? Have a look. If you are having a butadiene which is having 4 pi electrons, that means if you are having 4 pi electron system, a diene is this, and you are having a 2 pi electron system like this, ethene, this is known as dienophile because it loves this diene, and there will be an reaction between this 4 pi electron system and 2 pi electron system like this. It will form a bond with this and it will form bond over here, and this pi bond will be broken. That means it will be like this. This bond will be formed. This bond will be broken. This bond will be formed. This bond will be formed. This bond will be broken. This bond will be broken. So it will form a 6-membered cyclic transition state. Listen carefully. After that, after this cyclic transition state, the bonds which are broken is this bond, and this bond, and which are formed. So in nutshell, it will result in the formation of a 6-membered ring. So it's a cycloaddition, 4+2 cycloaddition, resulting in the formation of cyclohexene. But remember, whenever you are having cyclohexene, if it is treated with selenium at high temperature, it will result in the formation of benzene. So what is the function of selenium? Dehydrogenation. So this is what we call the reaction. Just a moment. So before this reaction, before 4+2 cycloaddition, let me write down one more reaction, that is reaction number 3. That third reaction is from cyclohexene or cyclohexadiene. Whether you are having cyclohexene or you will be having cyclohexadiene, hardly matters. What matters is, have a look, whether you are having cyclohexene or cyclohexadiene, what will happen over here? Have a look. If you are having cyclohexene or you are having cyclohexadiene, whether that is non-conjugated or conjugated, now you have to remember this one. That if it is treated with selenium, if it is heated with selenium, it will result in the formation of benzene. All are converted to benzene. Now this is third reaction. Then this Diels-Alder reaction is fourth. Then after that, fifth preparation is from haloarene. Have a look. If you are having a chlorobenzene, say for example, or a bromobenzene, this upon treatment with magnesium, in presence of a tetrahydrofuran, magnesium comes in contact. It comes in between magnesium, it comes in between what we call carbon and chlorine, so it results in the formation of phenyl magnesium chloride, once again a Grignard's reagent. This part is having negative part, this part is having positive part. When this is treated with any acidic hydrogen containing compound, say for example water, this will abstract this H positive, so it will act as acid, it will act as base, and it will result in the formation of benzene. So it will result in the formation of benzene. This negative part will abstract this H, and finally we will get benzene, and this hydroxymagnesium chloride will be the side product. Similarly, if this chlorobenzene is treated with nickel aluminium alloy in NaOH, then it will be simply replacement of this Cl by H. That means simple benzene will be obtained. So from haloarene we can obtain benzene as well. After that, from phenol, whenever you are having phenol, if it is treated with zinc, if it is heated with zinc dust, we will get benzene and zinc oxide. After that, from benzaldehyde, listen carefully. If you are having benzaldehyde and you want to remove this carbon attached to benzene ring. How to remove carbon attached to benzene ring? First of all, it should be converted to, say for example, you have to use strong oxidizing agent. For example, K2Cr2O7H2SO4. You can use any strong oxidizing agent, but I have written potassium dichromate in acidic medium, and it will convert this this CHO group to C double bond OH. That means it will convert it to carboxylic acid. After that, this carboxylic acid, this benzoic acid on treatment with sodium hydroxide, it will be simply resulting in the formation of sodium salt of carboxylic acid. So this acid forms salt on treatment with this base. So water will be lost over here. Finally, if this is treated with soda lime, NaOH and CaO in the ratio of 3:1 and is heated, then this Na2CO3 will be lost, Na2CO3 will be lost, and H will be added to this ring. That means benzene plus Na2CO3 will be formed. So whenever you want to remove carbon attached to, say benzene, you have to convert it first to COONA, and after that decarboxylation by using soda lime. After that, from benzoic acid, it is already done. From benzoic acid is done. Have a look. This is benzoic acid. From benzoic acid, it's already done. After that. From benzonitrile is this one. When you are having C triple bond N, cyanide attached to benzene ring. Now, my dear lovely students, first of all, we will do hydrolysis of this. Cyanide upon hydrolysis by using in acidic or basic medium is converted to COH. So cyanides upon hydrolysis yield COOH. Now, this COH is treated with NaOH. Water will be lost, and it will result in the formation of sodium salt of, carboxylic acid. This sodium salt of carboxylic acid on treatment with soda lime, will simply lose this Na2CO3, Na2CO3, and it will result in the formation of benzene. Very simple reactions. After that, from nitrobenzene, remember, if we want to remove N, that means nitrogen group, if we want to remove nitrogen attached to benzene, we have to convert it into diazonium group first. That means first, any active metal, for example, tin, zinc, iron, in presence of acidic medium, converts this NO2 to NH2. First, you have to convert this nitrobenzene to primary aromatic amine known as aniline. Now, this primary aromatic amine aniline is treated with NaNO2 in acidic medium, say for example HCl, or HNO2, nitrous acid, in excess of acid at a temperature of 0 to 5 degrees Celsius, we get benzene diazonium salt. Remember this reaction in which we get benzene diazonium salt from aromatic primary amine aniline by using NaNO2HCl or HNO2HCl at a temperature of 0 to 5 degrees Celsius. This reaction is known as diazotization reaction. Once this is obtained, then if it is treated with H3PO2 water, or my dear lovely students, if it is treated with ethanol, remember, then this N2 bond is broken, and instead of this N2, hydrogen will replace this N2 at that time. So hydrogen will replace N2 from benzene diazonium salts if this benzene diazonium salt is treated with H3PO2 water or CH3CH2OH. After that, from aniline, this is done because this is aniline, this is aniline. So from this is already done. Another preparation number 12 is from benzene sulfonic acid. Have a look. This is benzene sulfonic acid. This is benzene sulfonic acid. This on treatment with water, this is a reversible reaction. It results in the formation of benzene and H2SO4. So if benzene is treated with sulfonic acid, it will result in the formation of benzene sulfonic acid plus water, and these two will form this one upon heating. So I mean to say this is what we call a reversible reaction. After that, we will be having chemical reactions of aromatic hydrocarbons, and those chemical reactions are electrophilic substitution reactions. Have a look. This is benzene. Now, if this benzene is treated with halogen in presence of, say for example, Lewis acid, or in presence of, say for example, AlCl3, FeCl3, FeBr3, or in presence of Fe, then what will happen? These will form, remember, these will form X positive as an electrophile, and electrophile goes to that position which is having more electron density. But we know benzene is having electron density identical at all positions. So we will simply say that halogen will be introduced into the ring and it will replace H, so it will result in the formation of haloarine. So this is halogenation because introduction of halogen has been taken place. After that, if it is treated with nitric acid and sulfuric acid, mixture of nitric acid and sulfuric acid is known as nitrating mixture. Here NO2 positive will be the electrophile, and this electrophile will be introduced into the ring as NO2. This is known as nitration. So this is nitration. Simply. Now, after that, let me tell you, this X2 can be either Cl2 or Br2. Now, after that, if it is treated with H2SO4 concentrated, or you can say oleum. Oleum means fuming sulfuric acid. That means H2S2O7. So it can be anything: fuming sulfuric acid, oleum, H2S2O7, or H2SO4 concentrated. Then the electrophile of this reaction generally is SO3, or sometimes it is SO3H positive. So this electrophile is added to the amine, say is introduced within this ring as SO3 minus first. Finally, it will abstract H positive and it will be added as SO3H. So SO3H is known as, here it is water side product, here it is water side product. SO3H is known as sulfonic acid. So introduction of sulfonic acid is known as sulfonation reaction. After that, if you are having an alkyl chloride in presence of Lewis acid, these two will result in the formation of alkyl carbocation, which can undergo rearrangement if possible. Then this alkyl carbocation is introduced in the form of alkyl group. This is known as Friedel-Crafts alkylation. And finally, if acid chloride or acid anhydride is treated in presence of Lewis acid, the electrophile of this reaction will be simply RC double bond O, acylium ion. Then this acyl group is introduced into the ring. That is why acyl group has been introduced. This reaction is known as Friedel-Crafts acylation. Friedel-Crafts alkylation, Friedel-Crafts acylation, sulfonation. This is nitration, this is halogenation. But remember, sulfonation is basically a reversible reaction. But if halogen, say for example, if halogenation takes place, if chlorination takes place, in presence of Lewis acid, remember, in presence of Lewis acid, it will form Cl positive as electrophile. That means electrophilic substitution will take place. But suppose it is taken in excess. Then what will happen? All the hydrogens of this benzene ring will be replaced by Cl positive. So it will result in the formation of hexachlorobenzene, and it will result in the formation of 6 times HCl. So 6Cl and Cl, 12Cl atoms, that means it is taken in excess. So this is free of what we call, this is simply electrophilic substitution reaction, because these all are electrophilic substitution reactions, because electrophile is replacing this H positive of benzene. So these are electrophilic substitution reactions. After that, it is addition reaction. A simple addition reaction is if benzene is treated with hydrogen. Normally addition reactions of benzene is difficult, but it takes place at high temperature. Then what will happen? Benzene will result in the formation of cyclohexane. Similarly, if halogenation takes place, this reaction takes place in presence of light. When halogenation takes place in presence of light, it is addition reaction. If halogenation takes place in presence of Lewis acid, it is substitution reaction. So this is addition reaction. After addition, pi bond will be broken, Cl will be added, H is already there, Cl will be added, H is already there, Cl will be added, H is already there, because this is already having 6H. So 6Cl will be added and 6H is already there. 6Cl will be added and 6H already there. So in this way, this will result in the formation of BHC, means benzene hexachloride. It's also known as gamexane. It's also known as lindane. It's also known as 666. And this is used in agriculture as pesticide to kill termites, white ants, I mean to say. Okay, this is benzene hexachloride. After that, it's addition of hydrogen. We have already done this. Addition of hydrogen, we have done this. So let me delete this. Addition of halogen is already done. After that, it is oxidation. It is oxidation by using V2O5. Let me tell you, V2O5 is a strong oxidizing agent. It can also act as a dehydrating agent. Listen carefully. If you are having a benzene like this, benzene, and V2O5, it's treated with V2O5 at a temperature of 773 Kelvin. Then just break this bond and this bond. This carbon is converted to carbon dioxide. This is converted to carbon dioxide. This hydrogen and this hydrogen is converted to water. Then what will be the product? This carbon is converted to COH. This is converted to COH. That means it will result in the formation of this one. This is known as maleic acid. This is maleic acid. This maleic acid, in presence of V2O5, at high temperature, undergoes dehydration. It undergoes dehydration. That means OH from one side and H from another side, and it will result in the formation of anhydride. It will result in the formation of an anhydride known as maleic anhydride. Maleic anhydride. But if same benzene is treated with V2O5 at a temperature of 573 Kelvin, that means 300 degrees Celsius. Then it undergoes partial oxidation, resulting in the formation of phenol. resulting in the formation of phenol. Similarly, if naphthalene is there, then this naphthalene similarly breaks this bond and this bond. This carbon and this carbon forms carbon dioxide. This hydrogen forms water. This carbon forms carboxylic acid. This forms carboxylic acid. In nutshell, it will result in the formation of this. This is known as phthalic acid. This is known as phthalic acid. And this phthalic acid, on treatment with V2O5, loses water molecule and it results in the formation of phthalic anhydride. It results in the formation of phthalic anhydride. So this is all about today, and thank you very much. This is all about your class 11th organic chemistry. I hope everything has been cleared, everything has been revised. So I hope this is clear to you, and I am going to forward this PDF, or PDF of this session will be forwarded on my new Telegram channel, that is t.me/K. After that, there is no gap, then SIR chemistry class, but Sir chemistry class will be simply on small alphabets and KK will be capital alphabets. So thank you very much for being very much patient, and God bless you all. And I want you all to be in GMCs. My wishes, my good wishes and my prayers are always with you. But once I end the session, I would want from you all guys to comment. But after ending the session, comment how was the session? How was today's session? You just comment on that, please. And also let me know from which state you are watching, from which place you are watching this session, today's session. So let's meet on Saturday at 11 a.m. On Saturday 11 a.m. we will going to discuss class 12th organic chemistry in one shot as well. So thank you and God bless you everyone. Take care.